an inconspicuous little star on a cosmic scale. The Sun plays a major role in our solar system, in the sky and in our lives. In the solar core, protons fuse together to form helium nuclei, generating heat, warming the Earth and creating clusters of elusive neutrons. The Sun gives us light and life, but it can also bring chaos to civilization unless we can figure out its magnetism. Our galaxy is filled with 1 billion stars. Many of them shine very brightly and eventually become supernovae, while others are doomed to fade away. Among them are singletons and paired stars with and without planets, satellites, and without. Hoping to fathom the stellar mysteries, we will try to reach the very edge of the universe. But ultimately, at the heart of all our knowledge lies the starting point of our journey: the Sun. The Sun is made of plasma and gas, with fusion hydrogen atoms in its core. It erupts its radiations upon us and bestows its life-giving light. Compared to other stars, our Sun can be called mature. It is about 7 billion years old, and it will be another 5 billion years or so before it swells into a red giant and swallows up Mercury, Venus, and Earth. No matter how carefully we study it, our luminaries are still mysterious to us, replete with many strange phenomena. The magnetic calendar on our planet takes 24 hours to wrap around itself once, and 365 days to make one revolution around the Sun. The Sun's own timetable is not so simple. Different parts of the Sun rotate at different speeds. A solar day at the equator lasts 25 days, while the polar regions take a few days longer to complete a full revolution. This uneven rotation distorts the Earth's magnetic field. The rotation of the equator stretches magnetic lines of force toward the pole. Tension is created in the twisted magnetic field, as in twisting rubber band. Eventually, the magnetic field ruptures and releases energy in the form of solar flares or giant eruptions of plasma called coronal mass ejections. This activity obeys a cycle that lasts about 11 Earth years. At the same time, the Sun's overall magnetic field changes direction in each cycle, creating a kind of solar calendar. During solar minimum, solar flares are few. Few sunspots are also numerous. Dark areas on the surface of the Sun with the strongest magnetic fields. During solar maximum, the sunspot becomes larger. The number of flares and cardinal emissions increases. Sometimes the Sun's cardinal emissions reach Earth, disrupting power supplies and damaging its artificial satellites. The latest solar maxima in 2012 and 2015 were unusually calm. One of the weakest since observations began in 1755. Predictions made a couple years before it began promised something spectacular, which shows how poorly we understand the nature of solar cycles. Soap bubbles. Over the course of an 11-year cycle, the intensity of the solar wind, X-rays, ultraviolet, and visible light changes. It is those energy flows that come to us from the Sun that control the Earth's climate. The contribution of the other energy sources combined is 2,500 times less. The cooling and warming that has occurred on Earth in the past has also been largely attributed to solar activity. At present, low solar activity plays no small part in the fact that Northern Europe and the USA have cold winters, while Southern Europe, on the contrary, has rather mild winters. Compared to global warming, though, the impact of solar activity is not so great. In 2003, the NASA Space Agency launched a spacecraft total and monitor controller of the Total Radiation KC and Russian abbreviation, which continuously monitors the total intensity of incident radiation. The apparatus monitors the spectrum of solar radiation, recording the slightest changes in the studied flux. This gives scientists the opportunity to distinguish the human influence on the climate from other purely natural causes, which we cannot control. But solar radiation and jumps in its intensity affect not only the climate. During solar minimum, streams of charged particles, the so-called solar wind, fly from the poles with higher speeds and exert more pressure on matter from interstellar space. The sphere size of the huge bubble of charged particles and magnetic fields that swells around the Sun and makes its way beyond Pluto's orbit increases. During solar maximum, the magnetic fields on the Sun become entangled, preventing the strong solar wind from flowing out. As a result, the heliosphere shrinks. Rains on the Sun. We have found that the Sun strongly influences terrestrial and space weather, but the weather on the Sun itself is spectacular. Super-hot plasma accumulates around the Sun, forming the solar corona. Some of this plasma leaves the corona in the form of solar wind, while other plasma falls back into the Sun in the form of precipitation. Although the existence of such cardinal rainfall was predicted 40 years ago, it is only recently, thanks to the increased power of our telescopes, that we have been able to see it and begin to study it. The cycle is similar to the Earth's water cycle. Moisture on the surface heats up, evaporates, rises to the top and forms clouds. Cooling leads to condensation of the moisture, which falls back to the Earth's surface. At precipitation only on the Sun. The plasma does not change from a liquid to a gaseous state, but simply falls from the side back to the surface as a result of cooling. The scale of what is happening is truly grandiose, and the phenomena itself is very rapid. Drops of plasma rain the size of entire countries fall from an altitude of 63,000 kilometers, which is only 6 times less than the distance from the Earth to the Moon. Sometimes there are vortices in the solar plasma in which magnetic fields spiral and form super tornadoes that extend from the surface of the Sun to the upper atmosphere. A violation of the principles of thermodynamics. Solar tornado phenomena are amazing enough on their own. Perhaps they also help explain one of the strangest solar features of the Sun's atmosphere. Hotter than its surface temperature of 5,700 Kelvin at the surface looks cold compared to the few 1 million degrees typical of the solar corona. Normally, as an object moves away from a heat source, it cools down. The closer the march to the fire, the faster it roasts. But the solar atmosphere doesn't play by the rules. Energy wraps around the Sun's visible surface and flows into its corona. Much of it appears to come from the transition region separating the Sun's corona from the chromium. Spheres of the next atmospheric layer, tornadoes, rains, magnetic, oblique plasma jets, and strange phenomena called speculations. All of these are believed to play a major role in the process of heating the corona, transferring energy from lower-lying regions of the Sun upwards. The details of what is happening, however, are not yet clear and await their researchers. Flights to the Sun. To solve all these puzzles, we need to get as close to the Sun as possible. In October 2018, it was planned to launch from orbit the Solar Research Satellite Orbiter, which is being developed by the European Space Agency. Note the launch was postponed to February 2020. Here and hereafter translators note, unless otherwise noted, it is to fly to the Sun at a distance of 45 million kilometers and photograph its poles. Such images, the first of their kind, will help scientists figure out the cause of the Sun's magnetic field and possibly shed light on why the North and South poles swap each other so often. The probe will also be able to detect incipient solar wind that have not yet reached the Earth. The Parker Solar Probe, NASA's automated spacecraft to study the Sun's outer corona, launched on August 12, 2018. It is expected to fly to the Sun at a distance of 6 million kilometers. The probe will approach circumferentially cautiously, similar to a matador sneaking up on an angry bull. This is partly for safety reasons. As the spacecraft approaches the Sun, scientists will be able to monitor threats posed by radiation or excessive heat that could damage the spacecraft and take appropriate action in time. The apparatus will circle Venus 7 times before reaching its final trajectory. At maximum approach, the probe rushes past the Sun at a speed of 200 kilometers per second. Scientists hope to use it to figure out the mechanisms of coronal heating and solar wind formation. Metals in short supply. We can't swear to the Sun and tear off a piece of it for research. Still, we have 2 ways to find out what it's made of. Gel seismologists study fluctuations in the Sun's surface and can infer from their appearance the chemical composition of the luminary. Spectroscopists study sunlight by passing it through high-tech prisms and dissect it apart, picking out characteristic streaks and lines. A unique barcode to identify the constituent elements. For a long time, these 2 methods painted the same picture. The Sun is composed mostly of hydrogen and helium, with small flecks of other elements left over from the explosions of earlier stars in the universe. Astronomers, unlike chemists, refer to all elements heavier than helium as metals. These elements are found in the inner regions of the Sun and make up just under 2% of its total mass. Although metals are in a distinct minority, they play a key role in transferring energy from the core to roaming layers on the surface. But in early 2000, an embarrassment occurred. Martin Lund, a young scientist from Copenhagen, was investigating the motions of the outer layers of stars in order to make the necessary adjustments to the spectra calculations. He had at his disposal a faculty supercomputer on which he built a 3-dimensional numerical model of the outer solar layer. In 2009, with the help of this model, obtained an unexpected result: was missing 1/4 of the metals, but the presence of which was consistently indicated by seismic data. So far, no one has been able to refute. Bond's results, in light of his findings, have to be reconsidered. Conclusions that apply not only to the Sun, but to other stars as well. After all, our understanding and its cosmic relatives depend on the Sun, the closest to us and the most reachable stars. Not without exotic solutions, suggesting that dark matter inside the Sun will help to harmonize previous data with new ones. But much more plausible is the following assumption. At the extreme temperatures and pressures that exist on the Sun, the heavy elements behave differently than we expected. And the laws of radiation absorption for them are described by other forms. Great hopes for solving this mystery are associated with the neutral age detector, plus an extended version of the experiment implemented by the observatory in a selection installed in Canada. Detecting solar neutrinos is not unusual at present, but with the CH detector. Plus, there is hope to catch a faint signal from rare neutrinos produced in the fusion reaction cycle of turning hydrogen into helium, in which carbon, oxygen, and nitrogen act as catalysts. And thus it will be possible to look into the core of the Sun and estimate the amount of these heavy elements contained there. Long-lost solar siblings. Today, the Sun is walking around in space on its own. Its nearest neighbor is 4.2 light-years away. But it wasn't always this way. Once upon a time, the Sun was in a close-knit family, among kin and friends. Born together from a single cloud of dust and gas, the Sun's relatives scattered in space and scattered hundreds of light-years away from each other. In May 2014, astronomers announced that they had managed to catch one such runaway star named EH-162 826. This star is 110 light-years away from us. With binoculars, it can be seen in the left hand of Hercules. It is slightly warmer and sillier than our Sun, and its mass exceeds that of the Sun by 15%. To find its relatives, a group of scientists led by Ivan Ramazov from the University of Texas at Austin conducted a kind of archaeological dig in space, modeled the movement of stars in the Milky Way. In the past, the goal was to find such stellar offspring that were born in the same stellar cradle of the Sun, although they all scattered in different directions. Their current positions could give away where they were born, narrowing the search group to 30 candidate stars. The team scrutinized them to look for family resemblances. Of all the remaining stars, only 162,826 had a chemical composition similar to the Sun. Their ages also turned out to be the same. Note also the following tantalizing circumstances of these individuals: 162,826 is included in the catalog of stars that may have planetary systems. If more such stars can be found, in the picture of the first moments of the creation of our solar system, maybe a lot of things will become clearer. Maybe it will become clearer under what conditions the suns and planets formed. When will the next space storm begin? On September 2nd, 1859, a giant ejection of matter from the Sun hit Earth. Magnetic fields raged. The aurora borealis lurked where they'd never been seen before. And the sky above our planet was 2/3 covered with unique light patterns. The compass hands went crazy. Telegraph systems around the world failed as too much current flowed through the wires. The phenomenon was named after Richard Nixon, a British amateur astronomer who was the first to make his observations on most of the planet. The event had no effect on people's daily lives. They were admiring a grand light show, and only today an incident of this nature would have catastrophic consequences. Because we depend too much on devices, which are based on the principles of electromagnetism. The satellites would probably burn out all the electrical relays, and with them all the communication and orientation systems. All the transformers would have burned out. The power supply through the backbone grids would have stopped. Public transportation would come to a halt. The U.S. National Academy of Sciences estimated in 2008 that it would have cost $2 billion to respond to the event, and ringtones, surpassing the present. In the U.S. alone, it is clear that space weather prediction should have the highest priority in astronomical observations. To find remedies, we must clearly understand the mechanism of solar magnetism underlying coronal mass ejections. After all, it was the vagaries of solar activity that led to the ringtone effect. How the Sun generates its magnetic fields is still a mystery to us. Therefore, we cannot predict where and when solar eruptions will next occur. As mentioned above, there are high hopes for the European Space Agency's ESA satellite, the present-day orbit, which will be launched to study the Sun. This satellite will measure the Sun's magnetic fields. If we can understand the mystery of the solar dynamo, the effect of the very generation of magnetic fields, perhaps our civilization can avoid a repeat of the 1859 scenario. What happens if a giant comet collides with the Sun? Normally, comets quietly fly around the Sun to get lost in the depths of space. But if it happens that a large comet smacks right into the Sun, a decent amount of height can't be avoided. The SOHO spacecraft, the Solar Observatory, and Heliosphere, under the auspices of NASA, record at least 3 small comets passing very close to the Sun per week. Very small, Near-solar comets usually don't manage to get very far. And it's not even the solar corona, whose temperature reaches 1 million Kelvin. It's too hot and can't melt a comet with its heat. Or rather, heat. This is where the process of sublimation works. Resublimation. Comets directly change into gas, which dissipates into outer space. Comets can split apart, but some manage to survive. Comet J in 2011, although it took a while to get through the solar corona, but still survived the struggle for cosmic survival. But Comet Dyson, which met the Sun in 2014, did not manage to survive. It fell apart. So, what would happen if the comet and the Sun hit each other? The answer to this question was given by a group of scientists led by John Brown, the Royal Astronomer of Scotland. Calculations astronomers have shown the following: if the comet flies close enough to the Sun, more attraction of the central luminary will draw it into a steep peak. Its speed will exceed 600 kilometers per second. At this speed, the drag forces from the lower layers of the Sun's atmosphere will flatten the comet, and it will become flat, like a pancake, supersonic snowball that went straight to hell, so describes the situation Brown himself. Eventually, the comet will explode and burst into flames. As a result of the explosion will be released ultraviolet and X-ray radiation, which we can observe with modern instruments. As much energy will be released as in a solar flare or a cardinal mass ejection. But the spatial scale of the phenomenon will be much smaller. The momentum acquired by the comet can make the Sun ring like a bell, and the Sun's atmosphere will begin to spread. Echoes from the Sun Springs calculation results can be extended to other solar systems in which young stars are subjected to more intense chamber bombardment than our Sun. Had two worlds of iron and rock inside the solar system, and the very side of the Sun nestles for small planets on the scorched surface of Mercury. Only recently have we been able to see the details and map them. The poisonous vapors in Venus' atmosphere would seem like hell to anyone unlucky enough to be there. Let that be a lesson to Earth. And only one of the 4 planets, Mars, so beloved and booed by us, can show signs of living organisms. The third from the Sun. The much vaunted our planet is not touched on in this book. Instead, we're on the Moon. On our, of course, satellite, claiming to be the only celestial body, apart from the Earth, of course, on which the foot of man has set foot. A world of ashes and cinders. Mercury is hardly an ordinary planet. It's a planet inhabited by chimeras. Behind its facades, craters like the cave Moon, lies a heart of metal. And what a big heart it is! Not even Mars can boast such a heart. Mercury's metallic core accounts for 70% of the planet's total mass. Mercury's surface is unusually dark, and its magnetic field is astonishing. All the other planets behave quite decently and revolve around the Sun in the same plane, which is not the case with Mercury. It makes its way at a galling lurch toward the others. Whereas Earth rotates almost in a circle, Mercury prefers an ellipse. Of all the Earth group planets, Mercury is the least studied and raises the most questions. The Messenger probe, sent by NASA to Mercury, was the first spacecraft to orbit the planet, operating for 4 years from 2011 to 2015. It acquired 300,000 images of Mercury and made 1 million measurements of its various characteristics ranging from radioactivity to the chemical composition of the atmosphere. LISA Altitude Mir. Messenger, mounted on the interplanetary station, has measured the height of hills and the depth of craters, and now they're all mapped. These and other data are helping researchers get to some of Mercury's secrets: graphite, crust, Mercury's surface reflects far less sunlight than our Moon and therefore appears extremely dark. Before the Mercury mission, iron and titanium were thought to be responsible for the excessive absorption. But the MESSENGER probe did not detect sufficient amounts of either of these elements. Careful analysis of data taken by the probe directly over the darkest parts of the surface helped to establish the truth. Patrick Pawlowski and colleagues from the Laboratory of Applied Physics at Johns Hopkins University, Maryland, USA, using the method of infrared spectral metrics, along with analyzing the number of neurons in cosmic rays, found that the dark matter on the surface of Mercury is carbon in the form of graphite. The origin of graphite appears to be related to the very early stage of Mercury's formation, when magma was floating all over the planet's surface. Assuming that the chemical composition of Mercury during its existence did not change, almost all minerals formed in the ocean of magma should have fallen to the bottom, and only graphite continued to float on the surface. A graphite shell a kilometer thick could have covered all of Mercury. Later, lavas and flows buried the dark graphite underneath. But in the craters in which we see the original surface of Mercury exposed, this dark substance was preserved. That's the conclusion that Pawlowski and his colleagues came to. However, there is an alternative theory. Namely, that comets, when hitting Mercury in hibernation or its own carbon dust mysterious core, Mercury's presence of a huge metallic nucleus is inconsistent with generally accepted models of planet formation. Such a core could have been left by the planet after a massive collision with another celestial body that collected Mercury, the main part of its rocky mantle. Another theory is that the planet's outer layers vaporized in the hot rays of the nearby Sun. But the MESSENGER probe found volatile elements like potassium in the planet's crust. Such elements would not have remained if there had ever been a major collision or vaporization. However, observations of planets in other star systems have shown that Mercury's structure is not unique. The two smallest exoplanets, Kepler 10 and 7, had their densities measured. They turned out to be much denser than you'd expect. So they have large cores, just like Mercury. In addition, they are also located close to their suns. In 2013, the University of Duisburg-Essen, Germany proposed a hypothesis to explain the presence of a large core in planets of this kind. Gerhard and colleagues suggested the following mechanism: radiation from the star heats up dust particles, which then collide with gas molecules and give them some of their heat. The gas molecules would bounce off the dust pellets faster than they approached them, giving the small ones a small momentum. Calculations with colleagues showed how this force, called the critical force in the photo, makes the dust pellet spin around the star. Since metal pellets have good thermal conductivity, they will all have the same temperature. Such metal pellets will experience shocks from all sides and will not be able to fly far away from the star. Other granules, which later form rocky rocks such as syndicates, are electric from the side facing the Sun. Flying gas molecules will push them harder than on the opposite side. This effect will sort metal pellets from metal pellets at the birth of the solar system. The dense metals will remain at small distances from the star, while the light silicates will be kicked out, and so on. This process may explain the greater density of planets closest to their Sun, such as Mercury, Kepler 10 and 7 on the next Mercury expedition. BEP Colombo was organized as part of a joint mission between the European Space Agency ESA and the Japan Aerospace Exploration Agency. Module with 2 orbital stations should approach Mercury at the end of 2025. Then scientists will be able to answer these and other questions posed by the iron planet. What happened to Venus? Sometimes Venus is called Earth's twin, but in fact, our home planet and its closest planetary neighbor are more like Dr. Jekyll and Mr. Hyde. Note the characters in Stevenson's famous novel The Strange Tale of Dr. Jekyll and Mr. Hyde, which describes the story of a scientist's split personality into two subpersonalities of a well-mannered gentleman and a demonic villain. Venus is about the same size and chemical composition as Earth. It is only slightly more illuminated by the sun than the Earth. Basically, Venus is in the so-called life belt of the solar system, where water can exist in a liquid state. Perhaps Venus was once covered with oceans and there was life in them. Why did it become so hospitable? All attempts to explore Venus have been bogged down by dense clouds of sulfuric acid, completely impenetrable to the first flying spacecraft. Of all the spacecraft we sent out to explore the planet's surface, less than half survived the hard landing, and the rest could not withstand the depressing pressure of Venus' atmosphere. Those that survived soon ceased operations. The total duration of their observations of the planet's surface did not exceed 1 day. The picture obtained by the landing modules was bleak. Misty uninhabited deserts, solved by endless globally acidic rains and sold by caged winds, sharply breathing at sunset and dawn, but dying there or at a hot season of the day. If even you manage to survive in the stifling atmosphere, consisting mainly of carbon dioxide, but the surrounding heat with a temperature of 460 degrees Celsius can melt lead, surely you will be to the end. The peculiarity of the Venetian landscape is usually explained by the fact that the planet is a little closer to the sun than it needs to be to create comfortable conditions. Because of this, all the water on the surface has evaporated. A thick atmosphere was formed, which traps heat and creates the most self-sustaining greenhouse effect. Hence the truly hellish conditions on the planet. However, observations by the Venus Express spacecraft in 2007 put this simple scenario into question. Fluxes of ions were found to flow out of the atmosphere under the influence of the solar wind, which floats freely through Venus' weak magnetic field. In addition, because of the wind, the plasma regularly explodes and rips huge chunks out of the planet's atmosphere. Because of these continuous attacks, not much water can be preserved in the atmosphere from earlier times. The evaporation of moisture may have contributed to the original actual formation of the greenhouse effect, but there must be something else to maintain the suffocating atmosphere of today. And that something could be a factor that has played an important role in the past as well. The most likely candidates for key factors in shaping the composition of the atmosphere, sulfur and carbon dioxide from volcanic eruptions on the surface. No active volcanic activity has been recorded on the planet to date, but evidence of such activity in the past has been found. Data from the Venus Express probe indicate that 80% of Venus' surface is formed by volcanic flows. Some of them are tens of 1,000 years old. By unlocking the mystery of Venus' atmosphere formation, we may be able to eliminate such dead-end planets from our search for Earth-like worlds around other stars. And perhaps Venus' past will tell us what fate is in store for ourselves. Scientists are building models of Earth's future that suggest that in 2 billion years, as the sun matures and its luminosity gradually increases, Earth's climate will begin to resemble Venus. But what if we are wrong in our estimates, and such an ignominious end is just around the corner? Could there be an unaccounted-for factor that will bring us to the brink of survival? Much earlier, these questions sparked a whole series of initiatives to plan new missions to Venus in the hope of finding out if it is really so lifeless and has always been so. But let's take a closer look. Is Venus so hostile? At a height of 70 kilometers above the infernal surface of the planet float clouds, on which established a truly excellent weather, a lot of sunlight, abundant water, pressure and temperature is almost indistinguishable from the Earth. Under such conditions, it is possible to live on the clouds. You'll need a hot atmosphere for exploration. The North Roman Aerospace Company has designed an autonomous, inflatable spacecraft that could drift near the planet for a year, probing its neighborhood for life. An even more ambitious project was proposed by NASA's Jet Propulsion Laboratory. According to her idea, it is necessary to create an airship which will deliver scientists' model and recreate it for possible versions of the development of events on Venus. The scenarios differed slightly in details, such as the amount of energy the planet receives from the Sun or the longitude. Venus Trial. Where scientists lacked objective data, they filled in the gaps with plausible assumptions. The unusually high ratio of deuterium atoms to hydrogen atoms found on Venus is a sure indication that once upon a time the planet could not complain about the lack of water. So the scientists included a shallow ocean in their model. After considering the evolution of each version of their model, the scientists concluded that Venus in the past may have strongly resembled Earth in its early stages of development. It could also have been a haven for living organisms. The model suggested that the planet could have been habitable as recently as 700 million years ago. The most promising Venus in terms of the existence of life was characterized by moderate temperatures and dense cloud cover. A peak of an Iranian sky occasionally drizzled a light snowball. Greenspan argues that both patriarchal land and led to positive results. NASA is now considering two alternative projects. One involves sending a probe that asks for cloud cover and applies it to the surface. And in the other, the spacecraft simply flies and takes pictures of the planet. The researchers are not going to stop there. They want to build and other alternative models of the evolution of Venus. For example, the planet could have been a desert in the past or, on the contrary, was almost completely covered with water, like Earth. In this way, it is possible to find the most likely scenario that would lead to the pattern observed on Venus today. Why? Apollo missions and the birth of the Moon. In 1969, the whole world watched disappointedly as Neil Armstrong and Buzz Aldrin bounced around on the surface of the Moon. At the same time, the planets anticipated a valuable prize. The astronauts of the Apollo 11 mission were to return to Earth with a unique booty. The planet was not disappointed. By the time the astronauts climbed into the lunar module for the last time, they had collected 22 kilograms of moon rocks. The 5 crews of the following Apollo missions brought back a collection of moon rocks consisting collectively of 2,200 numbered specimens with a total weight of 382 kilograms. 3 automated lunar rovers from the USSR collected and delivered 300 grams of lunar soil to Earth. All samples of lunar rocks were declared the property of science. They were to overturn our ideas about the formation of the planets and dispel the many myths associated with the Moon. Harold Urey, one of the ardent supporters of intensive lunar exploration, predicted that the Moon was made of ordinary meteoritic material. He was wrong. A number of rocks could well pass for terrestrial specimens, especially the darker basalts that give the lunar seas a peculiar grayish hue. But there were others. For example, the ubiquitous and piled-up rocks like fragments of breaches shattered and mended into a single whole by meteorite impact over 1 million years. It took more than a year to decipher the message encapsulated in the lunar soil samples. And to this day, scientists continue to argue fiercely about these rocks. A huge surprise was the announcement that the ancient Moon was covered by a deep ocean of molten rock. The Moon's mountainous regions are dominated by magma-optic rock, rare on Earth, which forms when light aluminum-rich minerals float up. on top of the lava basin. If oceans are ubiquitous on the Moon, then its entire surface must have once been flooded with an ocean of AAR. And here's the mystery of how this AAR ocean came to be. At present, the prevailing hypothesis is that about 50 million years after the beginning of the formation of the solar system, there was a catastrophe of planetary scale. Then the Earth was still in its infancy, and this proto-Earth crashed into a planet the size of the current Mars. Fragments from the collision of the two celestial bodies grouped in orbit around the Earth fused into a single whole and formed the Moon. Samples of lunar soil delivered by astronauts seem to contradict this idea. According to the giant impact hypothesis, lunar rocks must partially contain material planted by another protoplanet. It is logical to expect them to be slightly different in composition from Earth rocks, in particular, to contain different numbers of isotopes of the same element. But scientists from the University of Chicago and colleagues said in 2012 their weighty word isotopes of oxygen, chromium, potassium, and silicon in lunar rocks are indistinguishable from those on Earth. Some scientists have argued in favor of revising the theory. Wim van Wee of the Free University of Amsterdam suggested that the Moon came from a giant nuclear explosion that occurred inside the Earth. Other scientists did not want to completely abandon the giant impact theory, but modified it slightly. Small compared to the early Earth, the celestial body crashed deeply into our planet, which was characterized by rapid in strength, rotation, and partially destroyed it. A plume of dislodged Earth rocks followed in its orbit and eventually formed the Moon. The Apollo samples held another surprise for scientists. It turned out that the largest impact craters on the Moon formed around the same time. Their ages range from 380 to 4 billion years old. The Moon, and probably the Earth as well, suffered a crushing attack 500 million years after the solar system formed. There must have been some major event at the back of the solar system that triggered this attack. Perhaps the orbit of Neptune or Uranus shifted, triggering a violent stream of comets toward the Sun. Curiously, this episode in the evolution of the solar system, called the lunar cataclysm or the last meteorite bombardment, ended at a time when the first signs of life appeared on Earth. Did it not create the conditions in which life could have originated? The last meteorite bombardment and the theory of the formation of the Moon by a giant impact. Two important presuppositions that caused scientists to radically revise the picture of the evolution of the solar system in the pre-Apollo era pertain to the system of celestial bodies revolving around the Sun like clockwork gears. They simply rotate next to each other without colliding or interfering with each other. Now it became clear that in the planetary family can occur truly dramatic events, as if someone shuffled the planets like cards. At the same time they can merge or, on the contrary, fly apart from the deck. None of the inner planets escapes the collision. And the Moon shows this particularly well. Without soil samples delivered from the Moon, it would be impossible to reach these conclusions. Do Moon rocks hold undiscovered secrets? Instruments for determining the age of minerals are becoming increasingly sophisticated. They can now tell the age of the tiniest flecks of rock. New methods of determining the age of rocks have forced us to take a new look at dating major milestones in the Moon's history. Basically, the Moon formed about 4.5 billion years ago, 20 to 30 million years earlier than thought. The last oceans of liquid magma asserted themselves about 4.417 billion years ago. Questions remain that the Moon rocks from Apollo will never be able to answer. What awaits us on the visible side of the Moon? Will we be able to recreate a detailed picture of the lava flows that became basalt, the bottom of the lunar seas? Will we be able to get samples of rocks buried deep beneath the surface? Finding answers to these questions gives us a powerful incentive for new missions to the Moon. Red rivers. The prospect of finding life on Mars, whether in the past, present, or future, hinges on the presence of liquid water. But the possibility of finding water on Mars is vanishingly smaller during the warm seasons. Oblique lines and dark streaks regularly appear on the surface of Mars. Over the course of a Martian year, they lengthen and then fade away. Streams of salt water were thought to run down crater walls and hillsides for long periods of time. The presence of salts in water can lower the freezing point of water, and theoretically, even on Mars with its cold climate, water could exist in a liquid state. In 2015, this idea found confirmation. Using a spectrometer installed on the Mars Reconnaissance Orbiter Station, abbreviated MRO, the NASA orbiter analyzed reflected sunlight. This made it possible to determine the composition of the minerals lying on the surface. Spectral data obtained at 4 points on the surface, where characteristic elongated structures are regularly observed, revealed the presence of salt hydrates, most likely chlorine, acidic magnesium, raven, acidic magnesium, and chlorine, acidic sodium. If it could be confirmed that there are indeed rivers of salt water flowing across the surface of Mars, it would add to NASA's determination to engage in a more persistent search for life on the red planet. In the Atacama Desert, it is among the places on Earth least suited for life. Colonies of microbes have been found caused by moisture created by salts, absorbing water from the atmosphere. Optimists believe that similar microbes could live on Mars. But what if the mysterious dark jets are not watery at all? After all, on Mars it is very difficult to melt ice or extract it from a resultant dry atmosphere. The structures one would like to mistake for water may turn out to be sand pens. They may be moved across the surface by sunlight. Friedrich Schmidt and his colleagues at the University of Paris South 11 believe that we are dealing with sand wine. Similar structures can be observed on Earth's dunes. Windy day. On Mars, they appear from the endless play of light and shadow. Sunlight heats only the upper layers of sand, while the deeper layers remain cold. The temperature gradient changes the pressure of the tiny gas bubbles surrounding the sand grains, and the gas shifts upwards. This, in turn, pushes and propels the sand and soil particles, causing them to slide down the Martian slopes. This effect should be most pronounced in areas that are in shadow at 12 o'clock noon, casting large waves or protrusions of exposed rock. Then the contrast between the cooler sandy top and still warm lower layers will create a second temperature gradient, shifting the gas and sand even further away. In late 2017, they further analyzed images taken by the Mr. Orbiter about. The analysis confirmed yes, the avalanches are most likely not water avalanches. The dark lines only appear on slopes deep enough where dry sand grains can roll down, similar to what happens on sand dunes. According to Colin Dantes, lead scientist at the U.S. Geological Survey's Austro Geological Research Center, Arizona State Flag, new evidence suggests that Mars is now dry, a dehydrating desert. If it is confirmed that the recurring oblique lines are not created by water, it will greatly shake our hopes of finding aboriginal organisms on Mars and make it more difficult for future settlers to colonize Mars. The ocean that wasn't supposed to be there. Mars' past also remains a mystery to us. Mars has ice caps and apparently once had no shortage of liquid water. Clay minerals, as well as lake and river sediments, unequivocally confirm that during the time period that began 4 billion years ago and ended 3.5 billion years ago, Mars had full-flowing rivers and probably splashing oceans of impressive size. There are extant signs of giant tsunamis hitting the coastline. Alberto Ferrer and his colleagues at the Astrobiological Center in Madrid applied thermal imaging to images taken by NASA's Mars Odyssey orbiter. They scrutinized the boundaries between a lowland area called the Plain of Christ and the Mount Arabia. Earth. Ice and cobbles appeared clustered as if they had run up the hills to occupy a space of hundreds of kilometers on the highlands. Such a pattern is difficult to explain by the effects of gravitational attraction, but it could well have been generated by a tsunami. A large asteroid, for example, could have hit the surface of Mars. This impact would have formed a 30-kilometer crater and caused a giant tsunami. Tsunami waves 50 meters high would have crashed onto the coast and driven up rocks, sweeping them away. This is the picture created by one of the computer models. And yet we can't understand exactly how water could exist in hard form on Mars, when the red planet was still relatively young. Scientists have been unable to solve this mystery for 40 years. It's even been called the Mars paradox. If we ever find the answer, we may have to throw out a lot of textbooks. The problems start with the fact that conditions on Mars at the time were even harsher. Even today, the average temperature on the planet is -61 degrees Celsius. Because the atmosphere is resolved and the sun doesn't warm much, water is concentrated in ice caps at the poles. 1 billion years ago, the sun was younger, it had not had time to warm up properly, and Mars was even colder. Let's assume that the freezing point of water on Mars is the same as on Earth. What could have melted the Martian ice and made liquid water flow across the planet's surface? One plausible explanation is that greenhouse gases trap Martian heat just as they do on Earth. The gases could come from a variety of sources, such as when their volcanoes erupt. The best heat trap is carbon dioxide. But even it can't heat the planet to a temperature hot enough for liquid water. In any case, sediments formed 3.5 billion years ago show the presence of very little carbon dioxide. Can the situation be salvaged by adding some methane or hydrogen to Mars' atmosphere? No. With little CO2 for warm fission, the methane or hydrogen content is irrelevant. A dense atmosphere is required. Only it can protect these sensitive greenhouse gases from solar radiation. But maybe the salts in water can keep it liquid even at temperatures below freezing? Then a lot of carbon dioxide wouldn't be needed. However, this explanation doesn't fit either. Salt water can form rivers and streams. At least there are salty rivers on Earth. But it is still difficult to explain where the non-flowing water came from. Tracks that have been printed into limestone sandstone for 1 million years on Mars with its cold temperatures simply could not have had enough precipitation to form standing water. Apparently, there is some planetary scale mechanism that we have no clue about yet. What it might be, a new unusual mix of greenhouse gases or properties of water that have yet to be discovered. We will enter completely unknown territory when we unlock this mystery. Interview: How did I spend a year on Mars with Shane Giffords? Spent a whole year living in a dome on the side of Shane's volcano. Chief Medical Officer of an expedition sent by NASA to see if the first settlers could survive on Mars. Below is an interview. She was interviewed by a New Sanchez magazine reporter in 2017. How did you and 5 other team members get to the volcano in Hawaii? NASA leaders set out to find out how the 6 crew members would behave, what their psychological compatibility would be in isolation. If they were sent to another planet, would we be able to work together? How would we respond to the inevitable stresses of such an environment? How would we conduct communication sessions with Earth? It was the longest simulated Mars mission program NASA had undertaken, and it was called the Hawaii Spaceflight Simulation Expedition. Note: the longest of all such experiments to simulate a flight to the Red Planet is considered Mars 500, conducted in Russia in 2010-2011 with the participation of 6 volunteers from Russia, France, Italy, and China, who were in complete isolation for 520 days. 6 people participated in the experiment, which took 366 days and ended in August 2016. We lived in a metal occupation. Who was part of the expedition? Our group consisted of a commander, a research scientist, a biologist engineer, an architect, and me, the expedition doctor. We wore electronic sensors at all times to monitor our interactions with each other. We were essentially lab rats, but that didn't stop us from doing science. We did geologic studies of the mountainous terrain, tested hydro, bottom-feeding methods of growing food, and studied our own volume. What is life on Mars like? All our communications with the outside world were on a 20-minute delay. That's how long it takes for a radio signal to travel from Earth to Mars. The slight variations are due to the changes in their relative position in space. We weren't allowed to use the telephone or Skype. We left our home only in spacesuits, and for a year, we didn't see a living soul. People were fighting with each other. We had some personal disagreements, but in the most difficult times, we remembered that we were professionals. When you think about the fact that you have to fulfill your obligations, that the mission cannot be interrupted, it keeps the group united. It was a big lesson for all of us. What challenges do you remember the most? The most difficult was the second quarter of our stay at the station. We started to run out of energy and food. Due to administrative problems, we did not receive the promised resupply. We only had 2 kinds of dried vegetables left, spinach and curly kale. And no one wanted to eat them, and it was very cold. The moral climate in the collective left much to be desired. But in such expeditions, one should always expect some kind of a trick. But we learned a good lesson. Having overcome a difficult period, our expeditions learned to cope with the convo and apologize in their rooms when it got cold. This habit has helped us in life ever since. Then things got better. By Christmas, reinforcements came in the form of a 3rd battery. Now, even though the days were getting shorter, the energy stored during the solar panel's daytime charging was enough to run for a day and a half. Everything went as well as it could. We managed to hook up the heater. We started cooking hot food for Hanukkah. I cooked a festive dinner and taught everyone a traditional Jewish game. How did you celebrate the holidays on Mars? That's an interesting question. Really, what is the meaning of the Christmas holiday on Mars? It has nothing to do with the Martian seasons and nothing to do with anyone that could live or die on Mars. Instead of Christmas, we celebrated non-religious holidays. Our holiday debuted with the first harvest of Ustra tomatoes. The expedition biologist had been growing these tomatoes for months. He grew them hydroponically in bottles because we had very little soil. We were living in conditions as close to Martian as possible. We each got 1 tomato. We set up plates, sprinkled dried parsley on them, lit candles, and dressed up in honor of Great Tomato Day. That's what we called the holiday. In the past, for months since the expedition began, the first fresh tomato. I took my tomato and for 10 minutes just enjoyed the smell of it. It gave off such an aroma, it was as if I was in a jury rig filled with bold fruit. When I finally tasted it, it burned my head. Tomatoes, and there was nothing wrong with it. It was something wrong with my lips. It's not like we didn't eat any acidic foods. Tomatoes were only present in our diet in powdered form. I had to eat that tomato very carefully. Did you miss your family, your friends? I missed them a lot. Their emails were a big help to me. I saw the suffering of crew members who didn't have that support. If someone sends you emails, it means you are still alive and someone is interested in you. Based on your experience, what can you say about the feelings that the first colonists on Mars will have? If you take a Martian who was both born and raised on Mars and move him or her to Times Square, he or she will be shocked to see how much electrical energy is wasted in an absolutely priceless way. All the electricity we generated in a day in advertising lighting would burn up in seconds. Earth's trash cans are filled with things that we Martians would never throw away. We would either keep using them or melt the waste and print something useful out of the resulting mass on a printer. On Mars, you see, you begin to appreciate things in terms of their real usefulness. Money, for example, is completely useless. The only thing that matters is your intelligence, your adequacy, and your abilities. What is it like to be the chief medical officer of an expedition? Being a doctor takes on a different connotation. You regain the demeanor of a sophisticated, old-school city doctor, like a family doctor who talks to people about their health, trying to keep them from getting sick. If they do get sick, your options for helping them are very limited. The first feeling a doctor wakes up with in space is a longing that he doesn't have to do his specialty work today. We were lucky. Only one person was seriously injured during the mission, and that was me. While doing survey work on the terrain, a frontal tube came down on me and injured my knee. Have you done experiments with virtual reality? Explain what that means. NASA scientists set out to find out how creating virtual reality could help with loneliness and boredom. Now looking for us away from home. They constructed a corner of the Earth's panorama for us using 360-degree cameras and recorded sound. The equipment in Wasdome created this panorama for us. In its detail, I found myself in Boston, put on my glasses, and suddenly found myself on a familiar street. People were looking at me, whether gesturing or not. Everything felt very real. I felt like I was on the ground. I think it's a great idea to apply virtual reality to Mars. The day I took part in this experiment, my grandmother had just passed away. She was old. It was to be expected. But I found out about it late because expedition rules didn't allow you to turn off the communication delay. The situation was not categorized as a crisis. The video came later. I said goodbye to her when she was gone. It was a difficult situation. I was worried sick afterward. Some might say that it's better to send people into space who have little or nothing to lose. Wouldn't you agree? The question is a little different. Is it better to send people who are outgoing or reserved? I'm in favor of sending people who have a lot of earthly attachments for several reasons. First, if relationships between team members go sour, they can get support from their family and friends. In the second, they will do everything in their power to return. They will save the ship and accomplish the mission. And finally, perhaps the most compelling reason people who stay on Earth would also like to fly, but can't. And they would like to see a very contact citizenry in space that would be in constant communication with Earth. We should send people from different countries with different religions. easily adaptable to different situations. After all, you will be out there in space not for yourself and your ambitions, but for the Earth. Chapter 3: Among the Giants. Each of the 4 giant planets of the solar system is remarkable in its own way. On them terrible storms rage, supersonic winds blow, no outlandish clouds sail higher, and the surface of primitive waters conceals immeasurably and profoundly. No less surprising are the satellites of these planets with their oceans, epitomizing the primordial horror and darkness with volcanoes red and lakes and torrential rains. The king of the planets. Jupiter exceeds in mass all the other planets in the solar system combined. Its gravity forms an asteroid belt. Its powerful magnetic field contains hard radiation belts. Along the way, Jupiter acts as a cleaner in the solar system, sparing us from an invasion of stray comets. Its gravitational fields serve as a safety shield for Earthlings. In July 2016, the Juno probe entered orbit around Jupiter. NASA sent the Space Interplanetary Station to study the planet's processes and structure. 9 instruments Juno and diligently penetrated with their mechanical gaze into the depths of the giant storms that constantly rage on Jupiter. The probe drew a picture of the distribution of gravitational and magnetic fields, looked for signs of a solid core, and observed flashes of auroras. Dashing the planet's atmosphere. Juno had an unusual trajectory. The space station's path ran not along the gas giant's equator, but over its poles. This kept the station at a safe distance from Jupiter's traditional belts, which pose a clear danger to the electronics and electrical systems of spacecraft. The spacecraft circled Jupiter 37 times. In early 2018, a hard landing on the planet was commanded and Juno ceased to exist. The first data obtained in April 2017 challenged all our ideas about the planet from its atmosphere to its internal structure. They found a dense zone of unusual gas in Jupiter's atmosphere along its equator. In other areas, ammonia was more resolved. Undoubtedly, Jupiter depends heavily on the presence of ammonia to shape its weather. We knew before that Jupiter is shrouded in clouds, but the existence of a belt of ordinary gas penetrating to such depths, and it extends 300 kilometers deep from the cloud, came as a surprise. The weather on Jupiter affects a vast range of altitudes. This was also news to scientists. Another surprise: Jupiter's magnetic field turned out to be very powerful, and the magnetosphere has an irregular shape. The curvature of the field may be caused by an unusual dynamo effect. It forms in several of Jupiter's inner layers, which are far from the core. Perhaps a layer of metallic hydrogen. Already in the first stages of the study of the planet, the probe obtained important information about its atmosphere. The camera recorded and sent back to Earth images of dozens of giant, the width of hundreds of kilometers cyclones raging over the poles. Previously, their existence was not even suspected. In the belts to the south of Jupiter, man equator noticed strange white shafts. Perhaps these are clouds consisting of ammonia and hydrodynamics. The latter substance is used on Earth as rocket fuel, dissolving the nucleus here. The probe has also challenged models of Jupiter's internal structure. It was previously thought to be fairly homogeneous inside. The atmosphere, made up of molecular hydrogen, extends about 1,000 meters deep. It was assumed that in the lower layers, due to the enormous pressure, hydrogen turns into metal, protons wander into the sea, drops of helium and other elements can fall from the atmosphere in the form of rain, and even lower, at a depth of 70,000 kilometers, there was supposed to be a small solid core. This picture of Jupiter's structure was based on data about the planet's gravitational field. But the very first measurements of the gravitational field, made by Juno, made corrections to this model. It turned out that the inner layers of the planet are not so homogeneous in their composition. Jupiter's core is not solid like Earth's, but rather eroded. It is penetrated by the overlying layers of metallic hydrogen. This picture is consistent with earlier 2011 calculations of Jupiter's internal structure, according to which the planet's solid core may be gradually dissolving like a pill tossed here. It is currently believed that giant planets such as Jupiter and Saturn are solid bodies composed of rock and ice during their initial stages of development. Then, when they reach 10 times the mass of Earth, their gravitational field begins to suck gas out of the parent nebula. A dense atmosphere forms around them, consisting mostly of hydrogen. Amusingly, according to some studies, the mass of Jupiter's core is less than 10 Earth masses, while the core of Jupiter's smaller counterpart Saturn is packed with 15 to 30 Earths. Some researchers have suggested that the high pressure and temperature in Jupiter's core could cause its core to dissolve into the surrounding atmosphere, which behaves like a liquid at such high pressure. Hugh Wilson, now at the Government Association for Scientific and Applied Research in Melbourne, Australia, and Eberhard Peace of the University of California, Berkeley. The US used the equations of quantum mechanics to understand how the mineral magnesium oxide, thought to be part of Jupiter's core, behaves. At a pressure similar to that of Jupiter, about 40 million times the normal atmospheric pressure on Earth, and a temperature of 20,000 degrees Celsius. They found that under these conditions, magnesium oxide does dissolve into a liquid dissolution medium. The rocks could eventually mix with the rest of the atmosphere on Saturn, which has about a third of the mass of Jupiter. The conditions are not so extreme. If Saturn's core does dissolve, calculations suggest that dissolution will be slow. On planets more massive than Peter, however, the process is much faster. Because of this, many large exoplanets may have no nuclei at all. The side of the loblaws on Jupiter's satellite Io. From the food given by the surface pits, and we intense radiation and denial, and constant volcanic eruptions. It is a fiery hell in the solar system, but it is also very cold, and much of it is covered with frost from the surface asteroid. At the same time, this satellite, the closest to Jupiter, has the most active volcanic activity in the solar system. Io's volcanoes spit out 100 times more lava than all of Earth's volcanoes, although its surface is 12 times smaller than Earth's. Its surface is dotted with bubbling lakes of molten rock. The largest of them has a loca and a half, with a diameter of more than 200 kilometers. In other places, magma suddenly pushes its way out of cracks in the rocky crust, creating a string of living fountains that can stretch for 50 kilometers or more. In 2007, NASA's New Horizons spacecraft recorded thermal radiation from one of these huge fire curtains as the probe flew past Jupiter on its way to Pluto. Some eruptions are both powerful enough to throw a giant plume of both gas and dust up to 500 kilometers into space. This happens when a head-on flow vaporizes the surface layer of a frozen surface hybrid, or when gas bubbles form inside the rising magma and eject rock fragments outward at high velocity. All this volcanic frenzy is the result of a love attraction and gravitational struggle between Jupiter and two congeners, or Europa and Jupiter. The orbital periods of these satellites are exactly 2 for 4 times the orbital period of Io, respectively. This causes all 3 of these satellites to line up quite often as a result of the gravitational influence from these periodic oppositions. Io's orbit has gradually taken on an increasingly elongated shape. As Io moves and orbits, Jupiter's gravity rises and falls, deforming the surface of the satellite. The overloads and stresses heat the satellite from the inside out. This process is called tidal heating. The heating effect on Io is so strong that rocks melt and volcanoes form. In 2013, researchers studied images of 3 hot spots on Io taken by the Cassini probe in late 2000 of volcanic regions. Ilona, the author of Veil of the Andes and Loki. Scientists Daniel Allen and his colleagues at Tunica College in Tunica, Illinois, USA, calculated the temperatures in the 3 lakes and found that the lava in all of them is likely molten basalt. They also found that each volcano has its own style of eruption. Bilan is the idea behind all 3 of the previous 3. Probes observed it erupt in 1997 and toppled. There was enough lava to cover 5,600 square kilometers of the satellite's surface. Temperature measurements from the Cassini satellite show that it is now surrounded by a high ring of incoming rock, created around a gentle lake 1.5 kilometers across. Meanwhile, it's starting to kick out. Allen says it's either a leaving lava flow or a lava lake during a period of low activity. As for Potra, Loki is the name in Germanic Scandinavian mythology, belongs to the god of cunning and deception. This huge formation extends 200 kilometers and radiates about 13% of the total heat of the satellite Io. If a passerby happens to land on Io, he could find himself either on a solid corridor that will be able to support the weight of his warm insulated rover, or in a molten quagmire. He might also find himself among the glittering fountains of Lane. Such excessive volcanic activity in the expanse of the universe, however, may be commonplace. For example, an exoplanet's orbit to itself is very close to its star, and exoplanets are strongly attracted to it. Even a slight elliptical orbit is enough to make the entire planet covered in volcanoes. Because of the decent heating, so that can give us an idea of the conditions on 1 million of these hellish exoplanets. But the orbit also appears to be cooling. Perhaps because the satellite's orbit becomes less and less elongated after tens or hundreds of 1 million years. The orbital resonance with Europa and Honey will probably open up, allowing it to settle into a nearly circular orbit that will leave the satellite without decent heating. Then the lights of Io will go out. Deep dark seas. The thesis "seek water" has long been a mantra in the search for life, because every organism we know of needs water to survive. Mars remains the most promising for water, but its water has either long since evaporated or is in a soil-bound state in the form of ice. Meanwhile, Jupiter's satellite Europa and Saturn's satellite Enceladus boast deep oceans filled with liquid water that splashes beneath their frozen upper shells. Astrobiologists are worried about whether these waters are capable of bestowing life to unknown non-terrestrial organisms. At least in the extreme form, they exist at the bottom of Earth's deepest ocean trenches, where life thrives only through the interaction of glowing magma and water. Scientists are eager to hear the hum of such underwater biochemical interactions on Europa and Enceladus to answer the question, are we alone in the solar system? The first hints of Europa's hidden sea came from the Voyager probes, a whole series of which explored Jupiter in the 11970 OS. Voyager 2 noticed cracks in Europa's icy crust, indicating active processes beneath the surface. The Galileo spacecraft circling Jupiter in the 11990 X found another phenomenon proving the existence of a liquid ocean beneath the surface. Force lines of Jupiter's magnetic field were excluded near Europa, which means that it has a magnetosphere. Apparently, there is a layer with good electrical conductivity, a network, most likely an ocean of salt water. Now we believe that this true ocean extends 100 kilometers deep into Europa. If so, it contains enough salt water to fill the Earth's ocean basins twice. The question of a sea on Hellas has only recently arisen. In 2005, the Cassini probe showed that Enceladus was leaving a distinct imprint in Saturn's magnetic field, something interacting with its magnetic field. That something turned out to be a fantasy come true, and a plume of ice particles and water vapor shooting out into space through cracks near Enceladus' south pole. Cassini has flown through this plume several times since then. First, its instruments detected the presence of organic compounds. Particles collected at the bottom of the plume were rich in salt, indicating an ocean spreading out below. Cassini also found ammonia, which acts as an antifreeze that prevents water from freezing even at low temperatures. All indications were that there was an ocean of liquid water beneath the surface in which primitive life could exist. News was pouring in like a cornucopia. In March 2015, scientists from the Cassini team discovered a plume of their silicate grains. These particles likely formed here in reactions to hydrothermal springs. By September of that year, measurements of the movements of Enceladus' outer crust convinced scientists that an ocean 26 to 31 kilometers deep existed beneath the surface. Compared to Europa, that's a frog. But this ocean is much deeper than Earth's oceans. So when is the next trip to these parts planned? NASA is going to send a probe to Europa in June 2022. It will be equipped with magnets to determine the ocean salinity and a radar that allows a signal that passes through the ice. This will make it possible to find out where solid crust is replaced by liquid water. The probe could also include a landing module to catch amino acids, the building blocks of proteins used by every living thing on Earth. NASA has also issued a call for proposals for a trip to Enceladus. One of them is sending a probe searching for life on Enceladus. This probe would examine samples of the plume with instruments capable of detecting large molecules and scrutinize and chemical composition. Some projects even propose to bring these samples back to Earth for analysis. With any luck, probes will arrive at these ocean worlds in the late 2020s. In the meantime, we can do a lot to probe the hidden depths of Europa and Enceladus. We can explore their surfaces with ground-based telescopes, looking for cracks through which water can make its way from the oceans and leave characteristic deposits. We can create and geophysicists such models to explain the presence of water in liquid form on celestial bodies so far from the Sun and the emergence of conditions to support life. At the same time, in our search for extraterrestrial life, we can be guided by examples of terrestrial flora and fauna which have adapted to extreme conditions. Earth's deep-sea hydrothermal vents at interfaces between tectonic plates, where magma pierces the sea floor, have long been recognized as hotbeds of life. In the murky depths around geysers, shields of hot and murky water roast. In hydrogeology, they are called black smokers. Bacteria live that feed on chemicals. Many other kinds of organisms in turn feed on these microbes. Europa or Enceladus can get enough energy from tidal shocks and gravity from their host planets. This energy causes the insides of the satellites to melt and feed hydrothermal vents. Scientists are not losing optimism. The chances of finding extraterrestrial life are not that slim. In 2000, a lost city was found in the Atlantic Ocean. It's an entire ecosystem thriving around hydrothermal springs without the slightest hint of tectonic activity. The life of the lost city is fueled by a specific chemical reaction of surf shading. When alkaline rocks from the Earth's mantle interact with the more acidic ocean waters, they generate heat, spewing out hydrogen, which in turn reacts with carbon compounds dissolved in seawater, creating food for microbes. Michael Russell, a former geologist and now an astrobiologist at NASA's Jet Propulsion Laboratory, City 1, California, USA, believes that it is in places like the Lost City that life on Earth could have originated. To see if it happens on water, a team of Cassini project scientists looked for hydrogen and its plume during its first approaches to Enceladus. The spacecraft did detect hydrogen there, but there was no way to tell if it was coming from Saturn's satellite itself or from inside the detector. The fact is that when particles from the plume penetrated the spacecraft's mass spectrometer, they interacted with its titanium walls, producing hydrogen. So experts had to switch the detector to a new mode that would register the molecules without allowing them to touch the walls. Finally, after processing the data from Cassini's last pass through the plume, they found the molecular hydrogen they were looking for, and lots of it. Enceladus' tiny ice shell or ocean contains too much hydrogen. Hence, it must be constantly being produced there, and probably by hydrothermal reactions. Europa is much larger than Enceladus. It is also likely to be undergoing shadowing processes, and due to its size, it boasts many more rock formations in contact with seawater. In 2016, Stephen Hand and his colleagues at the Jet Propulsion Laboratory published a paper on the properties of Europa's ocean, suggesting that its chemical balance is similar to Earth's. The calculations were based on the assumption that cracks beneath Europa's rocky seafloor could extend 25 kilometers deep. This would increase the surface area of rocky rock sections that could come into contact with water and release large amounts of hydrogen. As far as we know, living organisms need energy to support their life processes, which they obtain by releasing an electron. For this to happen, there must be a reaction between oxidizing oxides like oxygen, which add electrons, and reducing agents like hydrogen, which give up electrons. Europa, unlike Earth, doesn't have an oxygen atmosphere. But we know that Jupiter's radiation can produce oxidizer. On the surface of the satellite, Hand and colleagues assumed that these oxidizers circulate between the surface and the seawater. This assumption can be tested by strong winds completing the crust aboard a future landing module. It is quite possible that life on other planets obeys different rules and is based on a different set of building blocks. Then what exactly should we be looking for, if not organic molecules and amino acids? Asters. Biologists ponder this question, but it can probably only be answered by finding alien life forms. If we can find what look like deep-sea alkaline canals on distant moons, the chances of finding aliens will increase. We may also have to consider that equally life-friendly conditions lurk beneath the shells of other icy worlds, such as Jupiter's giant satellites Callisto and Animate or the dwarf planet Ceres. We now know that oceans hidden beneath frozen surfaces are common in the solar system. Perhaps such planets are the majority in the universe, while our blue planet with its peculiar open oceans is an exception, as imagined by the aliens. Cassini's unique instrument has discovered an amazing new atmospheric phenomenon on Saturn, a giant 6 corners, the newest over the planet's north pole. The probe also toured Saturn's neighborhood, exploring its satellites. Two-faced me. Strange. From the single corrosion-dotted geysers of Enceladus and the giant satellite Titan, with its methane, lakes, and rivers. Echoes from the depths not even Cassini has been able to peer beneath Saturn's multicolored clouds. But in 2015, the probe was able to get some interesting data from its interior perturbations in the ring system. The planets indicated planet-wide tsunamis studying around the equator and hinted at the existence of amazing structures beneath the clouds, perhaps giant whirlpools 1,000 kilometers deep, a buried sphere of light, or something even stranger. In 1980, the first Voyager mission discovered that Saturn's rings are arranged in a spiral pattern of prominent density waves and partly resemble the arms of a spiral galaxy. Most of these waves diverge outward. They are known to be formed by the gravitational force of Saturn's satellites, but a few waves point inward and are therefore suspected to be echoes of much more substantial waves deep inside the planet. Conventional wisdom holds that Saturn is a homogeneous liquid ball, a mixture of hydrogen and helium, and in theory this matter could form waves that run along the equator, undulating and gravitating peaks and troughs. One such planetary wave could well cause spiral waves to ring overhead. But don't draw specific conclusions based on limited data. Voyager Philip Nicholson and his colleagues at Cornell University began systematizing observations of Cassini orbiting Saturn through 2017. Nicholson and his colleagues found 3 independent waves with 3 special arms whose velocities differed little from each other, as well as 2 separate waves with 2 special arms. One explanation is the model of a large solid oscillating core whose oscillations produce waves of interference with fluid waves from above. Although this is consistent with generally accepted ideas about the formation of planets, some adjustments to the model are required to explain the existence of these specific waves. On the other hand, a planet may have a layer in which the hydrogen-helium mixture behaves strangely. At some points, the hydrogen and helium molecules could break up into individual atoms, and the mixture would become relatively transparent, creating a luminous sphere with different vibrations. In this case, the spiral arms could tell us what happens to matter at that pressure, a regime that our computers can't yet model. The strangest thing is that several of the spiral waves are traveling at almost the rotational speed of Saturn. This may account for the planet's persistent hills and valleys. But if Saturn is liquid, this would be tantamount to discovering water hills in the ocean. If the same laws of physics apply on Saturn as they do to us, there simply can't be liquid hills. Nicholson's colleague Miriam Schmidt makes another suggestion. Deep inside the planet exists a massive vortex, less dense than the surrounding liquid and therefore possessing less gravity. This configuration could create dips in Saturn's gravitational field, which could explain the presence of these spirals. The beginning of the rings. Saturn's spectacular rings are made up of 1 trillion icy particles, woven into 1,000 thin filaments over which tiny lunar reeds lord over. The different patterns in the rings are helping some researchers study the origin of planets and dusty disks around young stars, but the origin of the rings themselves is still unclear. A popular idea is that rings form when an asteroid or comet passing by a planet is atomized by its gravitational field. But that doesn't explain why Saturn's rings are made up mostly of water ice, while the rings around other gas giants are rocky. In 2016, Riki Hodu and his colleagues at Kobe University in Japan created a new model for ring formation. They looked at how a passing object rotates in space, whether its surroundings coincide with the direction it's traveling around the planet or whether it does a backflip. The scientists found that bodies whose rotation coincides with the direction they are traveling around the planet are more easily broken into pieces, and their fragments are more efficiently sucked into orbit. This happens because the planet's gravitational field more strongly attracts the near side of the small object and pulls it in the same direction it is traveling. If the planet's gravitational field works in the opposite direction to the object's rotation, however, it will not be able to capture as much matter as in the first case. The scientists also analyzed how Saturn and Uranus can affect objects with different types of rotation flying past them. They built a model that included more complex bodies, not only homogeneous spheres, but also much more realistic objects with a solid rocky core surrounded by an icy mantle. Some scenarios suggest that Saturn attracted only an outer layer of frozen water as it passed by the body, creating proto-rings that gradually evolved into the now observed icy commons. Modeling similar processes on Uranus tended to produce more rocky rings. Because Uranus is denser than Saturn, its gravitational field can capture much of the deeper, the rocky envelopes of the passing by this. Something about this scenario is puzzling. In the turmoil of the early solar system about 4 billion years ago, Saturn and other giant planets likely encountered passing bodies. As a result, most of these objects collided with planets or were ejected from the solar system. Over time, interplanetary dust should have contaminated Saturn's pure ice rings. But the pure water ice of Saturn's rings indicates that the rings are quite young. Cassini's observations indicate that the rings are low mass, meaning they are not that strong and are unlikely to have existed for 1 billion years. Could it be that Saturn just got lucky and encountered an icy world in the recent past, or that it broke off one of its moons after some orbital shenanigans? Or are the rings ancient, preserved since the formation of the planet, but somehow left clean by Titan's sea? The sky here has an ominous orange hue. But, after all, it always is. Suddenly there is the terrifying roar of an approaching whirlwind, and clouds begin to gather, threatening to bring down a flood greater than the flood. Even a seasoned alien sailor would wonder if it's worth going for the throat. Someday such a scene may actually materialize on Titan, Saturn's giant satellite. It's the only planetary satellite in the solar system with a dense atmosphere, and not counting Earth. The only known world with seas on its surface and an ocean on Earth. Rivers are filled with water and mountains are made of rock. On Titan, rivers and liquid methane flow, and the mountains and plains are made up of hard, iron-like water ice. Long before the Cassini mission arrived, scientists estimated that methane and other liquid hydrocarbons could accumulate in the sea, perhaps even forming a global ocean. But we don't have complete certainty, as Titan's surface hides a layer of orange smoke. To dispel the fog of uncertainty, Cassini carried the Huygens probe landing module, which was able to swim. In 2005, when Huygens dove into the smoke, it sent us an image of a landscape very similar to Earth's. The probe had landed on a rocky shoal. The surrounding terrain appeared to be saturated with methane and did not resemble the long-awaited ocean at all. The lakes on Titan were first discovered by Cassini radar in 2006. This instrument was able to look through a small section of Titan's surface each time Cassini passed by. Over several years of observations, it was able to determine that some of the puddles were large enough to be considered a sea. The largest sea, named the sea after a monster from Scandinavian legend, is about 1,000 kilometers long. On May 23, 2013, the spacecraft flew low over Titan's second largest sea, the Legian Sea. The radar was pointed straight down, allowing the instrument to track the height of land and sea. It sent out pulses of radio waves and then measured how long it took for them to be reflected. When the scientists looked at the data, they saw the signal reflected off the sea surface, as expected, and then a second faint signal was detected, which was reflected off the sea floor just a second later. Thus, for the first time in the history of mankind, measured the depth of the sea beyond the Earth. The time interval between the first and second reflection showed that the depth of the Legian was about 160 meters. The surprise was that the sea floor at all can be seen in Titan's atmosphere, very many complex hydrocarbon molecules that absorb radar signals. And scientists assumed that these molecules would be a serious hindrance to ocean scanning. So the fact that the Sea of Humans could be scanned through suggests that this sea is free of complex hydrocarbons. Most likely only some mixture of ethane and methane is present, as methane should evaporate from the seas fairly quickly. The planet many expected to see. The prevalence of it. However, new laboratory data has shown that ethane absorbs radio waves too strongly, and Titan's seafloor would be inaccessible to radar. So it's clear that the northern seas must be lit by crystal clear methane, perhaps through seasonal showers like those that have fed vast tracts of Earth's land near the equator. In 2011, Cassini also saw a strange feature in the Legian Sea that kept disappearing and reappearing. Some researchers have speculated that this magical island could be a swamp of nitrogen bubbles, sizzling out of methane. Koryakin's throat being the largest alien sea, the sea. Koryakin's throat has a special fascination, and most of the plans to explore the seas on Titan involve it. The Sea of Koryakina is almost split in two. We are land itself and a chain of islands. Ralph Lawrence of the University of Arizona in Tucson has named this area the Gulf of Koryakin. He suggested that something unusual might be happening on this section. Saturn's gravitational field should cause tides in Titan seas as Titan orbits. A decent wave in the throat of Koryakin can rise and fall by 1 meter. As it rises in the north, it must fall in the south. Ready from one shore to the other, seeped through the throat of Krasin. According to Lawrence's calculations, tidal current should reach speeds of 2 kilometers per hour, although this current may seem slow. Gravity on Titan is much weaker than on Earth, and the liquid in the seas there is much lighter. So even this mild decent current can be fast enough to drive Koryakin into a frenzy. Lawrence compares Koryakin's throat to the west coast of Scotland, where 2 islands frame a strait across the Europa. Here, tidal currents turn the sea surface into one of the world's largest whirlpool. Could Koryakin's throat be a haven for a similar whirlpool? If so, it would be a curious coincidence. Legend has it that the monster after which the sea on Titan is named created the whirlpool and which carried sailors away to their doom. Life in the ice. Could the seas of Titan be inhabited not only by mythical, but also by real living creatures? If so, they are quite unlike those on Earth. Every living cell on Earth is a sac filled mostly with water and surrounded by a shell of lipids. None of these components would feel good enough on Titan. It's too cold there for liquid water, where the average temperature at the surface is minus 179 degrees Celsius. But in 2017, Maureen Palmer and her colleagues at Goddard Space Flight Center in Greenwich, Maryland, USA, reported finding traces of vinyl cyanide in Titan's nitrogen atmosphere. According to a 2015 study, vinyl cyanide is particularly good at forming stable, flexible structures needed to create cell membrane-like structures. According to Palmer, Titan has plenty of vinyl cyanide. Plenty of the building material means there's a fairly high probability that membranes could grow large enough to support complex structures like cellular innards. Of course, membranes alone wouldn't be enough, but high up in Titan's atmosphere. The Cassini probe has discovered a molecule called carbon chain anion that could help create life. Ravi Desai and his colleagues at University College London believe that near Titan's surface, these antennae could create the foundations for larger and more complex organic molecules. Titan's flight of coves and beaches 1 billion kilometers from Earth, the site of Saturn's rings rising above the waves, and a swirl of exotic chemistry that could shed light on the origin of life. It's hard to find a more enticing travel target than titanium. Some planets are designing a spaceship or even a submarine to explore its distant seas. In 2010, Hunter will leave at the Southwest Research Institute in San Antonio, Texas, USA. He has developed the concept of an underwater mission. His floating base carries an underwater vehicle that will submerge by filling a hollow chamber. Liquid methane. Later, the submarine can jettison the chamber and rise to the surface again. Organic sediments may exist on the seafloor, containing deposits of chemical compounds, especially if liquid water seeps to the bottom from the bowels of titanium, mimicking the oxygenated, organic-rich environment of early Earth. The submarine can also measure the isotopic mix of different chemicals. Perhaps this will help geologists learn how titanium formed and evolved. Destroyer of worlds. Dark blue Neptune is the most distant giant planet in the solar system. The strongest winds blow here and rage constantly. A storm that's even got its own name, the Great Dark Spot. The planet seems to have had a turbulent past. In 2010, researchers speculated that Neptune had once swallowed Super-Earth, a large rocky planet, and in addition stole its satellite. Neptune's cruel act may explain the mysterious warmth emanating from the icy planet and the strange orbit of its satellite Triton. As a matter of fact, the very existence of Neptune has been a question mark until recently. The dust cloud that once spawned the planet is likely to have dissipated as it moved away from the Sun. It remains unclear how Uranus and Neptune, the most distant planets, managed to gain so much weight with such liquid building material. But what if they were formed not so far from the Sun? In 2005, a group of scientists suggested that the giant planets changed their position in the solar system in the early stages of its development. In this scenario, Uranus and Neptune formed much closer to the Sun and migrated to the outskirts of the solar system, perhaps by switching places in the process. This could have been caused by a stream of comets, the so-called last heavy meteor bombardment that scoured the interior of the solar system. It also means that there was enough matter in the area around the birth of Neptune and Uranus to allow a planet with twice the mass of Earth to form. According to calculations by Stephen from Arizona State University in Tempe, USA, Triton, an unusual satellite of Neptune, could have once been paired with this hypothetical super-Earth. Triton is a giant satellite whose orbital direction is opposite to the direction of Neptune's rotation. This suggests that it did not form with Neptune, but was captured by its gravitational field. At the beginning of this captivation process, the motion of Triton must have slowed down considerably. Perhaps Triton had a partner who carried away much of the couple's kinetic energy after the encounter with Neptune. One theory that emerged in 2006 says that Triton originally paired up with another object of the same size, and that object was pushed out into space by a gravitational field after the pair ventured closer to Neptune. According to the show, if Triton's partner was a heavy super-Earth, taking away much of the pair's kinetic energy, Triton may have slowed down quite a bit. Neptune may have absorbed this super-Earth. There was heat left over from the huge impact, and that may explain why the planet radiates much more heat than its cousin, Uranus. Neptune and Uranus made of ice. These planets are called ice giants, but they don't contain ice. In everyday parlance, planetary scientists use the word to refer to chemical compounds that freeze at temperatures typical of small objects in the outer regions of the solar system. For example, for comets, while Jupiter and Saturn are mostly composed of hydrogen and helium. The insides of Neptune and Uranus are thought to be composed mostly of water, ammonia, methane, and other ices. But these ices are not at all solid at the high temperatures and pressures that prevail on the planets. These compounds are liquid. In the solar wind's roundabout way, the tilt of the axis of rotation of almost all planets in the solar system with respect to their orbital plane is small. The exception is uranium. It rotates lying on its side, tilted to the plane of its orbital motion around the Sun by almost 98 degrees. This planet has the strangest magnetic field in the solar system. The axis of the magnetic field is tilted at an angle of 59 degrees to the axis of rotation and displaced relative to the center. And the magnetic field is shifted from the center of the planet to the South Pole about 1/3 of the radius of the planet. And if the magnetic field of the Earth resembles the magnetic field of a rod magnet, then on Uranus the nearby surface areas may have fields of opposite polarity. As on many other planets, Uranus' magnetic field forms a bubble around the planet called the magnetosphere. According to a model developed for Uranus' magnetic field in 2017 for solar wind particles, and its magnetosphere opens and closes. Magnetospheres work as a barrier to the solar wind's path. When particles move in the same direction as the magnetic lines of force, they slide off them like water off a duck's back. But when jets of water flood the duck's tailside feathers, the duck helps. When the solar wind blows the uranium at right angles to the field force lines, they align with the direction of the solar wind and let some of its particles inside. This process is called magnetic accretion. It sometimes occurs near the Earth's poles, and then the intensity of the polar lights increases due to the increased influx of solar wind particles. Carol is on the axis with his students dreaming. From the Georgia Institute of Technology in Atlanta, the U.S. modeled this process on Uranus and found that this pole switching must occur on Uranus every 24 hours once about 17 Earth hours, turning the magnetospheric shielding on and off. But earlier, apparently, there are also polar auroras. Strange water. Some of the strange features of the magnetic field can be explained by the equally strange properties of water. As the calculations of the year and experiments in 2005 showed, at very high pressures and temperatures, water can behave both as a solid and as a liquid. Oxygen and hydrogen atoms in water molecules will ionize, and the oxygen ions will form a lattice-like crystalline structure, while the hydrogen ions will be able to flow through it like a liquid. This superionic ice, formed at temperatures above 2000 degrees Celsius, should glow yellow. Conditions in the depths of Uranus and Neptune may be very favorable for the formation of superionic ice. In 2010, new computer models created by a team of authors led by Ronald Rasmussen at Boston University in Germany showed that both planets could have large stores of such ice. The models assumed the most extreme conditions that could exist inside both planets' temperatures of up to 6,000 degrees Celsius and pressures 7 million times higher than the atmospheric pressure on Earth. The results show that a layer of superionic ice should extend from the core amount to the planet's surface about half the distance. This agrees well with the results of a study conducted in 2006. Sabine Stanley, now at the University of Toronto, and Jeremy Blogskins from Harvard University. They attempted to explain why the magnetic field on Uranus and Neptune is so inhomogeneous. Stanley and Blogskins hypothesized that the insides of both planets contain a narrow layer of electrically conducting matter that are constantly stirring and generating the magnetic field. This conductive layer must consist of ordinary ionic water in which the molecules have broken up into oxygen and hydrogen ions. The study also showed that the zone could not extend deeper than half the distance to the center of the planets. If the zone were wider, it would create a more ordered field-like field. Rod magnet. The depth of the convection zone calculated by Stanley and the block diagrams may not seem quite right, as superionic water begins to predominate at these depths. Superionic water also conducts electricity through the flow of hydrogen ions. However, there is some factor that prevents superionic water from participating in the process of forming a homogeneous magnetic field. Perhaps superionic water mainly transmits infrared radiation, i.e. heat. Electrons in superionic water can absorb infrared radiation. But modeling shows that they tend to stay near the oxygen atoms, allowing heat to spread. This makes it easy for heat from the planet's core to penetrate through superionic water, rather than accumulating near the core and convection not occurring. Mysterious storms. In 2015. But earlier in the day, huge clouds appeared. So bright that they could be seen even by amateur astronomers from Earth and from the University of California, Berkeley, USA observed the planet 5 and 6 August 2014 and was surprised to find unusual bright geometric elements resembling high clouds. Normally, the weather on Uranus changes markedly every 42 Earth years. During the spring and fall equinoxes, when the sun shines over the equator. But the last equinox was 7 years ago, so explaining such a peak in activity was difficult. Using the Hubble Space Telescope, Peter and her colleagues observed storms at various altitudes that could be linked to deep atmospheric vortices. Chapter S for Wild Frontier. Y. Beyond Neptune spreads a swarm of icy worlds. This region of the solar system was once poorly explored, but we now know that it is a living and rich realm. Thanks to the automated space station, New Horizons has been sent to Pluto. But there may be larger planets on the far reaches of the solar system that are so far hidden from our eyes. Pluto unmasked for 85 years since its discovery in 30. Pluto has remained just a faint dot in the sky, hardly observed by astronomers. Scientists were lost in speculation about what to expect from this planet until in July 2015, the New Horizons automated interplanetary station sent the first images of the planet to Earth. The close-up images stunned scientists. This dwarf planet was unlike any other world in the solar system, with mountains and icy volcanoes floating beneath a very heterogeneous atmosphere, and terrain similar to the highlands of Mars visible along stretches of highway. Most striking were the smooth surface areas. Until the probe sent back the first images of Pluto, researchers expected to see a heavily cratered world bombarded with craters we have been seeing since formation at the dawn of the solar system. But Pluto's flat surfaces show that the planet was likely geologically active. The strangest turned out to be the plane of the satellite area of 1,000 kilometers wide, divided into polyhedrons with a diameter of several tens of kilometers. These shapes were created by convection. They show how nitrogen ice swirls in the back of the satellite plane, similar to what happens on the surface of the sun, or oil sizzling in a frying pan. While this slow-motion whirlpool is certainly bizarre and unexpected, it is not as difficult to explain as it first seemed. Nitrogen ice is friable, a substance with excellent heat-insulating properties. Even a weak heat source below can raise its temperature and kickstart convection. The amount of heat left over from the initial violent stage of Pluto's formation, plus the heat from the decay of impurities of radioactive elements in its core, is capable of producing 4 million tons per square meter. This surface heat flux density is enough to set off a convection process on the satellite's plane. This lively, changing landscape is enhanced by strange markings. They are probably caused by the sublimation of nitrogen from the ice. The clumps found at the junctions of effective cells may be floating hills of water ice, roaming expanses of denser nitrogen, but ocean on the northwestern flank of the satellite plane. Ice piles gather into a jumble of peaks. This is a ridge, and these mountains are kilometers high. Nitrogen, snow, and ice volcanoes. Pluto's cold atmosphere is dominated by nitrogen. The atmosphere is very permissive. The pressure at the planet's surface level is equal to Earth's pressure. At 80 kilometers above sea level, misty layers of fine aerosol particles extend upwards of 200 kilometers. The weather here is remarkably similar to Earth's. Only the cycle in nature is not based on water, as on Earth, but on nitrogen, just as water evaporates from the Earth's oceans. Nitrogen is summarized from the ice plains of the satellite. It then falls as snow on the eastern plateau and eventually slides down to the glacier plains. Signs of nitrogen fog and even clouds can be seen in some places. Mount Ride is unlike most of the jagged mountains that grace Pluto's surface. The hilly mass with a huge central pit looks suspiciously like a volcano. However, the 4-kilometer-tall Mount Wright and the neighboring even taller Mount Icarus are unusual volcanoes. They were not toppling molten rock, but some kind of colder liquid. It could have been water mixed with another substance, lowering their boiling point. Mount Wright is not a relic of the old days of the dwarf planet. There are hardly any craters on its sides. It could not have been exposed for too long to the rain of space debris found elsewhere on Pluto's surface. It is much less than 1 million years old. It's probably a few 1 million years old. So has this volcano gone extinct? Or is it just sleeping? The case of the missing craters on Pluto and its large companion Charon are relatively few large craters. This may tell us something about how the planets formed. According to the traditional picture, small bodies called planet Earth, lines that appeared in the first stage of the formation of the solar system, gradually increased in size as small rocks clumped together. This process led to the formation of a large number of objects with diameters of a few kilometers and some objects with diameters of tens and hundreds of kilometers. Planet Earth of various sizes must have bombarded Pluto and Charon from time to time, forming craters. Thus, the relative scarcity of small craters on Pluto seems to indicate an unconventional pattern. It supports an alternative model called pebble aggression, in which large planetesimals form almost instantaneously, while small pebbles immersed in gas suddenly collapse. This could be a vital step in building not only small icy worlds like Pluto, but also the cores of gas giants and warm rocky planets like Earth. Charon land. Charon's diameter is half that of Pluto, meaning Charon is the largest planetary companion in the solar system relative to its host. Some researchers consider Charon and Pluto to be dwarfs, twin planets. Before the New Horizons interplanetary station mission, we suspected that Charon would be a dull, monotonous world, but it turned out to have a colorful and varied landscape. There is a belt of cracks north of the equator, and coronal stretches nearly 2,000 kilometers. This system of fissures and coronal is 4 times longer than the Grand Canyon and in some places twice as deep as it. Apparently, Charon has had difficult periods in the past when its crust was torn apart. To the south is a smooth plain, a volcano. It has fewer large craters than the north, which means that this surface was formed relatively recently. Perhaps the inner ocean broke the crust when it froze, causing lava to flow to the surface. Let's go. The Oort cloud. Comets are clusters of dust and ice that orbit the Sun in highly elongated orbits. They're caught in a headwind of charged particles building up from the Sun. They put on their spectacular tails. Some come from the scattered disk of Trans-Neptune, the new objects of heat, the attraction of Neptune and Uranus. Push these objects out of their orbit. The orbital periods of such comets are usually no more than 200 years. Other comets like Comet Hill, which swept past Earth in 1997, have much longer waffle orbits and travel much farther away from the Sun than any object in the scattered disk. The inference is that they originate from more distant regions, and the solar system is surrounded by a thin halo of icy outcasts ejected from the region immediately adjacent to the Sun 1 milliard years ago. Under the influence of the gravitational fields of the giant planets, this celestial Siberia, known as the Oort cloud, was named after Dutch astronomer Jan Oort, who suggested its existence 1950. Still a purely hypothetical region, no one has observed it yet, but judging by the orbits of long-periodic comets, it must have a huge size, perhaps up to 100,000 astronomical units, 15 trillion kilometers, or 1.6 light years. At such enormous distances from the Sun, the main influence comets would experience would not be from the gravitational pull of sun-seeking planets, but rather from the nearest stars in the Milky Way. The Oort cloud should be where our solar system meets the void of interstellar space. In 2003, Mike Brown and colleagues at the California Institute of Technology City across the United States observed the dwarf planet. Today, it orbits the Sun in a highly elongated orbit, moving away from it in aphelia at a distance about 1,000 times the distance between Earth and the Sun. Scientists say the Oort cloud lies inside the so-called Hill sphere near solar space, where the Sun's gravity holds its planets and other bodies. The objects inside the Oort cloud are made up of matter left over from when the planets formed. If we know how many objects there are in the Oort cloud and how much they vary in size, we can understand how the planets formed. But it's not that simple. So far, we've gotten clues about this primordial building material by observing wandering comets and the largest objects in the Kuiper belt. They should have a similar composition. The number and trajectories of the long periodic comets observed so far suggest that the Oort cloud contains 1 billion objects 1 kilometer in diameter or larger, with a total mass several times that of the Earth. This enormous amount of matter does not fit into our current ideas about the formation of the solar system, and thus our models may need fundamental revision. The life of stars. Our galaxy is home to hundreds of billions of stars. No two are completely alike. Some are bright, others dim. Some are blue, others white, yellow, orange, or red. Some are huge, others are tiny. Some have just been born, while others are aging and about to die. Unraveling the nature of starlight has been one of the great triumphs of the last century. But there are many strange stars. Processes we still don't understand. Stellar spectra. To make sense of the diversity of stars, astronomers use Hertz charts. Spouse-Razel is abbreviated GR. It was developed by Danish astronomer Einar Hertz in 1911 and independently by American astronomer Henry Norris Russell in 1913. Just as Mendeleev's periodic table of elements allows chemists to sort chemical elements by their fundamental properties, the GRR chart allows astronomers to distinguish stars by their basic features. Two basic characteristics of a star are plotted on the chart: luminosity and color. Luminosity is the technical term for the brightness of the amount of radiation in the various bands of the spectrum studied by a star. Stars vary greatly in luminosity. If, for example, the brightest star in the galaxy were placed in place of the Sun, the Earth's oceans would boil and its rocks would melt. And vice versa. If our Sun were to instantly switch places, the faintest star would be darker during the day than on a lunar night, and our oceans would freeze. In the diagram of years, the stars of greatest luminosity are located at the top of the chart, and the faintest stars at the bottom of it. Approximately in the middle of the entire range of stellar luminosities is the Sunday, occupying an interdiurnal position on the diagram. The untrained eye can hardly distinguish stars of other colors in the sky except white and yellow. In fact, the colors of stars range from blue and white to yellow, orange and red. From the color of a star, we can judge the temperature of its visible surface. Orange and red stars have temperatures between 2000 degrees Celsius and 5000 degrees Celsius. Yellow stars like the Sun have temperatures between 5000 and 700 degrees Celsius. And white-blue stars are even hotter. Their surface temperatures range from 7.5 to 50,000 degrees Celsius. In the RR diagram, the hot blue stars are found on the left side, warm yellow stars in the middle, and cold red stars on the right side. Our yellow Sun occupies an intermediate position on the diagram, not only in luminosity, but also in color. The temperature of a star determines its color and the presence of certain lines in the spectrum that come from different atoms and molecules. Astronomers use these lines to classify the spectral type of the star. For example, the spectra of white stars have strong spectral lines of hydrogen, while the spectra of yellow stars are dominated by strong lines of calcium. Stars are classified according to the following major SOHO spectral classes. Hottest stars with the bluest hue: Di. Many bright stars, including those from Rigi Peak, Hay, white stars that contribute greatly to the luminosity of our galaxy. The spectral class includes the main sequence stars Sirius, Vega, and Altair, as well as the white-top giant with stars with a yellowish-white hue. The two brightest stars of this spectral class visible on Earth: Movie and Russian. Polaris is also a star of spectral class G. Stars in this spectral class are characterized by a yellowish warm hue. They include the Sun's Alpha Centauri and Capella. Giant K star. This special class includes giant stars such as Arthur and Deborah, as well as fainter main sequence stars called orange dwarfs. For example, Excellent is given by M. Some stars in this spectral class, such as Gizzy and Antares, are cool and red supergiants with luminosities 10 to 1,000 times that of the Sun. However, the main representatives of this class are red dwarfs. Faint stars on the main sequence. Main sequence. Having first plotted the characteristics of various stars on their diagram, Hertz, Froome, and Russell found, to their surprise, that the position of the stars on this diagram obeyed certain patterns. 95% of the stars are concentrated in a band that extends diagonally from the upper left edge. Diagrams corresponding to the bright blue stars, to the lower right edge, where the faint red stars are located. This band is called the main sequence. The source of energy of a main sequence star is the reactions of fusion of hydrogen atomic nuclei into helium nuclei occurring in the center of the star. The greater the mass of a main sequence star, the hotter it is in its center and the faster the hydrogen burns out. This is why massive stars are the hottest, blue, and brightest. The mass of yellow main sequence stars is about equal to the mass of the Sun. White blue stars are more massive. Their mass can be 100 or more times that of the Sun. The orange-red main sequence stars are less massive. Some of them have masses as low as 0.07 solar masses. Blue main sequence stars are few in number. Their number does not exceed 1/10%. The small number of these massive stars is due to two reasons. First, they form relatively rarely, and second, they do not live long because they burn their hydrogen fuel at a furious rate. The centers of the most massive stars run out of hydrogen a few 1 million years after their birth. Many such stars are visible to the naked eye. They are characterized by enormous luminosity and can be seen from great distances. In fact, almost all of the stars we see in the sky, without the aid of optical aids, shine brighter than the Sun. In contrast, there are many more less massive stars, but they are difficult to see. The most common main sequence stars are red dwarfs, which are located in the lower right corner of the RP diagram. Red dwarfs burn their fuel so slowly that some of them remain on the main sequence for 1,000 billion years. This is one of the reasons they are so numerous. There are more red dwarfs than all other stars combined. They make up 75% of the total number of stars in our galaxy. But because of their low luminosity, no red dwarf is visible to the naked eye. If the mass of the star is even less than that of a red dwarf, such a star will never heat up to the temperature necessary to sustain hydrogen fusion, and so it will never reach the main sequence. Such stars in the intermediate stage between a star and a planet are called brown dwarfs. When all the hydrogen in the center of a main sequence star is used up, combustion of the layer hydrogen around the core begins, followed by helium combustion in the core. The core is compressed while the rest of the star expands and cools. The star leaves the main sequence and becomes a giant or top giant. Large and bright most giants and supergiants are stars with small temperatures. They are located on the RR diagram at the top right. The color of some of them is blue or white. For example, Giant Miguel is blue on top and giant white on top. Generally, the evolution of the hottest and bluest main sequence stars leads to supergiants, while less massive main sequence stars evolve into giants. Huge giants and supergiants emit a lot of light. When our Sun becomes a giant, it will shine 100 times brighter than it does now. But the giant or supergiant stage in a star's life does not last long, and that is why we see such stars compared to others. Comparatively few. The supergiants begin to rapidly use up the available fuels, first helium and then carbon, neon oxygen, silicon, and sulfur. The last two of these elements are eventually converted to iron. During each subsequent stage, less and less energy is released, and there is simply not enough energy for the iron synthesis reaction into heavier elements. Note: the nuclei of elements heavier than iron can probably be synthesized in small quantities by neutron capture in supernovae and supernova explosions. But that's a different story. Having exhausted internal sources of heat, the core collapses with the formation of a neutron star or black hole. There is a powerful explosion, a huge amount of energy is released. The outer layers of the star are destroyed and ejected into space at a tremendous speed. The star turns into supernovae. Few stars go through this ordeal because most are born with masses less than 8 solar masses. The fate of a less massive star takes a different course. It becomes a red giant and ejects its outer atmosphere into the surrounding space, exposing a hot core. Too small for the star to collapse. Into a neutron star. Radiation from this core causes the ejected shell to glow. Astronomers call such glowing shells planetary nebulae, but not because they have anything to do with planets, because through a small telescope they can look like planets. Stellar magnitude: the distance to stars and their luminosities. Around 120 BC, Cheetah divided all stars into 6 groups according to their luminosity from first magnitude. The brightest stars when observed from Earth to the 6th magnitude, the faintest. Cheetah's classification experienced refinement in the mid-19th century. To indicate the brilliance of stars, developed a logarithm and a clear scale of brightness so that one stellar magnitude corresponds to a decrease in brightness by a factor of 2.5. A first magnitude star is brighter than a second magnitude star by a factor of 2.5. Most of the bright stars we see in the first magnitude sky are the faintest stars we can see with the naked eye. 6th visible stellar magnitude depends on how far away a star is from us. Distances to stars are often measured in light years. 1 light year, the distance that light travels in a year, is equal to 1 million kilometers. This distance is a huge 1 light year, the same number of times the distance between the Earth and the Sun. How many times? A mile is more than an inch? Over 60,000 times. Yet, even the closest star to the Sun is 4.24 light years away, and most stars we see in the night sky are distances of a few hundred light years. Knowing the distance to a star, astronomers can calculate its luminosity from its apparent stellar magnitude. Luminosity can be expressed as powerful jungle radiation per second, or in units of solar luminosity, or as absolute stellar magnitude. Absolute stellar magnitude is the apparent stellar magnitude that a star would have if it were 32.6 light years away. 10 peaches under the ground. The stars are fading. Only a few tens of 1,000 years will pass and the planetary nebula dropped by the red giant will dissipate, leaving behind a small but extremely hot star. The white dwarf is a typical white dwarf. Not much larger than Earth, but its mass reaches 6% of the solar mass. A teaspoon of the matter that makes up a white dwarf weighs more than tons. In the process of evolution, quite a few stars turn into white dwarfs, so they are widespread in the galaxy and make up 5% of the total number of stars. But because of their extremely low luminosity, they are not visible in the sky to the naked eye. A typical white dwarf has a dull and unimpressive life. It has no fuel for thermonuclear reactions. It glows simply due to its residual heat, radiates its energy into space. Such a star gradually dims and cools down to completely extinguish in a few 1 billion years. Despite the name white dwarf, the star can be any color. Newly formed white dwarfs have high temperatures and a blue color. Older white dwarfs that have severely diminished energy reserves may be orange or red in color. In the RR diagram, the white dwarfs form a sequence that runs parallel to the main sequence. It will take quite some time before a white dwarf disappears completely, turning into a black dwarf. But black dwarfs don't exist yet. The universe is not old enough for that. Under certain conditions, white dwarfs can put on extravaganzas. Suppose a white dwarf has a companion star orbiting around it. If this companion drops on the white dwarf, its matter, it can explode. In this case, astronomers will say that a new star has appeared. The star could become 100,000 times more luminous. But no matter how powerful the explosion, both stars will survive. If too much matter comes from the companion star, the mass of the white dwarf may exceed the limit of 1.40 Q400 of the Sun's mass. A nuclear explosion occurs in which carbon and oxygen are burned. the white dwarf turns into G1-type supernovae, and during the supernova explosion temperatures and pressures reach extremes, resulting in the formation of large amounts of iron. As the star collapses in the explosion, all of this iron is dispersed into outer space along with the remnants of the planetary nebula. The stellar matter left over from the supernova explosion eventually collects in star-forming regions where it will someday give rise to new stars and planets. Some of these planets may one day harbor life. That's how the Sun and Earth came into existence 4.6 billion years ago. We are part of the supernovae legacy. Except for hydrogen, virtually all the atoms in our bodies were created on stars. Without any metallic cargo. Hydrogen and helium make up the bulk of stellar matter, but most stars also have significant admixtures of heavier elements, which astronomers collectively refer to as metals. This is not entirely accurate, though. These heavier elements are the legacy of earlier stellar generations. The object XTG 102,215 plus 172,927, which is about 4,000 light-years away, stands out oddly against this background. Its composition is an almost pristine mixture of hydrogen and helium with a paltry addition of other matter of just 0.0007%. It looks as if this object was formed from the original matter from the Big Bang and has not undergone any changes since. The impurity-free hydrogen, helium, and gas it contains is devoid of carbon and oxygen, which normally help clouds cool and condense into stars. The origin of the star remains in question. Scientists do not understand how this anomalous object was able to form. It may have been a fragment that broke off early in the life of the universe from a supergiant star. Stellar makeup. After supernova explosions, the nuclei of exploded massive stars, neutron stars, remain. The source of energy of F1A-type supernovae is thermonuclear reactions of other supernovae, fueled by the energy of gravitational collapse. When massive stars run out of nuclear fuel and the radiation pressure drops, they lose their own gravity and shrink to a critical density until a new force emerges that can stop the star from shrinking further. The strong nuclear interaction that holds protons and neutrons together in the nuclei of atoms begins to play the role of a repulsive force. The density of the compressed matter, gravitational and strong interactions come to a standstill when the nucleus is compressed to about the size of 10-15 kilometers. Under these conditions, most protons and electrons combine to form neutrons. These particles are packed so densely that a teaspoon of neutron matter weighs several 1 billion tons. Neutron matter must be ultrafluid, able to flow without friction and permeated by magnetic vortices. This matter is very strange in itself, but nature has gone even further. At least in the hypothesis of some physicists, in especially massive neutron stars, they say, excess pressure can cause neutrons to decay, releasing the quarks that make them up, or particles can form Einstein's boson. Any condensate is such a quantum state in which the individual properties of neutrons are blurred and they behave as one large collective particle. Theories of the existence of exotic matter got a real kick in the butt from a neutron star called EX 0078-676. Its mass is estimated to be equal to 2 solar masses. At the same time, most models of wax stars and neutron stars containing Bose-Einstein and condensate predict that they will collapse into a black hole before reaching such a high mass. But the case is not yet completely closed. In 2014, Charles Horowitz and his colleagues at Indiana University, Mystery Town, USA modeled the behavior of a tiny neutron star smaller than one atom, containing tens of 1,000 neutrons and protons, super dense packing of protons and neutrons. It turns out to be a battlefield between the strong nuclear interaction and the electrostatic force, and turns the star into a sort of vasodilator-like structure. In their characteristic size, these military structures are only slightly larger than the atomic nucleus of the star Quagmire. The crust of neutron stars is compressed, not so much. It rather resembles the solid matter we are familiar with nuclei and electrons. This matter is also super strong, but it can be torn apart by the magnetic field of some neutron star magnets. The magnetic fields of these stars are so strong that if a magnet were to pass halfway between the Earth and the Moon, all magnetic maps on Earth would be erased. The rotating magnetic field binds the crust of the magnet from the inside, and a fireball of particles bursts out. And then astronomers see a bright flash of high-energy photons that makes the star shudder. In 2006, astronomers measured the thickness of a neutron star's crust, taking advantage of a particularly strong analysis. Star shaking. It was detected in December 2004 on star 6820 by the SpaceX X-orbiting X-ray Observatory. Laura is a temporal radiation researcher, named in honor of astronomer Bruno Rossi. A scientific team led by Todd Strohmeyer of NASA's Goddard Space Flight Center, who decided to measure the thickness of the crust of this neutron star, found that shaking caused the neutron star to vibrate at different frequencies. The corresponding oscillations in the X-ray spectrum were recorded, based on the assumption of vertical propagation of some waves through the crust. It was possible to calculate its thickness, which turned out to be equal to about 1.5 kilometers. With the help of magnets, it is possible to explain the origin of welding of bright supernovae and their rotating. Magnetic fields can pump additional energy into the cloud of divergent fragments, ejected by the supernova explosion that resulted in the formation of the magnet. Cold-blooded, as if the cosmos isn't lonely enough on its own. There are still pity-inducing brown dwarfs compared to their more successful stellar siblings. These astronomical objects could be called cosmic objects. Losers. Although they have a lot in common with planets, they don't seem to fit into this family either. Intermediate cosmic links. Uncomfortable status. It puts brown dwarfs in the position of poor relatives who are often neglected, unlike promising planets or fiery supernovae. And yet it is precisely this property of originality that makes brown dwarfs interesting to study, attracting increasing attention. The existence of brown dwarfs in 1962 predicted Shiv Kumar of NASA Goddard Institute for Space Studies, New York, USA. Kumar set out to find out what the minimum mass of a star might be. Calculations showed that there is a critical mass limit below which thermonuclear burning does not occur. Hydrogen. Kumar called these hypothetical objects black dwarfs, but the name was not quite successful. As the American astronomer Jill Tarter noted in the 70s of the last century, this name is quite suitable in dark cooling stars whose evolution ends. Various names have been suggested, among them Planet Dead Star and Nido Star. But Tarter settled on brown dwarfs. She realized, of course, that in reality they were hardly brown, but she chose this light for the name because of the faint radiation. These stars are very difficult to observe in reality. If you speed past a star like this in a spaceship, you might not see it. There's too little energy it's emitting. If you look closely, you can see a faint glow from the area where there is still some heat. But the color of that area is more of a dark orange. For the next 20 years, not a single object of this species could be detected. But finally, in 1995, astronomers discovered a brown dwarf in the double system of Lens 229. The dwarf itself was named Lens 229 by. This brown dwarf is about 19 light-years away from us. Its mass is 20-50 times that of Jupiter, and its surface temperature is a relatively cool 680 degrees Celsius. Since then, 1,000 brown dwarfs with mysterious characteristics have been found, generating. The debate over whether they are properly categorized as stars or planets has not subsided. Ever since humans first looked up at the sky, they have always divided celestial objects into stars and planets. Brown dwarfs defied this simple systematization. They are born from the collapse of a gas cloud, just like stars, so they share some common features with their stellar relatives. Like stars, they have magnetic spots, and some of them even emit in the radio band, like a pulsar. Many of them are large enough that they have briefly turned on fusion reactions in brown tarper. By recycling the remaining deuterium in the larger ones and lithium too. In addition, heat is released during gravitational collapse when brown dwarfs form. Both of these processes cause brown dwarfs to radiate invisible light, albeit slightly. Gradually cool down, for example, the brown dwarf Weiss J is 085,510.83-071442.5, which is 7 light-years away from the Sun, have already cooled to below 0 Celsius. Such cold objects, which do not support fusion reactions, seem very unlike ordinary stars. But should they be considered planets? Brown dwarfs are much more massive than planets. They are usually tens of times the mass of Jupiter. There are brown dwarfs with masses from 13 to 70 Jupiter masses. Among exoplanets, only 3–4% can compete with them. On the other hand, most brown dwarfs are not much larger than the diameter of Jupiter. They have atmospheres that are similar in composition to those of gas giants of a toxic mixture of carbon monoxide, hydrogen sulfide, and water or methane and ammonia. And they have different weather patterns. Scientists have long suspected that clouds thicken over brown dwarfs because their internal heat causes the gases entering their atmospheres to rise and then condense, as they do in the atmospheres of planets in the far reaches of our solar system. Recently, evidence has been found that the weather on brown dwarfs changes over time. If you follow a brown dwarf through a telescope for several months, you can see how its infrared emission changes due to storms and hurricanes. By studying the chemical composition of stars, astronomers have learned that the atmospheres of hot brown dwarfs contain silicates and iron in a gaseous state, which eventually condenses into moisture as they rise and cool. Imagine standing in a rain of molten iron, with clouds of hot food mocking you. It's about to snow silicate. It's very interesting that some brown dwarfs can have weather patterns very similar to our own planet, and even clouds of water vapor. But the funny thing is that brown dwarfs can have planets. In 2013, a group of astronomers discovered a gas giant orbiting around brown dwarfs. If we find more planets around brown dwarfs in the future, they will probably be small and rocky because there is less matter around young brown dwarfs to form planets than more massive stars. And in principle, life could arise on a planet in brown dwarfs. You could say that brown dwarfs have grown up and matured. We should probably do away with trying to classify them as families of planets or stars and start treating them as a special class of astronomy. Such objects. The birth of a star. A star is born in the interior of a dense dark cloud of molecular hydrogen, wanting itself under its own gravity. The cloud of gas may begin to collapse upon collision with another cloud or by the action of an explosion of a neighboring star, resulting in a shock wave propagating through the cloud. Then the cloud may break up into fragments, and the newly born bright stars will beautifully illuminate these fragments. As it happens, for example, in the Eagle Pillar Nebula. This was the name given to the clusters of interstellar gas and dust that the Hubble Space Telescope observed in 1995. 20 years later, in 2015, Hubble got another image of the same nebula. During this time, several tendril-like coils of gas managed to shift in space. Eventually, the star-forming region is cleared of gas and dust and becomes a diffuse star cluster. Such Pleiades, while still connected to each other by a common origin of the cluster's stars, are ready to scatter in different directions to embark on a wild ride through the vastness of the universe. Big Little Guys. The Great Magellanic Cloud is a dwarf galaxy 180,000 light-years away from the Milky Way. A companion to our galaxy, it has a nebula called 30 Goldfish, in which active star formation processes take place. Because of its enormous size of about 50 light-years across, the nebula can be seen through binoculars in the southern hemisphere's sky. It looks like well-defined spots. Stars stroll through there at a furious speed 10,000 times faster than in our Milky Way. If one imagines that living beings had time to appear on a planet around one of these stars, able to appreciate what was happening around them, they would see blue stars in the sky amidst a web of dust and gas, shining brighter than a full moon. Among its many attractions, the Goldfish region boasts that it contains some of the largest stars in the universe. Astronomers say that stars this big should theoretically simply not exist. They shine much brighter than smaller stars and burn up faster. At some point, their outer shells must be thrown off by their own radiation. And that's why, theorists say, stars more massive than 120 solar masses shouldn't exist. But some stars in the region of 30 Goldfish. Apparently, the masses reach St. 195 and, quite obscenely, 325 solar masses. To explain these masses, theorists have had to resort to sophisticated computer modeling. Some progress has been made, but there's still no agreement on the details. This actively fermenting stellar population is changing the environment with explosions, ultraviolet radiation from charged particles. In a few 1 million years, all the gas from the star-forming region will be carried away. It is simply given off by a powerful stellar wind, and future supernovae outbursts are similar. A star formation flash is like a forest fire on a plain that burns brightly and spreads rapidly in all directions. Both processes sow destruction, consuming everything in their path, but they also cultivate a nourishing environment, working toward the future. Just as the soil on the plain is enriched with organic elements, so the cosmic environment is replenished with heavy elements. Born in explosions of stars to then fall with seeds to future planets with plowed fields are left for one summer, unseeded under fallow to let the earth rest. Then it begins to bear fruit with renewed vigor. The star formation processes in the 30 Goldfish region have already passed peak climax in a few 1 million years, when the supply of interstellar gas runs out. New stars will stop forming, perhaps only in the surrounding regions. There will still be faint pockets of stellar creation smoldering somewhere. The cosmic clock. Night after night, rhythmic radio signals reach the Earth. The slowest of them can be compared in frequency to the sound of a hammer killing a nail in wood, or to the thump of a shoe. When we stand on a pole to kick up dirt, others are like a passing motor having to slow down at a stoplight. Some blend into a solid background. A little more, and a cosmic symphony pours from the heavens. The melodies are the same, always from the same points on it. No wonder that when astronomers first heard one of these radio signals in 1967, they wondered if it was a message from extraterrestrial intelligence. In fact, the 1967 signal was from a neutron star radio pulsar, which is sent by regular radio signals for a neutron star to be a pulsar. Its magnetic axis must be at an angle to its rotational axis. Then powerful jets of eruption radiation moving from the magnetic poles of the star will pay out space like a beacon beam as the star rotates. The jets send out radio waves that make the antennas of our telescopes vibrate. But we still don't fully know how these echoes of a star lying old are formed. Scientists Jensen Goldman and Andre Schmidt of Los Alamos, New Mexico National Laboratory, USA, have compared the mechanism for the birth of radio waves in pulsars to the supersonic pops that occur when a supersonic airplane breaks the sound barrier. The theory of relativity does not prohibit magnetic fields on the surface of a pulsar from rotating faster than the speed of light, he says. When they do, particles of opposite charges are repelled on opposite sides of the pulsar, where they emit radiation. Directional radiation is formed when the magnetic field crosses the light barrier. A sharply delineated pulse of the studded space emerges. Vortices and waves. In 1974, astronomers Russell Haas and Joseph Taylor discovered a double pulsar. The two stars orbited closely around each other, making one revolution in 8 o'clock. The distance between them steadily decreased as they spiraled closer together. This was happening at the same rate at which they would lose energy studying gravitational waves. Thus, the first proof of the validity of the general theory of relativity was obtained. First, they discovered pulsars, which rotated with laziness. It took them a few seconds for one revolution. But in 1982, a group of scientists led by Donald Barker, now deceased, discovered millisecond pulsars as many as 642 revolutions per second. At this dizzying speed, the pulsar was spinning, fueled by matter falling from a neighboring star. Other millisecond pulsars have since been discovered. By their fast, regular pulses, clocks can be checked, and these clocks are fantastically accurate. Some astronomers use them as reference clocks as detectors to search for gravitational waves. Interview with Jo Saline and her pulse. 50 years ago, Jo Saline Bell Barnell discovered a mysterious pulsating radio signal and the downsides of science to a young woman scientist. In 2017, a reporter for New Sanchez magazine interviewed her. To be fair, this was the second signal, quite powerful. The first signal could still be mistaken for an accidental outburst. The second one could already be seen as something serious. It took a while to realize we'd found a new kind of star. This was the very first pulsar. Today, we're still learning the true meaning of the discovery. It was 1967. We were searching for quasar with a radio telescope designed by Tony Hughes, my supervisor at Cambridge University. All we knew then was that quasars are very distant objects that produce radio signals with irregularly varying intensities. The new signal was powerful and came in short pulses with absolutely clear periodicity. It wasn't interference at all, although that was often the problem for us. Our telescope was a plexus of 2048 antennas spread over for acres outside the city. We had to accept the fact that when dealing with such a large area, there was bound to be a lot of interference due to interference. One day, by mistake, the frequencies we were monitoring were given to the local police. The first surprised the signal occupied only a quarter of an inch on the paper. The recorder was a pen, mechanical, moving along a paper tape. That time I set the tape recorder to a slower speed so that I could see the long signals from the quasars in detail. Then I increased the speed of the recorder at the time of day when I calculated the signal should have reappeared to turn it wide open. But there was no signal. It was gone. One of the first questions my colleagues asked me was this: could it be that I had turned the telescope on wrong? I was used to skepticism on their part. First of all, I was only a graduate student. In the second place, the fact that I was a woman played a negative role. It was even worse in Glasgow, where I did my undergraduate studies. There, when a woman entered the classroom, all the guys whistled, stomped their feet, tapped their cards and hooted. The people at Cambridge behaved more mannered, but they were also more arrogant. I felt myself there. Imposters, girls from the provinces, from Northern Ireland. I was sure that someone was bound to expose me and kick me out in disgrace. So I worked hard to keep my conscience clear. When did this happen? About a month later, the signal appeared again. I immediately called Tony Anthony Hughes. He said that if it was indeed a signal, then it must have an artificial earthly origin. Its periodicity could be compared to the beats of a metronome 2 regularly every 1.3 seconds, but I was sure he was wrong. As the Earth revolves around the Sun, the stars rise and set for minutes earlier each night. I first noticed the signal in early August. It was now November, and the signal was keeping pace with sidereal time. If the signal had an artificial origin, for example, radio interference from a car generator, it would hardly appear every day with such filigree accuracy 4 minutes earlier. I mustn't confess that I felt uneasy. When Tony walked into the observatory the next day and peered over my shoulder, sure enough, the signal had come through. That's when we had to wonder if its origin was terrestrial or celestial. I jokingly called it EMD1, short for Little Man, Little Green Men. But if it was a message from an alien intelligence, they used some pretty damn stupid techniques. For one thing, the signal was amplitude on modeling. Signal amplitude is often modeled from natural causes. If you want to send a signal several light years away, you wouldn't use amplitude modulation. You will apply modulation in frequency. That will make the artificial origin of the signal more obvious. We were able to estimate the distance to the source of the signal. It turned out to be about 200 light years away. The source was clearly in our galaxy, but well beyond the distance that our terrestrial TV and radio signals could travel into space. Since we started broadcasting on the radio band a couple decades ago. If they were green men, it's not clear what explains their desire to start broadcasting to the solar system. Nothing subject matter to them. Then we detected another signal, and a few weeks later a third and a fourth. Each of their own periodicity. This disproved the Little Green Men hypothesis, unless one seriously considers the assumption that a multitude of aliens from opposite ends of the universe are persistently trying to contact us. Obviously, it was some new type of star, but we didn't know it. When in February 1968, we published a magazine article entitled Observation of a Rapidly Pulsing Radio, the source, of course, the media picked up on a single line in the article, which said that we had first considered the possibility that a new signal had originated on an alien planet. I published under the name G. Bell. Note the full name of pulsar discoverer Susan Jones. Lynn Bell. And at first the journalists didn't realize I was a woman, much less a young one. When they found out over the phone, I began to get annoyed with reporters who asked if I was brunette or blonde. No other color apparently my hair could be. They also asked me what my chest, waist, and hip measurements were. I, by the way, was clueless. I was asked questions about my height, whether I was taller than Princess Margaret or not. And photographers asked me to undo the top buttons of my blouse. I have a pretty sharp tongue, and I would have loved to use it, but I felt I had no right to do so. Our lab needed publicity, and I needed good references to get a job. Another major disappointment befell me in '74 when Tony, Hugh, and Shu were awarded the Nobel Prize for the discovery of the first pulsar, and I was not included as a recipient. At the time, I said it was okay, because he was my supervisor. But in my heart, of course, I was very worried. It is unlikely that I was ignored because I am a woman. Most likely, the fact that I was a graduate student played a role. At that time, undergraduate and graduate students were not perceived as serious scientists. The situation has since changed for the better. Shortly after the discovery of pulsar, I got married and left radio astronomy. We traveled with my husband to the site of his new job. Since then, I have been working in astronomy in different fields, giving private lessons, lecturing, doing scientific and organizational work. But I still have a special warm feeling for pulsars and follow their publication in this field. Final collapse. It turns out that strong nuclear interactions are not always strong enough. If the mass of a star is more than 20 solar masses, then when its core runs out of fuel and it begins to collapse, no known force can resist the rush of the star will collapse inward. Gravity itself steadily compacts the matter, reducing its volume, leading to the formation of a black hole. If we use Einstein's general theory of relativity to describe what happens to the gravitational field of a black hole, we find that right in the center of the described events, the curvature of space-time becomes infinite. A peculiarity of a hole in the fabric of space-time, a so-called singularity, appears. But it's not all weirdness. Around the singularity, a spherical surface that is not visible is formed. An event horizon. Nothing caught under the event horizon can escape. But almost nothing. Stephen Hawking has shown that black holes may not be completely black. The quantum foam made up of particles and antiquity of birds born near the event horizon emits a special radiation, the so-called Hawking radiation. This could mean that in the unimaginably distant future, black holes will lose all their energy and completely vaporize. Although black holes have not yet been directly observed, scientists believe there is compelling evidence for their existence. They can be detected by the effect they have on astrophysics. Stellar or gas objects that are in the neighborhood. In 1972, this is how the first probable black hole, object Swan X1, was discovered. It is located at a distance of 6,000 light-years from the Sun. The invisible object orbits a blue supergiant. Gas from this giant falls on the invisible object and in the process of its gradually accelerating the fall, heats up and emits intense X-ray radiation. The mass of the object is about 15 masses. Sun is too much for it to be a neutron star. Therefore, it is very likely to be a black hole. Since Swan X1, many similar black hole candidates have been discovered in X-ray double systems. Theoretically, the birth of a black hole is thought to be preceded by a bright supernova flash. But there are stars whose masses are near the lower limit of the allowed mass range, acting on a different scenario. The black hole that forms can absorb most of the matter around it and suppress the explosion. We may have recently seen the birth of a black hole in just such a failed supernova. In 2016 at Ohio State University, Columbus, USA, a team of scientists led by Christopher Kachanov, processing data from the Hubble Space Telescope. Researchers were interested in the strange behavior of the red giant N6946H1. This star is located at a distance of about 20 million light-years from Earth. Scientists compared the results of its observations in 2004 and in 2009. In 2009, its luminosity suddenly increased for a few months, after which the star went out. New Hubble telescope images show that in the visible wavelength range it disappeared. These observations are consistent with theoretical predictions about what happens when a star of similar size shrinks to the size of a black hole. First, it emits a lot of neutrinos, which causes it to lose mass. Because the star's mass is small, its gravitational field becomes insufficient to hold the cloud of hydrogen ions scattered freely around it. The cloud of ions floats away from the star and cools. The separated electrons rejoin the hydrogen ions. As a consequence, a bright flash occurs, leaving a black hole. The true nature of the black hole is still unknown. Some theorists suggest that if an astronaut falls into a hole just below the horizon, he will be destroyed by a wall of fire. Hawking's fiery wave of radiation spikes. Others believe it is possible to fall through the mouth hole into another universe, which could happen near the singularity. Apparently, it will remain a mystery. Neither relativity nor quantum theory can answer this question, and physicists are battling to create a unified theory of quantum gravity that could do so. Instead of a sun, there's a black hole. If a black hole had planets, as in the 2014 movie Interstellar, they would be the most hospitable place in the entire universe. Cold and lifeless deserts, that's their entire landscape. But is that the case? It turns out that there is a strange property in thermodynamics, thanks to which such planets can in principle support life. According to the second law of thermodynamics, life requires a temperature difference to provide a source of usable energy to sustain life. Life on Earth exists because of the temperature difference between the sun and the cold cosmic vacuum. What if the sun and sky were reversed? The sun would become cold and the sky hot. Some black holes are among the brightest objects in the universe, actively radiating not only invisible light, but often in the radio, infrared, ultraviolet, X-ray, and gamma-ray ranges. This is because when falling on a black hole, gas and other substances heat up and begin to glow. As Tom Patney of Polansky University in the Czech Republic has shown, a saturated black hole has a temperature of effectively zero, which means it could potentially play the role of a cold sun. The rest of the sky has a temperature of 2.7 Kelvin, about -270 Celsius. This is the temperature of the cosmic microwave background KF of residual heat preserved since the Big Bang. According to calculations by the group of patrons conducted in 2015, Earth-sized planets orbiting a black hole the size of the Sun could extract about 900 watts of usable energy from this temperature difference. That's not much, but it's basically enough to sustain life. To illustrate their ideas, the scientists turned to the movie Interstellar, which is about a massive rotating black hole called Gargantua. Orbiting very close to this black hole is the planet Mill. The general theory of relativity implies that the gravitational pull of the black hole slows down time on the planet, so that 1 hour equals 7 years outside of this planet, meaning that time on this planet flows slower by a factor of about 60,000. It's just incredibly difficult to imagine for the average person. The energy of a quantum of radiation is proportional to its frequency. When a photon from KF arrives at Miller's planet, its frequency is increased by a factor of time dilation, i.e. the energy increases. Note: light coming from regions with a weaker gravitational field experiences so-called blue gravitationally displaced light with a time dilation factor of about 60,000. Miller's planet will be heated to nearly 900 degrees Celsius. In the movie, water in the ocean forms huge tidal waves, but the pattern say decay is more likely. Aluminum is a little further away from the black hole. Conditions on the planet would be cooler. Time dilation effects would be less, and the planet would be more hospitable to life. Other researchers believe that in reality this is unlikely, even though planets could form in orbit close to a black hole. There is a possibility that some matter would fall into the hole and radiate heat. Which black hole is closest to Earth? The closest known black hole candidate is in the X-ray double system at 616 Unicorn, where observations show a black hole with a mass of 7 solar masses orbiting an orange star. It's about 3,000 light-years away from us. But there are probably another 1 million undiscovered black holes lurking in our galaxy, so some of them will be much closer to us. Our galaxy is full of planets, with 1,000 planets already discovered. Amazingly varied eternal heat on giant planets, the cold of rocky worlds. Some may be habitable, but all are undoubtedly unique. What awaits us among the many billions of planets yet to be discovered? And can we hope to find alien life there? Alien zoos. Until 1995, the planets in our solar system were the only ones we knew for sure existed. Then graduate student Didier Loss of the University of Geneva discovered the first planet orbiting an alien star, and soon planets were sprinkling in like a cornucopia. Now, with more than 3,500 exoplanets discovered, and more to come, we have discovered a huge variety of other worlds. The search for life beyond Earth has always been a top priority for humanity, for life as we know it to exist requires light, water, mild temperatures, and moderate gravity. Therefore, rocky, Earth-like planets are of particular interest, especially if these exoplanets are in the golden weasel zone, where temperatures are just right to keep water in a liquid state. Note: this is how the potential habitable zone around the central star is referred to in English language literature. In the fairy tale, which in the Russian version is called Three Bears, Zlata in the Weasel manages to survive thanks to the fact that she makes the right choice from the sets of objects offered to her. A prime example is Planet System 1. A total of 7 moderately sized Earth-like planets orbit close to each other at a distance of 40 light-years from the Sun. Each has different physical parameters and different variations of ocean atmospheres and possible life forms. In principle, such systems of small planets, whose characteristics are as if repeating each other, but on a new level, like Matryoshka dolls, can be quite common in our galaxy and may be best suited for the search for extraterrestrial life due to the proximity of their orbits and mutual gravitational influence. They have come into a certain harmony with each other. For every 8 revolutions of the innermost planet L1 around the central star, there are 5 revolutions of the second planet, 3 revolutions of the third planet, and 2 revolutions of the fourth planet. Such a compact clockwork of clutches and gravitational gears could even facilitate the spread of life between worlds. Meanwhile, exoplanets 1140 at star 11 is now being actively considered as the most optimal place to look for signs of life outside the solar system. This super-Earth is 1.4 times the diameter of Earth and 6.6 times its mass. Despite the proximity of its orbit, its central star has 25 days in its year. The planet receives about half as much light as Earth because the star is cool. The planet's temperature is likely low, which means it is likely that it has liquid water. Star N1 is a red dwarf, and stars of this type tend to flare. Flares can damage likely life on nearby planets, but there is one unusually calm star, so the risks to its planet are not so great. LH is one of the 40b. It is only 40 light-years away from the Sun. It is one of the closest potentially habitable exoplanets among those found so far. In principle, we can observe the eclipse of star 1 of this exoplanet if it passes between us and the star as it orbits it. A great opportunity to look for the exoplanet's atmosphere, because the atmosphere will distort the starlight at the time of transit, and it will be possible to find signs of life if they are present in this atmosphere. The closest solid planet to us, about Moby. It is 4.2 light-years away from us. There are no accurate estimates of its size, but it is probably slightly larger than Earth, being near the red dwarf Centauri. This planet emits large doses of X-rays and has a powerful stellar wind pouring down on it. It's certainly not the best option for the existence of boxy life. What makes Beta attractive is that it's practically in our neighborhood, and we can look for an atmosphere and signs of life on it, and one day even send an interstellar probe there. Alien hell. Most exoplanets look hellishly unhospitable. The hottest Delta Beta found is called Hot Jupiter. It's twice as big as Jupiter in size. Its orbit is near a hot star, and its daytime temperature exceeds 4,300 degrees Celsius, which is comparable to that of an orange star. With this intensity of the star's radiation and heat, the gas giant's atmosphere evaporates at a rate of up to 10 million tons per second. By the time the star expands to the size of a planet, the planet may have already become an exposed core. But there are other exotic planets. If the heat isn't enough, you can find a planet where volcanoes erupt relentlessly and lightning blazes. Kepler-10 is the first solid-surface exoplanet discovered outside the solar system. It is so close to its star that its surface is covered with solid volcanoes. Volcanic dust is often the cause of lightning flashes. One model, which takes data from terrestrial eruptions as a basis, suggests that on planet Kepler-10 it could be as many as 1 trillion lightning flashes per hour. Planet XM, that's 1,000 light-years from the Sun. That's another story. Mitya reports from this amazing world would focus on changes in cloud cover. This planet's sky is hidden by ruby, its sapphire, and its clouds. And that's no exaggeration. The planet's luster changes over time. Most likely, this is due to the movement along the planet of its brightest areas, namely the pregnancy of the cloud cover at high temperatures prevailing on the planet. It is possible that the clouds may consist of corona. It is from this mineral that sapphires and rubies are formed. On Earth, as other planets are searched for, most exoplanets have been discovered by one of two methods. The planet's gravitational field can make the star wobble slightly, and the lines in the star's spectrum will experience small shifts. Or if the orbit is in the plane of the line of sight, the planet may pass in front of its star, and we on Earth will see the star dim periodically. Such an event is called a transit. 1,000 planets have been discovered by the transit method using the Kepler Space Telescope. The same telescope has detected a change in the brightness of a number of planets, which may indicate a change in weather conditions on them. But both of these methods don't work well when the planet is small or far from the star. That's why the first exoplanets to be discovered were the so-called hot Jupiter giant planets in close orbits to their stars. It is also clear why the catalog of extrasolar planets is dominated by large planets with high temperatures. Some planets have been detected by gravitational microfission, where a planet's own gravitational field, along with the gravitational field of its star, enhances the brilliance of a star farther away. Gaining sight. There are other methods, such as direct observation, but they require much more effort. The cold and lonely planet 2 Mars J2126 in a very wide orbit is one of the few planets that we have been able to see directly. It orbits its luminary dim brown dwarf at a distance of 1 trillion kilometers, 6,900 times farther from its star than Earth is from the Sun. With the method of direct observation was also able to detect the motion of the 4 planets in the system HR 8799. Along with hot Jupiter conventionally adopted and such names for newly discovered planets such as super-Earths, big rocky planets and mini-Neptune and the smallest gas giants. But not all planets fall under this classification. A separate class had to be invented for the planet Kepler-10, which is about 560 light-years away from us. The radius of the planet only slightly exceeds the diameter of the Earth. Therefore, at first astronomers attributed the planet Kepler-10 with it is not Neptune. But in 2014, new information came in. It turned out that this planet is 17 times more massive than Earth, which, given its diameter, means that it must be incredibly dense. Such solidly strong planets have not been observed before. Planet formation models didn't predict this combination of parameters. We had to call it Kepler-10, the first mega-Earth. An old planet. When Earth first formed, these 5 small planets were already as old as the world. The age of the planets is comparable to the age of the universe itself. They're only 20% younger than it. The Kepler Space Telescope has discovered the planets in an orange dwarf called Kepler 44 at a distance of 117 light-years from Earth. This star is slightly smaller than the Sun. It is believed that the planets around orange dwarfs may well develop alien life, because such stars usually do not show activity and can remain stable for 30 billion years. Recall that the Sun's lifetime would be only 10 billion years. Assuming that life arises by chance, older planets have a better chance, more time to have a suitable sum of factors for the emergence and development of life. The size of the planets at Kepler 44 is between 0.4 and 0.74 Earth radii. The method of astroseismology estimated the age of the star about 11 billion years. Recall that the age of the universe is estimated at 13.8 billion years. Of all the planets discovered to date in the galaxy system, Kepler 44 is among the oldest systems with Earth-type planets. The planets of Kepler 44 are too hot. Life as we understand it is impossible there. But their very existence leaves us with the hope that somewhere there may be cooler worlds and no less ancient. Strange new planets and planetary systems discovered outside the solar system strike us as surprisingly diverse. Some of them bask in the light of 4 suns at once, others, having left their native lands as pariahs, wander around the galaxy with not a single star nearby. Still others have joined the very young stellar breed, barely 1 million years old. Milk pumps. Among the stars, theorists are making their speculations about what solar worlds should be like. Their naive theories don't stand up to the scrutiny of new facts, and there are likely many more surprises ahead. In an attempt to anticipate the surprises that nature may present to us, researchers zealously fantasize, inventing new types of exoplanets that may be discovered in the future. It should not be assumed that bored astronomers are just playing games. After all, it is very important to understand to what limits nature can reach with its ability to create new measures. Through this we can compare our solar system with other planets and conceptualize our place in the universe. many fictional worlds present a real challenge and confusion to our formal theories of planet formation. The very understanding of what a planet is. In addition, improvising on new exotic types of planets is useful also because it expands our inevitably. Earths are cylindrical. By analogy with eccentric. Imagining where life might arise eventually in the search for aliens Chen Helt's fantasy. Dual planets in our solar system. Planets are far apart. Around the planet's orbit they're much smaller satellites. It is generally believed that planets form from a protoplanetary disk when dust particles condense around a young star. Gradually the dust is poured into initially small conglomerates, which become rocky clumps that start out in orbits and suspect all matter that meets their path. From the debris that doesn't attach itself to the planet and keeps spinning around it, satellites are formed. Another version of the formation of satellites is that they pull in fragments of planetary bodies, which hit in the early stages of the formation of the planetary system and ricochet bounce off each other. But there is a third option, and he is sympathetic to many astronomers. Our moon could be formed when the primordial Earth crashed into a planet the size of Mars, broke away from it. Significant chunks subsequently merged with each other to form our natural satellite. If, say, it was not a frontal attack, but a tangential impact, one planet could have boarded the other, and it would have been a double planetary system. The discovery of double planets could shed light on the tumultuous childhood of solar systems that didn't survive all that well. If such a scenario of the collision of two planets, which resulted in the formation of our moon, is confirmed, it could be applied to the theory of the formation of planets, not just satellites of sponges. Fortunately for astronomers, double exoplanets should cast characteristic double shadows as they cross and partially eclipse the shining disks of their stars, leaving transiting signals easily detected by the Kepler telescope and other observatories. They are designed to search for new worlds. Surely the most intriguing would be the finding of two Earth-like planets in the same planetary system. Imagine that every night another planet similar to our own would descend in our sky. And it too would be habitable, and a civilization would arise on it too, which one day would want to go into space. Group planets. The planets in our solar system each follow their own path, accompanied by faithful companions. But sometimes they have to endure the neighborhood of other celestial bodies. There is such a group of asteroids, called Trojan asteroids, which crowd in the vicinity of Lagrange points. These are very attractive places where the combined gravitational forces of a planet and its star allow a third body to hover over the planet almost motionless. Jupiter oversees a whole army of Trojans that orbit the Sun with it. And Earth has its own Trojan asteroid, a rocky clump codenamed 2010 TC7. Theoretically, there is nothing preventing objects the size of an entire planet from orbiting in a group orbit at roughly the same distance from their central star. Configurations of this kind can be maintained for 1 billion years, until some disturber of gravitational tranquility appears, which can break the exquisite choreographic ensemble of waltzes, shouting in harmonious orbits of celestial bodies. It is not quite clear, though, how such a configuration can actually work out in reality if the possibility of existence of several planets on one orbit is proved. This would contradict the generally accepted dogma that a planet by the force of gravity should clear the neighborhood of its orbit from other large objects. And this is what caused Pluto to be dropped from the list of full planets in 2006. Such measures could even cross a beam thanks to meteor strikes that would blast away the rocks that carefully adorn the hardy bits of genetic material. Yates and similar measures. The gas giant VAZ-12b orbits its star at such a possessively close distance that the star's strong gravitational pull has distorted its shape into a convex oval of space. Oksana and his colleagues at George Mason University, Virginia, USA, decided to investigate how this tidal distortion might affect a rocky Earth-like planet. They calculated that exoplanets of this type from the expansion could become 20% wider along the equator than along the meridian, and then break apart. The discovery of such planets, shaped like rugby balls, could be the impetus for the development of a planetary response to gravitational pressure. A star opens up a whole new avenue for studying its internal composition. For example, it would be possible to find out whether a planet is mostly solid or gaseous. In addition, the gravitational field will act differently on the atmospheres and colored planets in different places. Because of this, the climate can change in unpredictable ways. Botanical planets. As the planetary system evolves, planets can migrate inward, closer to their central luminary, or outward, pushing them toward the stellar crucible. Gas planets may lose their atmospheres, being blown away by sultry stellar winds. Eventually, these planets will have nothing left but bare rocky cores. Such planets torn down by the pogroms that formerly concealed their underlying and now cast away are commonly called Catholic by analogy with the subterranean deities. In Greek myths, if, for example, a cold mini-Neptune moves into the temperate habitable zone of its star, the extra heat may not only blow away its atmosphere, but also melt the exposed surface layers rich in water ice. Such a planet could become an ocean-covered world with life-friendly air. Storm planets. You may think this is pure mind game, but some planets may be in a kind of orbital purgatory between two stars. In a double system, they spin in a spiral around the axis connecting them, tugged by a gravitational rope then to one, then to the other star. Such a model of planetary motion was proposed by theoretical physicist Eugene Ox from the University of Bern in Alabama, USA. Under certain conditions, the orbit, which will move the planet as a squirrel in the wheel, is quite stable. OCS carried out the calculations for a planet in the double-star system Kepler-16, consisting of an orange dwarf and a red dwarf, located 200 light-years away from Earth. The planet discovered by astronomers orbits around the two stars. The storm planet in the WorldCom model makes a dead loop of one revolution in a V-shaped orbit in less than 1 Earth week. Any life form that could survive on such a persistent planet, where the seasons change in a matter of days, would witness one of the strangest phenomena in the night sky. When the storm planet reaches one of the extremes of its orbit and embarks on a return trip to another star, at that moment the sun closest to it seems to reverse its direction. The search for extraterrestrial intelligence. Our attempts to find extraterrestrial intelligence are akin to waiting for a person to stand at a payphone and wait for it to ring. Since the late 1950s, the prevailing view among scientists has been that extraterrestrials must be emitting radio signals into space. So all we have to do is tune into the right frequency and we'll hear them. But our surveys so far have only covered a few 1,000 stars in a galaxy of hundreds of billions of stars. No wonder we still haven't heard a sound from space that could be attributed to other civilizations trying to contact us. The latest project to search for extraterrestrial life started in 2016. It is designed to last 10 years. The budget is $100 million. The project is called Breakthrough Technology Listening. It is funded by technology and innovation entrepreneur Yuri Milner. The project will install 2 of the world's largest radio telescopes that will probe 1 million of our closest stars across a wide band of the radio spectrum. It is expected to listen to 10 times the broader spectrum of the sky than all previous surveys combined. Despite all the hopes associated with it, the project is the brainchild of mid-20th century thinking, and the organizers themselves agree. Just as the widespread use of steam power on Earth was only a transitional stage in its technological development, communicating via electromagnetic radiation may prove to be no more than a passing fad in the life of a distant civilization. Given that extraterrestrial civilizations may be several 1 million years old, our radio search may seem a laughable anachronism. Yet exciting new strategies for finding aliens are opening up before us. From scrutinizing the way they breathe to discovering their advances in space technology, the atmospheres of other planets of all the life forms we know are machines for reproduction itself. In the process of this reproduction, fuel is turned to waste. Over the course of time, the biochemical processes of countless 1 billion individual beings can transform the entire world in a very tangible way. On Earth, virtually all animals inhale oxygen and release carbon dioxide, while plants spend most of their time doing the opposite. Some bacteria emit methane, and so life produces a whole cocktail of diverse gases. And it's a distinctive biological feature of our planet. The James Webb Space Telescope, due to launch in 2023, will conduct deep scans of the atmospheres of exoplanets and could give us some insight into biosignals from other worlds. The telescope will study planets passing through the disks of their stars. During these tiny eclipses, light from eclipses and stars passes through the halo of the planet's atmosphere. Spectral analysis can detect stellar imprints of molecules 1 trillion kilometers away with a certain amount of luck. Sustain signs of biological activity similar to our own. On other planets it will be possible to detect in practice, however, exotic geologic phenomena not similar to Earth's, and also completely alien to our own. Biochemical processes can distort the signal and frustrate our efforts to decode it. Poisonous gas, even if an exoplanet's atmosphere shows clear signs of life, we won't know if it's inhabited by mindless green slime or intelligent city builders. A more reliable approach to finding soulmates might be to try to detect signals of man-made origin, certain chemicals that only alien intelligences can produce. Suppose intelligent extraterrestrials have a basic knowledge of chemistry and nurture, at least for a certain period of their evolution. The same predilection for global pollution as we do. This is the reasoning of astronomer Abel of Harvard University. He believes we should be looking for traces of gases such as chlorine, fluorine, carbon for short, in the atmospheres of other planets. Once ubiquitous in air conditioners and aerosol cans. These harmful ozone-depleting substances are now being phased out. However, some of them can persist in the atmosphere for tens of thousands of years, and this is expanding for us. The window for detecting alien biological activity. For the James Webb Space Telescope to spot signs of X and Y, the levels of these substances in the atmospheres of exoplanets would have to be at least 10 times greater than Earth's. That's too much even for civilizations that care little for the environment. Unless we assume that the inhabitants of cold planets specifically maintain high concentrations of these substances in the atmosphere to keep their planets warm with the help of the greenhouse effect. City lights. If representatives of an alien civilization have a limited ability to see in the darkness, as we do, they may wish to decorate their environment with artificial lights. Can we then see city lights shining on the dark side of planets with our current Earth-based telescopes? Tokyo can be seen from Pluto. To see the city lights from a planet near our nearest star would require a space telescope with a mirror diameter of 200 meters. The mirror size of the James Webb Space Telescope would be about 40 times smaller. It is unlikely that a telescope of that size could be built in our 100th year. But maybe the aliens have cities, compared to which Tokyo is just a small dim spot. A planetary-scale cityscape can in principle be seen with a space telescope, which we hope to build in the near future. Admittedly, our attempts to discern the urban landscape may be thwarted by the giant colors of bioluminescent algae that can mimic glittering cityscapes. And, like radio communications, artificially lit cities may just be a transitional stage in the life of an alien civilization. In which case, we'd be very lucky to witness this stage of their evolution. Aliens in the neighborhood. Humans are probably going to start actively exploring the solar system very soon. We may even be able to go on distant space journeys. It's possible that alien civilizations are already ahead of us. If we even leave aside the almost physically improbable hyper-engines of both Krotov and Nora. Those means of transportation that are very difficult to detect. What exotic modes of alien transportation we should be looking for? If guided by our ideas about innovative technologies, space aliens could apply star years and solar sail using the pressure of stellar wind or other radiation. So far, our efforts in this direction have been small. But if we can create a sail the size of a soccer field, which will be inflated by radiation from a powerful laser, then flight on such a sail is quite possible. With modern telescopes, a stream of such bright light is easy to spot. In addition to searching for aliens in the radio band, the Breakthrough Technology Listening Project will scan outer space in an attempt to detect radiation from space lasers pointed in our direction. This could help us detect aliens by sailing them. The vastness of the universe. It is much harder to detect alien ships powered by nuclear or fusion engines. It is difficult to see the light signal from such aircraft unless the star path of aliens will not pass under our very noses. Detecting aliens would be easier if they made full use of the physical phenomenon we know about. They could, for example, use an engine based on the annihilation of matter and antimatter, which gives the highest return in terms of fuel conversion. Such a ship would launch inversions, photon, and formation. Perhaps the giant telescopes of the future will be able to detect interstellar transport streams during galactic rush hour. Large-scale construction in October 2015. The internet was flooded with rumors that alien civilizations had finally noticed. The Kepler Space Telescope discovered that the light flux from the unofficial star KC846-2852, known as Toby, fluctuates by as much as 22%. Usually such fluctuations in the luminosity of star system sex behind the planets can be explained by the effect of eclipses. But in this case, there was a catch. By comparison, Jupiter blocks only 1% of sunlight, and since the radius of the star KC800, Ts28, b-52 is more than 1.5 times that of our Sun, what is eclipsing it must be truly colossal. Have we really encountered a manifestation of vast extraterrestrial construction? In 1960, physicist and engineer Freeman Dyson laid the foundation for the concept of searching for extraterrestrial civilizations. He proposed looking for evidence of large engineering structures created by extraterrestrials, just as the Egyptian pyramids that have survived their creators allow us to study the history of the ancient world. Megastructures in space could provide a reliable target for hunters of alien civilizations. A classic example is a sphere that collects solar energy and is made up of a large number of individual elements, or perhaps even represents a hard shell around a star. This sphere is ideal for projects such as building supercomputers powerful enough to simulate the entire past and future of the universe. Completed and commissioned. The sphere completely obscures the star from us, but we still have hope of capturing the dissipated heat escaping through gaps in its construction, or noticing occasional flashes from the work in progress. To us, they may look like a partial eclipse of the star as a result of the planet passing across its disk. It turned out that fluctuations in the brightness of the star are more noticeable in the ultraviolet than in the infrared region of the spectrum. This is hardly possible in a partial eclipse of a star by large objects. Another popular explanation for this phenomenon is an irregular ring of dust around the star. However, other stars may provide us with even more striking evidence for the existence of alien megastructures. Feeling the heat. Of course, we can refer to ourselves as an advanced civilization, but the table of ranks ranking system developed by Soviet astronomer Nikolai Kardashev finally and irrevocably puts humanity in its allotted place in the universe. In the 1960s, Kardashev proposed to evaluate the degree of development of a civilization by taking as a basis the amount of energy they are able to use. A civilization that is able to extract all available energy from its home planet has a status of slip 1. The civilization, having constructed a sphere around its star, has received the status K2, and the one which is able to absorb all energy in its native galaxy occupies the top of the pedestal with the status K3. According to our humanity deserves a score of K0.73. Despite all the perfection of K2 and 3 civilizations, the fundamental laws of physics suggest that a significant amount of heat will still be lost through infrared radiation. The most ambitious project to search for Katrina civilizations is the HIDE survey of heat gaps from alien technology. It was carried out using NASA's Orbiting Space Telescope. WISE, short for WISE, is a WISE broadband infrared surveyor. WISE narrowed the search from 100 million galaxies to 100,000 galaxies with intense infrared emission. However, further analysis showed that this additional infrared emission is fully consistent with the model of intense star formation in particularly dusty galaxies. At the same time, Super 3-level civilizations may well remain invisible, as they do not recycle all of their galaxy's energy, but only a fraction of it. Along with grandiose construction within their star system, extraterrestrial civilizations may not neglect fundamental science. Alien nuclear physicists, if they exist of course, are likely laughing at ours. The lauded Large Hadron Collider, capable of colliding particles with energies as high as 13 electrons. Big physics starts with an energy 1 billion times the collider's energy. Such energy will allow gravity to be combined with the enduring fundamental forces of nature. We may not see an extraterrestrial particle gas pedal to explore such energies because of its colossal size. It could be the size of a galaxy, emitting abundant heat and radiation. The most likely particles emanating from this large galactic collider with dimensions of 2xSL are neutrinos, tiny bits of nuclear shrapnel that hardly interact with normal matter. Yet these neutrinos would be so rare in the overall cosmic census that today's detectors like the kilometer-long ice cube in Antarctica would not boast an abundant catch of such particles. For this purpose, we need a detection network of 1 billion sensors deep in the Earth's oceans. An investment of this magnitude may be slightly beyond the means of any billionaire philanthropist. Chapter 8: Mysteries of the Milky Way. Even if you are not in a city, where it is almost impossible to see the stars in the sky due to the strong artificial lighting, even outside the city limits you will not be able to fully appreciate the grandiosity of the Milky Way. Our galaxy appears to you as a starry streak. What we see is just a faint echo of the true grandeur of the galaxy, which has hundreds of 1 billion stars forming a special structure. Compared to some of them, our sun shines as dimly as a candle. In addition to stars, the galaxy can also flaunt colorful gas clouds and ink over dark streaks of dust. The closer we get to the center, the more we approach fierce stars with faint X-rays, the prominent presence of a monster slumbering in the heart of the galaxy. Home on an island. Sitting inside the Milky Way, we can't see beyond the trees to the forest of interstellar dust smothering much of the galaxy and completely obscuring some areas from us. But gradually, the outlines of our galaxy's giant geographic map are emerging from the fog. After all, over the past few 10 years, astronomers have been painstakingly mapping our galactic island. The most characteristic feature of the Milky Way is a dense disk of gas and dust stars with a cross-section, approximately 100,000 light-years across. From the center of the disk protrude two helices of stars about 12,000 light-years across. From the side, it resembles an egg crate with eyes made of two eggs lying side by side. These bright parts of the galaxy are surrounded by an enchanting halo of old stars and more than 150 globular clusters. In total, the Milky Way contains at least 250 billion stars, with some estimates as high as 1 trillion. This picture began to emerge in 1923, when American astronomer Edwin Hubble first accurately determined the distance to stars in a distant indistinct day of light, called the Andromeda Nebula. His measurements showed that the Andromeda Nebula was essentially an isolated cosmic island of stars. By analogy, it was conceivable that our Milky Way is also an isolated stellar island in space. A spiral scattering of stars. Observations made since then have shown that our galaxy has bright spiral arms made up of dense, a cluster of stars intent on the central disk. We can't go outside the Milky Way to see what it would look like from afar, but it probably resembles a giant spinning firework. Spiral galaxies this large are not common. Most galaxies are small, rather dim and blot-like. Our galaxy is magnificent in comparison. However, our view of the universe remains fragmentary. The very appearance of the spiral structure remains a mystery to us. Stars move around the center of the galaxy in relatively circular orbits, not spirals at all. Sleeves. Scientists believe the special structure is created by a disturbance called a density wave. Stars and clouds of gas in their motion periodically get caught in spiral density waves that stretch from the center of the galaxy to the edge of the disk. Just as cars flow into more intense streams, the waves compress the gas and trigger the formation of numerous new bright stars, which are highlighted by the spiral structures. However, it is not clear whether density waves themselves are already coming from spiral patterns in our galaxy are quite difficult to see, as they are located ribbed to us and in addition are hidden by dense cloud. Dust. Astronomers did their best to map the positions of the bright stars inside the spiral arms, and radio telescopes picked up signals from the compressed clouds of hydrogen around them. In this way, it has been possible to trace the four main spiral arms: the Southern Cross Shield Arm, the Sagittarius Keel Arm, the Perseus Arm, and the Outer Arm. There are also several small arcs between them. In late 2003, a research team led by Naomi Mackler-Griffiths at the Australian National University in Canberra, Australia, reported the discovery of another arm fragment. Using the 6-meter Parkes radio telescope and an array of 6 22-meter Bolivian antennas, scientists found an arch about 77,000 light-years long made of dense hydrogen running along the outer edge of the galaxy. Earth. The arch appears nearly 150 times wider than the full moon and is likely part of the galaxy's outer arm. The undulating effect in 2013 created a three-dimensional map of the velocities of several 1,000 stars and their distances. From this map, it appears that the galaxy is making undulations and motions. Mary Williams and her colleagues at the Leibniz Institute for Astrophysics in Potsdam, Germany studied data from measurements of radial velocities, abbreviated ROL, for nearly 500,000 stars up to 6,500 light-years away. In all directions, they mainly studied stars from the so-called red. The densification in the Hertz diagram of Russell's consort, which have roughly the same brightness and are therefore easier to compare when calculating their relative velocities and distances to them. The scientists analyzed data on the stars' horizontal motions and data on their motions in the perpendicular direction. They found that stars closer to the center of the galaxy form a thickening protruding outward from the plane in both directions. Stars farther from the center, on the other hand, form a structure that is solid inside. The movement of individual stars in these zones is chaotic. Some of them move in different directions. But if we could see the big picture from the outside, our parts of the galactic disk would resemble the Colossus flag in the wind. Perhaps the wave is a reminder of an outward collision between our galaxy and another galaxy. Or it could be a consequence of the fact that around the Milky Way revolve Magellan, its cloud satellites of our galaxy, and shift its disk. Consider a more exotic possibility, namely, that the perturbations are caused by large masses of the notorious dark matter. Perhaps, using data from the European Space Agency's Gaia Space Telescope, we will soon learn whether the Milky Way as a whole makes oscillating motion. The Gaia telescope will be used to make a three-dimensional map of our galaxy. And now the work is in full swing. A dark beginning. How the Milky Way formed is a very difficult question to answer. The oldest stars in the galaxy are about 13 billion years old. Assuming that they formed less than 1 billion years after the Big Bang, which occurred 13,800,000 years ago and started the universe. From the Big Bang, a hot, super-dense fireball emerged, which gradually expanded and cooled. But this fireball was not completely homogeneous. From it tumbled myriads of dense clots that seeded space with the massive galaxies that present themselves before our eyes today. In the details, however, astronomers are not entirely sure whether stars or small star clusters formed first, and then galaxies formed under the gravity of the galaxies, or whether the gas and dust in the young universe first formed huge structures from which individual stars later emerged. Good neighborhood. If there were real estate agents and galactic real estate agents in the wild, they would be interested in selling the solar system. The property is in a quiet neighborhood with great views, with plenty of chemical raw materials. And no problems from noisy stellar neighbors. The Sun is nestled in a suburban area about 26,000 light-years from the center of the galaxy. A little less to the outer edge of the galaxy. It is quite possible that we are not accidentally placed in the Daxon zone of the Milky Way. Some scientists say that for life to evolve on a planet, it probably needs many elements heavier than hydrogen and helium to make molecules with different biological functions. And these heavier elements are most abundant closer to the center of the galaxy. So planetary systems on which life could in principle form should not be too far from the galactic nucleus. On the other hand, the development of civilization may require several billion quiet years, and the center of the galaxy cannot provide such comfortable conditions due to frequent supernova outbreaks. The clash of the titans. No galaxy evolves in complete isolation. In fact, galaxies are constantly in motion, and gravity, the attraction between them often pushes them on opposite courses. Stars from a star system in a galaxy are usually a few light years apart, so when galaxies converge, their stars pass a decent distance apart. However, the interstellar clouds inside the galaxies collide, then collapse due to gravity, causing new stars to form. Galaxy collisions are far from rare. At least one such event is happening right now before our eyes. The Milky Way is swallowing up a dwarf elliptical galaxy in the constellation of Sagittarius. This galaxy sits on the opposite side of the galactic disk from us. It contains about 30 million stars, mostly old and yellowish, and is passing through the disk of our galaxy at a speed of about 250 kilometers per second. In the distant past, much larger mergers probably took place. Our galaxy is organized as follows. A thin disk of the Milky Way, made up of stars of all ages, into a thicker disk containing only older stars. And the likely explanation is that the Milky Way swallowed up another galaxy about a tenth of its size, or several smaller galaxies. And this happened at least 10 billion years ago. The gravitational field created when the galaxies interacted scattered the stars that had already formed in the Milky Way in different directions. So the thicker parts of the disk were formed in a mere 3 billion years. Our descendants may witness an even grander collision among the dozens of galaxies that make up our local group of galaxies. Only the Andromeda Nebula matches the Milky Way in size and is 2.2 million light-years away from our galaxy. But every minute the gap shrinks by about 8,000 kilometers. In about 3 billion years, these giant galaxies are expected to collide, which will change both of them beyond recognition. Scientists have built a plausible model of this event. The galaxies could pass back and forth through each other 2 or 3 times. In doing so, the galaxies will pull long thin jets of stars out of each other, before forming one rather shapeless optical galaxy. By this time grown to the size of a red giant, the Sun will bring down all life on Earth. Perhaps humans, or other members of intelligent life to succeed us, will enjoy the spectacular view of the Andromeda Nebula approaching the Milky Way and complementing the sky. Star mountains. Galaxy sees galaxy makes the closest companion galaxies to the Milky Way. We can chart the same crime as the Milky Way itself of dismembering a celestial object that came too close to it. There are over 50 galaxies orbiting around the Milky Way. The brightest of these is the Large Magellanic Cloud. It is located at a distance of 160,000 light-years from Earth. This galaxy is so bright that it can be seen with the naked eye. In 2016, Nicolas Martin and colleagues from the University of Strasbourg in France discovered a densely packed group of stars, partly similar to globular clusters in distress. The cluster is on the outskirts of a large grave cloud about 42,000 light-years from its center. The shape of the cluster is oval rather than spherical. Its long axis points directly at the Large Magellanic Cloud. All indications are that the gravitational field of the Large Magellanic Cloud, its cloud, is attracting the near side of the cluster, pulling it apart. But if star clusters for a long time revolved around the Large Magellan, its cloud, it is not clear why the destruction processes began in it just now. Therefore, Nicolas Martin and colleagues suggested that the cluster originally revolved around the less massive galaxy of the Small Magellanic Cloud, located nearby. Because the gravitational field of the small cloud is weaker, it didn't do much damage to the cluster. It was only recently that the Large Magellanic Cloud ripped the cluster out of the small cloud's embrace and began to destroy it. Hydrogen gray clouds. If a space monster from the depths of the universe were to taste the molecular clouds of Sagittarius B02, it would need a giant, supersensitive tongue. But he would hardly like it. The Sagittarius B2 molecular cloud is about 100 light-years in diameter and is near the center of our galaxy. It is a mishmash of hydrogen and helium with a mass of 3 million solar masses. Added to this cocktail for sweetness are glucose, ethylene, syrup, figurative and toxic elements, antifreeze and ethyl ether, and some acids with a fruity lemon flavor. Instead of vinegar, heavenly bartenders use acetic acid. In short, there's plenty of booze to go around. Ethyl alcohol in space was first discovered in this very cloud in 1975. All of this is spiced up with less tasty things like acetone, which works well as nail polish remover, and hydrogen sulfide, by the smell of which rotten eggs are unmistakably recognized. The amounts of all these substances are vanishingly small compared to hydrogen molecules. But since the size of the cloud is huge and in some places it is illuminated by bright and cold stars, even micro-impurities of various substances leave visible traces in the spectrum. For more than 40 years now, Sagittarius B2 has been for space chemists something like the Valley of the Kings or a mountain range called the Burgess Shale, a place to return to again and again. Behind the discovery, studying space chemistry helps us gain some insights into the origins of life. Interstellar Organic Chemistry Lab. It only needs a few ingredients in clouds like Sagittarius II, as well as in the cloud that gave birth to our solar system long ago. Tiny dust particles can become coated with a thin crust of ice. When radiation falls on the ice-covered grits, free radicals arise and chemical reactions begin that can create larger molecules. Stars also condense out of the cloud, as is happening now in the northern fragment of Sagittarius II. Their radiation heats the ice, and the resulting molecules vaporize. The processes of changing chemical bonds in the molecules lead to radiation in the radio band, which we can detect on Earth in this particular part of the cloud. Surprisingly complex chains of organic molecules have been found. In 2008, a group of scientists led by Arno Bogus of the Max Planck Institute in Bonn discovered the neutrino-colored compound amine, a related compound to goloxin, the simplest amine, an acid. In 2014, the same group announced the discovery of the first interstellar molecule with a branched carbon framework. This suggests that complex amino acids can also grow in space. And in 2016, another team of scientists discovered the first washing interstellar molecule structure, a structure common in biology that is characterized by a lack of symmetry with respect to the right and left sides. Many of the same molecules, including amino acids, have been found in comets in our solar system. This is also true of meteorites. It is very likely that meteorites, making forced landings on the surface of the Earth, delivered to our planet some of the ingredient necessary for the beginning of life. But before that, long before that, they may have grown into thin icy crusts of clouded films, drifting through space and bathed in the light of newborn stars. Dark heart. Monsters lurk in the heart of the Milky Way, watching the speeds of stars flying around the galactic center. Astronomers have concluded that it hides an invisible dense object about 4 million times more massive than the Sun. This mass is concentrated in such a small region that the only plausible explanation is a supermassive black hole. Most large galaxies, if not all, harbor black holes at their centers. Some of these monsters self-consciously and enthusiastically consume the gas around them, falling on the black holes. The gas heats up and creates quasars, the blazing beacons of the universe. But our own supermassive black hole, called Sagittarius A with a star, looks unusually sleepy and dim. It emits only modest streams of X-rays and radio waves. And this despite the fact that our monster has plenty of food. There are many massive stars orbiting around it. According to scientists' calculations, their stellar winds contain enough gas to annually supply the black hole with matter whose mass is equal to 4 times the mass of our planet. If Leviathan at the center of the galaxy swallowed that much food, it would shine 100 million times brighter in X-rays. Could Sagittarius' modest appetite be because the gas around it is too hot? Stellar winds collide in the stellar disk and heat the gas to 10 million degrees Celsius before it begins to collapse into the black hole. Particles of the collapsed hot gas engage in rapid random motion, and it's difficult to drive them into the black hole's lair. The jets of matter from black holes can also prevent the gas from getting inside. Old flares. The weakness of our supermassive black hole may be just an incoming phase in its life. In 2003, the integral satellite of the International Gamma-Ray Astrophysics Laboratory recorded hard X-ray emission coming from the Sagittarius B2 gas cloud, which is about 350 light-years away from the black hole. It is highly likely that to observers on Earth about 350 years ago, the black hole at the center of the galaxy looked incredibly bright at short wavelengths 1 million times brighter than it does today. If Newton or Galileo had invented a powerful gamma-ray telescope, they could have seen at the very center of the galaxy a dazzling sight. The bright radiation from the center reached the N2 cloud 350 years after the outburst. And now we see the Flores cloud associated in X-rays. So our galaxy may have been active relatively recently and may well flare again in the future. It's not known when, though. A much more intense flare apparently occurred 2 million years ago. In 2010, using the Fermi Gamma-Ray Space Telescope, astronomers discovered a pair of spectacularly mysterious structures that stretch perpendicular to the plane of the Milky Way for 25,000 light-years. Each emit radiation in the gamma and X-ray range. They've been called Fermi bubbles. Several theories have been devised to explain these mysterious objects. For example, gamma rays may arise from the annihilation of dark matter, or intense bursts of star formation have led to the appearance of supersonic winds. In 2013, Bill Matthews of the University of California, Santa Cruz, USA, and Fly Ross and the Shanghai Astronomical Observatory, China suggested that the bubbles were caused by a flare of Sagittarius A. Their idea is that when matter falls on a supermassive black hole, this matter accumulates in the surrounding disk, heats up and begins to glow. When a large amount of matter falls into the disk, energy is released in the form of bright jets of particles flying out along the black hole's axis of rotation. As the modeling of the process suggests, 2 such jets of high-energy particles could lead to the formation of Fermi bubbles. Calculations suggest that the flare could have occurred between 1 and 3 million years ago and lasted for several 101,000 years. Jess Blount of the University of Sydney in Australia suggested that such a flare could lift the veil on another long-standing mystery. In 1996, astronomers discovered that part of the Magellanic Stream of a fast-moving jet of hydrogen gas about 240,000 light-years away from the Milky Way glows about 10 to 50 times brighter than the rest of the stream. Could the reason for this bright glow be due to the same explosion after which the Fermi bubbles formed? After all, the bright part of the stream lies below the galactic center. Based on data obtained for other galaxies with supermassive black holes that are active and sparkling jets, Blount, Fawn and colleagues concluded if Sagittarius A was also active, its ultraviolet emission could indeed both analyze and therefore brighten part of the Graves stream. If such a huge flare were to occur, Its echo would be a bright spot the size of the moon in the southern sky. In winter, the man skillful Komuka, or the man directly entering someone with, could have already witnessed this flare directly. A fast star, the white-blue star C2, is one of the fastest known stars with a very high luminosity. It's in close proximity to the galaxy's central black hole. It orbits around Sagittarius A at speeds of up to 5,000 kilometers per second, which is almost 2% of the speed of light. Where would it come from? At such a close distance, the black hole's gravitational field should have torn the clouds of gas to shreds, even before they could concentrate into new stars. The hypothesis that the star could have been born in more favorable conditions and then drifted toward the center of the galaxy is contradicted by its age. The bright star 2 is no more than 10 million years old, and it is unlikely that it could have undertaken long journeys in such a short time. Interview: How will I photograph a black hole at the movies? Volker Radio, an astronomer at Radboud University in the Netherlands who is a particle astrophysicist, talks about his plans to use a global network of radio telescopes to take pictures of the black hole at the center of the Milky Way. An ANTIIDS news correspondent interviewed him in 2015. Why do you need to photograph a black hole? Black holes were predicted 100 years ago. But my feeling is that time goes on and we understand them less and less. We still don't have conclusive evidence for the existence of an event horizon from which nothing can escape. Furthermore, the existence of an event horizon cannot be explained in quantum theory. Something in the theory will have to change, and it's not clear what it is. How do we even know there's a black hole in the core of the Milky Way? Stars orbit around the center of the galaxy at about 10,000 kilometers per second. That means there must be an object at the center with a mass more than 4 million times that of our Sun. The only thing we see at the very center is the source of very short submillimeter radio wave Sagittarius A. How does a giant network of radio telescopes help you? The black hole's event horizon has a diameter of about 25 million kilometers, but it is 270,000 light-years away from us. You need a telescope the size of the Earth to image it at millimeter wavelengths. A worldwide network of radio telescopes can provide the necessary resolution. Aren't American astronomers working on a similar idea? I first discussed the idea 10 years ago with House Chief Young at MIT. Doyle Mann is now leading the U.S. Event Horizon Telescope project. It doesn't make much sense to use only a small set of available telescopes. They need us, not us. What exactly are you looking for? We are hoping to see radio waves from the neighborhood of a black hole being bent and absorbed, like in Christopher Nolan's movie Interstellar. As a result, we hope to see a kind of central shadow. By comparing the size, shape, and sharpness of this shadow with theoretical predictions, we can test the general theory of relativity. Let's say the shadow turns out to be half the size, or conversely, twice as big as predicted. Then the general theory of relativity is wrong. What were the biggest difficulties along the way? There were very serious technical difficulties, but we overcame them. Each telescope has to record many hours of observations at 64 gigabits per second, and then exchange this information between continents. Finance. The hurdles have been overcome with grants from the European Research Council and the U.S. National Science Foundation. When can we see the first portrait of a black hole? In 2000, I said that the first result could be obtained within 10 years. Now I see that we should temper our expectations a bit. Maybe we'll have to wait another 10 years? I hope not. but eventually it will take some time. Note: astrophysicists presented the first photos of a black hole in April 2019. Boson star. Excitingly misleading and all-around terrifying. Such epithets can characterize black holes, spreading around them the hateful monster of the universe. The existence of these insatiable cosmic cannibals was predicted by Einstein's general theory of relativity. It is currently the best theory of gravity we have. Soon we will have the first direct image of the black hole at the center of the Milky Way. But what if it's not there? Scientists obsessed with black holes may be overlooking an even stranger phenomenon that belongs to particle physics and whose significance we cannot yet appreciate. Although this is still a purely speculative idea, there are good reasons to consider it. We don't know what happens inside black holes. These are places where the scope of the general theory of relativity, which deals with very large quantities, collides with quantum theory, which is responsible for the very small quantities in black holes. These two theories do not get along well with each other. Relativity theory assumes that any object falling inside a black hole will be crushed by its gravitational field and become a singularity of zero volume and infinite density. But this renders any equation meaningless. Meanwhile, detailed theoretical calculations show that black holes either have to annihilate all information phenomena absolutely impossible from the point of view of quantum mechanics, or surround themselves with a wall of energy. In Russian language literature, this phenomenon is often called a fireball, and this assumption violates the principle of the general theory of relativity. Convincing evidence for the existence of black holes came in 2016, when scientists announced the first detection of gravitationally different waves. The Liege and Verve experiments, the Laser and Interferon Metric Gravitational Wave Observatory, and the Gravitational Wave Detector detected signals that exactly matched the theory's predictions for the collision and merger of two stellar mass black holes. So the inquiry is closed. There's no need to rush, says Luciano Soler of the Frankfurt-based Institute for Advanced Study in Germany. These signals may not come from black holes, but from a stellar boson. So far, however, these objects exist only in the minds of theorists. For the most part, matter consists of the basic elementary particles fermions. Their characteristic feature is that they obey the principle of Pauli's prohibition, which states that particles cannot occupy the same quantum energy state. The Pauli principle is responsible for the basic parameters of the material world. It determines how electrons are arranged in different energy states around the atomic nucleus and therefore determines the properties of the various chemical elements. A very different matter is owed. Perhaps the most famous example is the Higgs boson, discovered in 2012 thanks to the Higgs boson. Particles of matter have mass. There are other bosons that are responsible for the interactions between particles. You can't say that bosons are something exotic. We see them around us all the time. Photons are the bosons that carry the electromagnetic interaction. The main thing to understand about bosons is that they can accumulate in one place, virtually unlimited. They are essentially one collective particle, a special state of matter known as an Einstein-Bose condensate. Physicists can create an Einstein-Bose condensate in the lab. There is nothing preventing a boson with special properties from forming a fairly large object, perhaps a very large one. Some physicists believe that even stars can form Bose-Einstein condensates, although their properties will be different from those of ordinary stars, which we know when a star is formed from ordinary matter, it is compressed by gravitational pressure and heated to such an extent that it starts fusion reactions. This releases energy, including light radiation. unlike ordinary stars. In the star zone, it's just a cosmic slacker or a god who has taken the shape of a donut. This is the shape, according to calculations, that stars should take under the action of centrifugal forces if they rotate like an ordinary star. These celestial donuts should be transparent, does not emit its own light, they should be invisible. And the main indication of their presence would be strong gravity. That reminds us of something, doesn't it? The idea of battalion stars is not new, but astrophysicists brushed it off because no one could imagine what sort of boson could be used to create such stars. Particles like photons, which transmit fundamental interactions, are not suitable for this. The discovery of the Higgs boson revived interest in bosons in general. A prime candidate for boson and star formation is axiomatic. An ultralight hypothetical particle from the Aksanovs could also consist of dark matter, the mysterious glue that astronomers believe holds galaxies together. How can we get evidence for the existence of obligate stars? Gravitational waves can help us with this if the merger of two objects produces a black hole. The time-space tremor that propagates from the merger site in the form of gravitational waves will be of a different character than that of the formation of a star zone. An improved design, or one with greater precision, would probably sense the difference in the frequencies of the gravitational waves being studied. The Event Horizon Telescope may clarify the situation somewhat sooner, although there are differing opinions as to whether it will be easy to see the difference in the images of the black hole and the star zone. According to calculations by Frédéric Vincent of the Paris Observatory in France, the gravity of the compact zone of the star will unbind the light around it, creating an empty region that can be mistaken for the shadow of the black hole's event horizon. Believes that such a conclusion is overly pessimistic. Like a black hole must, the star will absorb matter from its neighborhood. But the transparency of the star's zone means that this matter in its center we will be able to see. In addition, this matter can heat up and start emitting light or some other form of electromagnetic radiation. The hypothesis of the existence of black holes has to some extent become a brake on the development of a comprehensive theory of nature, because black holes are the embodiment of the conflict between general relativity and quantum mechanics. If it could be proved that black holes don't exist, perhaps it would be a breakthrough in theoretical physics. So, what is dark matter? Obviously, dark matter is not just invisible matter, consisting of ordinary protons and neutrons, electrons hidden from us by a dark veil. If the universe originally contained much more ordinary matter, then, a few minutes after the Big Bang, more helium than the amount we see today would have been formed from all the protons and neutrons that were still tightly packed together, as a result of a thermonuclear fusion reaction. Dark matter must represent something else. It is generally assumed that dark matter is composed of exotic particles that interact weakly with other particles and do not impede the passage of light. The standard model of particle physics cannot offer anything suitable to explain this phenomenon, so one has to resort to all sorts of tricks. For a long time have long favored particles and the so-called weakly interacting massive particles, as well as much lighter axions. Dark matter in general may not exist in the form of particles, but in the form of primary black holes formed in the early stages of the life of the universe. Chapter 9. What's out there beyond our galaxy? Our galaxy, called the Milky Way, is just one of many 1 trillion galaxies. Some are quite small and contain only a few 1 trillion stars. Others are elliptical galaxies of enormous size. The collisions of some of them resemble the slow-motion power of a grand cosmic dance, the hustle and bustle of others that crowd into the dense layers of a cluster of galaxies. None can be explained without dark matter, and almost every one contains a supermassive black hole. things are provincial. Our local cluster of galaxies resembles cosmic galaxies. The scenery's been done. You could say it's a village in the universe. In our vicinity, within a few 1 billion light-years, there are only 3 spiral galaxies: Milky Way, Andromeda Nebula, and a small triangle spiral galaxy, plus dozens of dwarf galaxies. According to recent studies of the galaxy, local groups may have exchanged matter with each other that was given off from them by galactic winds from supernova explosions. Recent modeling estimates suggest that the galactic winds could transfer from a large galaxy about 50% of the matter that currently exists in the galaxy. At distances of up to 1 million light-years, large galaxies tend to take matter from their smaller neighbors. For example, our galaxy takes matter from its neighboring Magellanic New Clouds. Our body may be half made up of galactic atoms once captured by the Milky Way. To get from our space village to the nearest city would take us 60 million light-years. The Virgo cluster is made up of more than 1,000 galaxies. As in other large clusters, the galaxies in the Virgo cluster are splashing around in resolved superhot gas at temperatures of about 30 million degrees Celsius. Among them is the giant elliptical galaxy M87, 100 times the mass of the Milky Way. The difference between elliptical and spiral galaxies is that in spiral galaxies there is a significant supply of cold gas, which when condensed can form bright new stars. In optical galaxies, however, new stars are practically not born in clusters of Virgo-type galaxies, which can be considered the largest objects in the universe. The question, however, is what exactly should be understood by the term object. In principle, we can identify much larger structures, called superclusters of them, and Walters from the English what void. These are just patterns in the sky, slowly stretching the existing ones as the universe expands. In contrast, clusters of galaxies have quite definite and independent distinguishing features. They're bound together by a gravitational field. That is, their constituent galaxies orbit within the clusters and, as a unit, together oppose the expansion of the universe. In 1933, Fritz Zwicky studied the motion of galaxies in a cluster located in the constellation Veronica's Hare. It's a cluster of galaxies located 300 million light-years from Earth. It turns out that the galaxies in this cluster are spinning too fast. At these speeds, the gravitational field of visible matter is clearly not enough to keep them in the cluster. Zwicky suggested that there was additional matter that we, for whatever reason, don't notice. A few decades later, this idea was reinforced by the observations of Vera Rubin, who noticed that the outer parts of spiral galaxies rotate too fast. It is possible that the presence of dark matter once helped galaxies to form. The gravitational field of dark matter attracted the gas needed for this. Different galaxies contain varying amounts of dark matter, but in general the total mass of each galaxy is several times the total mass of its stars. The record holder in terms of hidden matter content is the Andromeda Galaxy 441. Its mass is about the same as that of the Milky Way, but it contains extremely few stars and is thought to be almost entirely 1 meter and 90.09% composed of dark matter. How do such mysterious dark galaxies arise? This is a mystery astronomers have yet to solve. A kamikaze galaxy. Don't mess with them, Lechin Way. One faint galaxy from the constellation Hercules learned this lesson well from its own bitter experience. As soon as it dived into our galaxy, the gravitational field of the Milky Way tore it apart. The dwarf galaxy in the constellation Hercules is now 460,000 light-years away from Earth. That is almost 3 times farther away than the Milky Way's brightest companion galaxy. The Large Magellan. Its cloud. The stars of this dwarf galaxy are scattered far apart. The Milky Way's gravitational field drags them in different directions. Andreevsky Cooper and Katherine Johnston and colleagues at Columbia University, New York City, USA calculated the path of the dwarf galaxy in Hercules through the Milky Way. Knowing the observed position and velocities of individual stars, they got that the most distant object that belonged to the dwarf galaxy is now 600,000 light-years away from the center of the Milky Way. And the closest ones are only 16,000 light-years away. That's closer than any other galaxy. A satellite could come to the center. It's even closer than from us to the center of our galaxy. The convergence of the Hercules galaxy with the Milky Way 500 billion years ago proved fatal to the dwarf galaxy. Matter from our galaxy flooded its vastness. The gravitational pull of this new matter entering the dwarf galaxy began to draw stars and dark matter more strongly to its center. Then, as the dwarf galaxy circled the center of the Milky Way, the stars and dark matter flew away again, and the galaxy assumed its present highly elongated shape. Today, the stars that once belonged to the dwarf galaxy in the constellation Hercules belong more to the Milky Way than to this dwarf galaxy. They are so widely scattered in different directions that they barely feel each other's gravity. And yet the stars keep moving along the same trajectories, like parachutists jumping out of the same airplane. Johnston predicts that the next time a galaxy ventures closer to us, it will be seen as a stream of stars bringing everyone past at a very high speed. Metamorphosis. In 2014, the Hubble Space Telescope detected several spiral galaxies rushing towards a cluster of galaxies in the process of this rapid motion. They are literally tearing apart, becoming shapeless space jellyfish-like amorphous bodies and glowing tentacled stars. Hubble telescope observations have more than doubled the number of known amorphous jellyfish-similar galaxies and should contribute to a clearer understanding of galaxy transformation. We know that galaxy clusters contain many more elliptical galaxies than spiral galaxies. Perhaps this indicates that new spiral galaxies adjacent to clusters are somehow transforming into elliptical galaxies. Harold Abel of the University of Hawaii. City of Honolulu, Hawaii, and the United States believe that the Medusa galaxies reflect this transformation process. The space between galaxies in a cluster is permeated by gas with very high temperatures, so an alien galaxy cannot quietly and stealthily enter a hot gas cluster. The cluster collides with the cold gas of the newly arrived galaxies and calls it away. A long plume of streams of cold gas will stretch behind it. This tentacled gas, stretching behind the amorphous body of the galaxy, shrinks and ignites new stars. Billing and colleagues discovered their first celestial jellyfish in late 2005. Since then, they have been on the hunt for more extreme examples of such galaxies. Looking through hundreds of Hubble telescope images through 2014 managed to find only a few examples of such a transformation in relatively close-lying galaxy clusters. Perhaps because the change happens too quickly, and once a spiral galaxy is stripped of its cold gas, no more drastic metamorphosis happens to it. Perhaps a detailed study of amorphous jellyfish-like galaxies will help explain another puzzling feature of galaxy clusters. Why do they contain relatively young orphan stars that do not belong to any particular galaxy? The gas inside clusters is too hot to collapse into new stars, so they are likely to appear from outside. Probably another finger of Medusa at the spider in the web. Dwarf galaxies, like cosmic spiders, make a feast for themselves by attracting their tenants. Only they feed not on flies, but on clots of gas hung here and there in a hidden web. Something similar happened at the dawn of the universe, when stars were born and galaxies grew. The idea that galaxies grow and are fueled by matter due to clouds of cold gas from giant cosmic webs has been around for a long time. Lately, this idea has become particularly popular and has received additional confirmation thanks to modeling calculations. Modeling has shown that it is where the gas clouds get into the gravitational vice of the galaxy as a burst of star formation begins. However, it is difficult to observe this process. The Milky Way and most of the galaxies we see nearby are filled with hot gas, which heats up, trapping matter, preventing it from forming into stars. And because clumps of cold gas in optical space themselves emit very little light, it's hard to notice them. In 2015, a research team led by Jorge Sanchez Almeida of the Canadian University of Astrophysics, Tenerife Island, Canary Islands began studying small faint galaxies with low levels of heavy elements heavier than hydrogen and helium. The scientists investigated changes in oxygen levels in the disks of these galaxies. They found that bright star-forming regions contained about 10 times less oxygen than others. The picture is that the newly arrived gas activates the processes of star formation. And this gas has to appear in galaxies. It's relatively recent. Indeed, if the gas were old, it would have lost its distinctive chemical features, mixed for a few 101 million years into a homogeneous mess. How do we explain where young gas comes from? Perhaps clots of gas flowing through the cosmic web could explain its appearance in galaxies. A new process of activity in them and the very existence of these galaxies. Cosmic gas pedals. The first hints of the existence of dark matter came from the study of galaxy clusters. Today, astronomers are scrutinizing galaxy cluster collisions to find out the nature of this dark matter. Dark matter is thought to make up about 83% of all matter in the universe, but it apparently only interacts with ordinary matter through gravity. Astronomers have tried to abandon the concept of dark matter by changing the laws of gravitational interaction. But the observation of collisions of clusters of two galaxies, one of which is called a bullet and is located at a distance of 3.7 billion light-years from these attempts, left no stone unturned. The fact is that usually dark matter and normal matter are too well mixed, and it is not possible to separate one from the other. But at the collision of exactly these two clusters, the galaxies entering them slipped past each other, leaving behind them a tail of hot interaction-going gas. Dark matter, whose presence is indirectly confirmed by gravitational interaction, stayed with the galaxies. And this suggests that dark matter should be treated as matter, not as an addition to the law of gravity. And that dark matter particles don't bounce off each other like ordinary atoms and molecules. Studies of other galactic catastrophes first led astronomers to believe that objects or something made of dark matter could interact with objects like themselves by means of a special agent, a force acting only on dark matter. But in 2015, additional data came to light that says otherwise. The Chandra X-ray Observatory observed 30 new galaxy cluster collisions. It turned out that when galaxies collide, the dark matter continues on its way unimpeded as if unaffected by any other dark matter, no matter how much of it is around. Which means it doesn't interact with its own kind. But that still doesn't rule it out. It's hard to pick up new forces. Perhaps by analyzing 1,000 other colliding galaxy clusters, astronomers will finally understand the nature of dark matter. Bright black. Floating in the void of space is a huge cloud of cold gas, a clumsy black patchwork against an even blacker murky background. Then, as if out of nowhere, a thin jet of matter rushes towards it. The jet crashes into the cloud, compressing its constituent matter in the process, and causes a flurry of star formation that looks like a firestorm. The gas cloud ceases to be dormant, it becomes a real galaxy. Maybe this is how a galaxy is born, under the action of emissions from supermassive black holes. The mystery of black holes and their relationship to galaxies has preoccupied astronomers since the mid-60s of the 20th century, ever since quasars were discovered. The size of these objects is small, they could fit within the solar system, and their luminosity is enormous. Their energy, released in the form of light and other forms of radiation, can be 100 times the total luminosity of the Milky Way. Such a colossal energy output from an object that is tiny by cosmic standards can be produced by a black hole with a mass 1 billion or even 1 trillion times that of the Sun. If it absorbs gas and dust from the surrounding space, the matter collects in a disk around the black hole and heats up and releases bright radiation in intensity exceeding other known sources. In addition to quasars, other types of active galactic nuclei are known, such as radio galaxies and northern galaxies. They do not shine as brightly, but are also characterized by a fairly high luminosity. Apparently, they are also the result of active black hole energization. Astronomers used to think that supermassive black holes are only found in these rather rare active galaxies. That is, they are certainly interesting, but hardly of great importance to the entire vast cosmos. However, this view had to be revised when it became clear that most galaxies, if not all, contain supermassive black holes. The fact that we don't notice them is due to a lack of fuel. That's why in most galaxies, ours included, black holes are dormant. They simply have nothing to digest. There is a clear connection between these objects and their parent galaxies. Spiral galaxies have a central thickening, called a beam, made up of the oldest stars. Such a beam is usually about 1,000 times more massive than a black hole, coming here in its core. The same estimates hold true for elliptical galaxies, which are essentially just beams. The mass of a black hole is in direct proportion to its mass. Further evidence that there is a connection between the two, the peak of star formation and quasar activity occurred at roughly the same time from 8 to 10 billion years ago. Even if the black hole is supermassive, it is still much lighter than the rest of the galaxy. Therefore, the hole can't have much effect on it. Perhaps a large one forms first, and then the black hole grows to a detectable size. However, the black hole may gain extra weight. Some theorists believe that the ball and black holes grow in synchrony, and when the black hole eventually becomes large enough, wind and radiation and its descending disk knock out the extra gas, setting a limit on the size of the ball. But events can also unfold in a different, more radical scenario. In many active galaxies, black holes eject into matter in the form of two oppositely directed atypical jets. These jets can travel at close to the speed of light and then burst out of their galaxy and take a voyage 1 billion light-years deep into galactic space. In 2009, a team led by David L. Bazam of the French Atomic Energy Commission France reported the results of a study of the unusual quasar H-0 for 50B 2958 jet, located 5 billion light-years away. H-0 for 502958 is called a naked quasar, and it is the only quasar of its kind. It represents a single supermassive black hole with no surrounding galaxy. Using infrared equipment on the Very Large Telescope, abbreviated BT, in Chile, scientists have made a startling discovery. Jets fired by the quasar-like laser beams pierced space and fought their way into a young galaxy 23,000 light-years distant from the quasar. This galaxy is undergoing an intense process of star formation. The rate of bright stars appearing in it is equivalent to F35 with the Sun per year, which is 100 times what would be expected for galaxies in this region. Scientists have suggested that the jet from the quasar was the cause of the new galaxy. Meanwhile, the object itself, HN0 for 50b 2958, was initially a supermassive black hole that pulled gas from galactic space. Until it became a quasar, the mass of the quasar continued to grow, and then there was a critical moment in its life when directional jets of matter, called jets, appeared from two opposite sides. This happened about 200 million years ago. One of the jets met gas clouds in its path. Shock waves arose, which began to propagate through the gas and caused star formation. And so a new galaxy was born. This is a radical departure from the standard theory of galaxy formation, which holds that galaxies appeared first and supermassive black holes formed in them later. Scientists realized that their idea would cause a storm of controversy, so they began to look for another explanation for the connection between quasars and galaxies. At first they assumed that some force simply pushed the quasar HN0 for 5028 out of the galaxy. Modeling the process of merging two galaxies into one indicated that their central black holes can ricochet away from each other, and one even flew into galactic space. However, it is then a strange coincidence that quasar was ejected in the same direction as one of its jets. Furthermore, there is no evidence that there has been a galaxy merger here in the last few 101 million years. And to escape from a galaxy as large as the one in question, which is about the mass of our Milky Way, the quasar would have to be pushed with such force that it would develop a velocity of 500 kilometers per second. But it's moving much slower than that. At such a slow speed, the quasar would eventually fall into the galaxy, which it apparently created to take its rightful place at the center of the galaxy. Some quasars are observed slightly away from cold gas clouds composed of carbon monoxide. We may be seeing a stage prior to star formation in these quasars. Indirectly, this confirms the hypothesis of Baz that even before the formation of galaxies in the cosmos was the era of supermassive explicit black holes. Their mass was growing, they became the ruler of the universe, and then galaxies originated from them. And if that's true, where did the black holes themselves come from? Observations of quasars suggest that giant black holes with masses of 10 billion solar masses formed within 1 trillion years after the Big Bang. For years, astrophysicists have puzzled over how they were able to grow into such giants so quickly. One growth scenario envisioned that they grew from small stellar mass black holes formed when stars collapse at the end of their evolution in a superdense star cluster. Some of these black holes may have merged to create one huge hole that continued to grow, feeding on itself. But critics of this idea rightly point out that during the first 1 trillion years after the Big Bang and the merger of stellar mass black holes, the black hole simply would not have had enough time to grow into something big enough. An alternative hypothesis for the formation of supermassive stars. If such a star were ever to form, it would not be able to survive long. The heat-generating thermonuclear reactions in its core would not be enough to resist the gravitational forces trying to crush it. Such an object would inevitably and immediately tell, leading to the formation of a black hole. Mitchell Gelman of the University of Colorado at Boulder, USA, has studied this picture in detail. According to his calculations, the grain of a supermassive black hole can form inside a supermassive star. Then the outer layers of this bizarre star explode and expose the black hole hidden inside. To prove or disprove this idea, we'll have to wait for the next generation of telescopes to arrive. The green classes are attacking. Imagine you are on a night hike in a remote desert to spend the night away from any sign of civilization. You reach the top of a hill and are suddenly surprised to find the building in front of you flooded with artificial light. Your amazement will be partly reminiscent of the bewilderment with which the discovery of the so-called Hani object was greeted. This curious gas cloud was discovered in 2007, brighter than 30,000 suns. It was simply floating in space with no visible source of illumination. So far, 19 similar clouds have already been discovered, and they all glow, apparently without an internal energy source. Probably, the cloud owes its energy supply to the intense radiation from huge nearby black holes. This connection between clouds and huge black holes is interesting because we can now use clouds to study how matter grows and is absorbed by these unfathomable behemoths. Hana was discovered by a school teacher involved in the Hubble Galaxy Zoo project on classifying different types of galaxies. Everyone can participate in this internet project. While examining images in artificial colors, Hana van Ark, a volunteer for the project, noticed a strange blot-like spot that appeared to her to be too blue. She reported it by email to the researcher who founded the project. The researchers included in the telescope's work plan a new observation of the object. Glow object observed lines of ionizing oxygen, whose atoms are stripped of some of their electrons, studying the green region of the spectrum. Other elements were also initiated. It required a tremendous amount of energy to ionize all this gas, but there was no hint of an energy source. The study of hot young stars could still explain the presence of initiated oxygen in the cloud, but in no way the initiated neon radiation, neon ultraviolet observed in the cloud could not occur unless excited by large amounts of X-rays. All of this suggested that a monstrous black hole was involved. Most galaxies are believed to contain black holes in their cores. In many cases, black holes produce powerful X-rays when matter collapses onto them. At a distance of about 45,70,000 light-years from the glowing cloud is a galaxy called Alice 2497, and a black hole in its nucleus could well send a stream of X-rays to the Hani object. But there is one catch: the nucleus of the galaxy Alice 27 does not show any signs of X-rays. In 2008, the Hubble Galaxy Zoo project staff put forward the following explanation. The black hole in the Alice 2497 galaxy was once very active in absorbing matter and emitting streams of X-rays. Less than 100,000 years later, the galaxy has taken its present form. It took time for the X-rays to reach the cloud. Some of them still arrived and made the cloud glow. That light is what Hani van Ark saw. Although the black hole was no longer manifesting itself in any way by then, the observations of this object when it was discovered were unique. They showed how much the activity of black holes can vary over tens of 1,000 years. The task of scientists to understand what this activity depends on, because the flares that come as a result of increasing the rate of the black hole have a huge impact on the environment. Such events can stop galaxies from growing, heating up the gas that goes into forming new stars and pushing it out of galaxies. While the Hani object was the only one of its kind, it was unclear how characteristic this behavior is of black holes. Time has passed. Professional astronomers and volunteers from the Hubble Galaxy Zoo project working in the same harness. Since then, many similar objects, like Hani's object, have been discovered. They were luminous gas clouds near galaxies, the black holes in which are now inactive, but probably initiated the glowing clouds. In the past, most of the clouds detected are in the neighborhood of galaxies that interact with or merge with other galaxies. This pattern is consistent with the scenario of episodic black hole activity described earlier. Indeed, collisions of galaxies with each other communicate momentum to gas clouds and can push them out into galactic space. This is how objects arise that can subsequently be exposed to X-ray irradiation from black holes. All this shows that the Hany object is not a trick of the eye. Throughout the universe, black holes behave like flashing beacons, give onboard salvos at neighboring objects, and then quiet down and disappear from view. The cosmic web. As astronomers have more and more sensitive telescopes at their disposal, an ever finer structure begins to appear before the eye. Village. It turns out that galaxies and clusters of galaxies, huge as they are themselves components of even larger strings and nodes of superclusters. Sometimes these superclusters, in turn, can combine to form objects called walls. At the largest scales, the universe resembles a cosmic web of matter surrounding relatively empty expanses of water. Such a web can also be compared to silk lava. It is a spider's web. The structure is consistent with computer models that take as their starting point a nearly smooth universe where dark matter dominates gas. Of ordinary matter made up of neutrons, protons, and electrons in a ratio of about 5:1. Mapping voids may give us a new way to explore dark energy, some substance with repulsive properties that gives these voids a visible form. So far, everything seems to be going well. But as new observations are able to penetrate ever deeper into space, astronomers are beginning to identify structures of increasingly unprecedented size. First, we learned of the existence of the Great Wall as if, and in 2014, we discovered that the Milky Way belongs on top of a cluster of galaxies called the Lunacy. The size of both of these structures is enormous. Then, in 2016, astronomers discerned the outline of the Great Galactic Wall. WHO is about 5 billion light-years away. Note BOSS, abbreviation for the English word spectroscopy. Review. Brennan. Associations is one of the Sloan Digital Sky Survey projects with which the Great Wall of China was discovered. The mass of this superstructure is 10,000 times the mass of the Milky Way. It is 2/3 the size of the wall, like or unlike the Great Wall. The BOSS includes 830 galaxies that we observe, and probably many more galaxies that are so distant and faint that they simply can't be seen in a telescope. Which galaxy is the largest? According to the standard model of galaxy formation, the largest galaxies are elliptical, formed by the collision of many smaller galaxies. The largest known galaxy of this type is the lens visible galaxy Alice 1101. It is at the center of a cluster of galaxies called Abell 2020. It is 1 quadrillion light-years away from us. It is nearly 6 million light-years across, which means it is 1,000 times the volume of the Milky Way. Since Copernicus, these growing walls of emptiness and the indication of the existence of a giant structure in the universe have caused astronomers much trouble. In his time, Copernicus put forward the revolutionary idea that the Earth's location among the stars was not unique, and this idea has been considered fundamental in astronomy ever since. On its basis was formulated cosmological principle: nowhere in the universe there is nothing special. That is, the universe is homogeneous and out of tropes. Of course, at the level of solar and other star systems, galaxies and clusters of galaxies, individual differences exist, but it is worth to remove a sufficiently large distance, and the universe should be homogeneous. No huge hyperclusters or voids larger than 1 quadrillion light-years astronomers did not expect to find. The assumption of a smooth universe made it much easier to apply Einstein's general theory of relativity to the entire universe. In general, and that in the West with a team of scientists from the University of Hawaii at Mono in 2015 discovered a giant hole void 2 billion light-years in size in the universe. Such a discovery clearly contradicted the notion of a homogeneous universe. Scientists called this vast empty space superspecies and suggested that the mysterious cold spot of relic radiation has puzzled astronomers for more than 10 years can be explained by the presence of this superspecies. But it turned out to be more than that. Back in 2012, a group of specialists led by Roger Klaus from the University of Central Lancashire, UK, reported that in the universe there is a huge structure stretched over 4 billion light-years. It was more than twice the size of a supervolt, and that in the West alone it was not empty space, but instead densely populated. It contains 73 quasars and is known as the Huge Group of Quasars. Recall that quasars are the bright, active central regions of very distant galaxies. That quasars tend to cluster together has been known to astronomers since the early 80s of the 20th century, but it was not previously known that they could cluster in such large numbers. Then, in 2015, a group of Hungarian astronomers discovered a colossal group of gamma-ray bursts. These bursts came from galaxies forming a ring 5.6 billion light-years in diameter, which is 6% of the size of the entire visible universe. Aliens from another dimension. Some scientists question the monolithic nature of this ring of bursts and a group of quasars, but a number of experts believe that these cosmic megastructures indicate a fundamentally new concept of the structure of the universe. That's the view, for example, of Raina Dick, a theoretical physicist at the University of Saskatchewan, Canada. He's made a stunningly bold assumption. These megastructures are direct evidence of an invasion of our own dimension. Others leaving dirty footprints on our smooth and homogeneous cosmic background. For several decades, many theorists have viewed the existence of extra dimensions as a good chance to reconcile Einstein's general theory of relativity with another bastion of 20th century physics, quantum theory. The union between these two concepts, which seem fundamentally different, one deals with very large objects and the other with very small ones, would give what is often referred to as a theory of everything and allow for a unified approach to describe the universe in its entirety. One such unifying theory would be the theory of, based on string theory. According to this theory, we live in an 11-dimensional universe, the 7 dimensions of which we do not experience because they are back in a very tight ball and have disappeared from our sight. It is an elegant and mathematically appealing structure that has influential proponents. But it lacks one important property. It cannot predict specific phenomena against which it can be tested. Dick's work on generalizing string theory brane theory could provide such predictions. At the heart of brane theory is the idea that the universe we perceive is a 3-dimensional membrane floating in a sea of similar brands spanning many additional dimensions. And, according to Dick's calculations, neighboring country effects lapping in from ours can distort the distance measurement using redshift, creating vast mirages of super-wars and other megastructures. Redshift, blue shift. The effect of cosmological redshift is at the heart of measuring the distance to distant objects in the universe. Light from a distant object takes a long time to travel through expanding space, which stretches it to longer, redder wavelengths. Astronomers study the light from the object with a spectrometer to identify the spectral lines characteristic of the object. The farther away an object is from us, the faster it will appear to us to be moving away, and the greater the shift of its lines will be numerically. Redshift is the difference in wavelengths divided by the original wavelength. Thus, if the redshift of an object is equal to 1, the apparent wavelength of radiation from that object is twice the original wavelength, and a very distant object with a redshift equal to 9. The wavelength has increased by a factor of 10. Redshift is observed either in a strong gravitational field or when an object is moving away from us. In the latter case, this effect is called upshifting. This effect can manifest itself in other ways as well. An object heading in our direction, such as the Andromeda Nebula, may appear blurry. Flares and collisions. Everywhere in space, we see the flashes that accompany the death of giants and the collision of dark stars. These flashes illuminate the brightest, most distant, and most interesting to us events of cosmic life. The darkness is lifting. Some mysterious force is pushing the universe apart. What that force is, we do not know. It is present everywhere, but we cannot see it. It makes up more than 2/3 of all the energy in the universe. But we have no idea where it comes from, what it's made of. At least we have a spectacular name for this substance: dark energy. Until 10 years ago, we believed that the expansion of the universe was slowing down. But in 1998, astronomers were extremely surprised when they analyzed the brightness of distant L1 type supernovae, and since the luminosity of all supernovae of this type is about the same, such supernovae can be used as standard candles. The fainter its flash looks, the farther away it is. Because of the low luminosity of many supernovae flares, they have been thought to be farther away than one might think. It's as if at some point space starts to expand faster, as if it's being pushed apart by an unknown force. A counterforce, the pull of matter. One thing we can say for sure is that dark energy is great food for the minds of theoretical physicists. They give it hundreds of different forms and fantastic meanings. The simplest and most innocuous form of dark energy is the cosmological constant. And even it looks fanciful. The cosmological constant is interpreted as the energy density of the vacuum inherent in space itself, which within Einstein's general theory of relativity creates repulsive gravity. This energy density increases as space expands and compared to the weakening gravitational attraction of increasingly scattered matter, the repulsion becomes stronger. To explain the existing acceleration of the universe, the cosmological constant must have a value on the order of 1 Julio per cubic kilometer of space in the total mass of energy of the observable universe. Dark energy occupies 2/3, and only 1/3 is accounted for by dark matter and normal matter. Particle physics explains the presence of intrinsic energy in empty bubble space than all unpredictable quantum vacuum. Virtual particles appear and disappear all the time. The problem is that, according to the theory, these particles should have too high an energy density of 10⁻120 joules per cubic kilometer. This catastrophic inconsistency has prompted physicists-theorists to create a whole slew of alternative theories. For example, proposed such a variant dark energy may be a kind of ether, a special entity resembling outer space. This hypothetical medium is akin to an energy field, permeating all space. It may change over time and perhaps even condense in certain places. Another hypothesis: dark energy is a modified form of gravity, which at great distances begins to repel rather than attract objects. There are many quite clever hypotheses, such as that the presence of dark energy indicates a loss of quantum information or the presence of radio waves with lengths 1000, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000 times longer than those observed in the village. It would be very interesting to find out if dark energy changes with time. If so, then at least the cosmological constant can be put out of brackets. In most models that treat dark energy as a kind of ether, the energy slowly dissipates as space expands. Although there are some models where it is amplified and plugged in by the expansion of the universe. In most modified theories of gravity, the density of dark energy also changes. It may even increase for a while and then go down, or vice versa. The fate of the universe hangs in the balance. If dark energy remains constant, the predominant part of outer space will continue to fly off in all directions, and we will remain in a small island universe, forever cut off from the rest of the cosmos. If the dark energy intensifies, however, it will eventually tear all matter to shreds or even make the fabric of space unstable in the here and now. The most accurate estimate to date is based mostly on observations of supernovae and says that the density of dark energy is fairly constant. There is a suggestion that it is increasing slightly, but the uncertainty in these estimates is too great, and there is no reason to worry about this increase yet. Astronomers are currently working hard to more accurately establish the behavior of dark energy. There are a number of projects, such as the Dark Energy Survey, dedicated to finding eloquent evidence for the existence of dark energy in broad segments. On it, these projects observe many new supernovae and determine the position of 1 billion galaxies. To detect sound waves left over from the Big Bang and count the number of galaxy clusters formed at different stages of cosmic evolution. All of these processes are influenced by dark energy in various ways. An even more impressive hunt for dark energy is set to begin in a few years, both through special space missions like the Euclid Space Telescope and through the new generation of giant ground-based telescopes, the Large Optical Survey Telescope 30-meter telescope, the European Extremely Large Telescope, and the Giant Magellan Telescope. Few expect the hunt for dark matter to succeed in the near future. Scientists have been speculating about the nature of dark matter for 20 years, and so far to no avail. But on the other hand, we have a key to the door behind which may lie the clues. Interview. We've solved a cosmic mystery. Adam Rees was the engine and Brian Schmidt. They won the 2011 Nobel Prize in Physics for their discovery of the accelerated expansion of the universe. Rees currently works at Johns Hopkins University and the Institute for Space Research. Using the Space Telescope City of Baltimore, Maryland, USA, a reporter from News Magazine interviewed Rees in 2011 after he was awarded the Nobel Prize. Our congratulations. Where were you when you got the news? Thank you. I was at home. It happened at 5:30. I was trying to sleep. My son is 10 months old and he doesn't sleep well at night. When the bell rang, I was hoping he'd fall asleep so I could finally get some sleep. True light performance. What exactly did you and First Morning and Schmidt discover? Independently of each other, we observed near and far supernovae to estimate the rate of expansion of the universe at various points in its evolution. We were able to establish that the expansion of the universe, contrary to expectations, is accelerating rather than slowing down. Were you working at the University of California at Berkeley at this time? Pearl and his group were also at Berkeley. Was there competition between the two of you as well? Yes, there was competition between our groups. We both knew that we were collecting data on the same objects and that no one had ever done a scientific search of this kind before. Neither of us wanted to come in second, much less be on the fringes of research. From time to time I met with these guys. We even chatted a bit. Saul was kind enough to arrange for me to be assigned a parking space at Lawrence National Laboratory in Berkeley, where he still works. To get to work, I used to walk down the hill to the UC Berkeley campus. Einstein had the idea that space-time has an internal energy density that does not change with time. He called this quantity the cosmological constant, but later repudiated it and called it his biggest mistake. Does your work confirm or refute this idea? It marks the spectacular success of Einstein's general theory of relativity. Several decades have passed since Einstein proposed his theory. In that time, we have discovered a great many exotic phenomena in the universe, all of which are consistent with his theory. Many have even been predicted using his theory. Not so long ago, astronomers couldn't even qualify for the Nobel Prize. You're right. I can name discoveries in cosmology that could well qualify for the Nobel Prize. The discovery of the expansion of the universe, that is, the size of the universe. Observations pointing to the existence of dark matter as a source of additional gravity. They are fundamental to our understanding of physical phenomena. You're only 41 years old. What are you going to do next? Well, there's a literary prize this week and then an economics prize. I'm kidding. Laughing before I knew about the Nobel Prize. I've started on a couple of interesting projects and I'm going to keep working on it. They have to do with the Hubble Space Telescope and the problem of measuring distances at closer intervals. Radio stars. Fast radio bursts is short for radio bursts. Both are among the most. It is difficult to capture their occurrence in the universe. Powerful radio signals appear in distant space for a few milliseconds and then disappear without a trace. They have been attributed to causes ranging from black holes to extraterrestrial intelligence. Only 18 fast radio bursts have been discovered to date. They're understandably short-lived. And a radio telescope can only view a small section of the sky. At any given moment, only orbits 12-1102. Repeated several times in 2017 Ears for Times with colleagues from Cornell University, Ithaca, New York, USA were able to pinpoint the position of this repeating radius close. They used data from the Karl-Janovsky Ultra-Large Antenna Array, consisting of 27 radio telescopes located in New Mexico, USA, as well as data from 21 telescopes of the European Array. These array antennas, working together, give much higher resolution than any radio antenna individually, which allowed astronomers to locate the radio burst 100,000 times more accurately than during previous attempts. It turned out that the radio splash is associated with a dim dwarf galaxy about 2.5 billion light-years away. Its diameter is 10 times smaller than that of the Milky Way. Knowing exactly where the radius burst is coming from can limit the number of hypotheses regarding its origin. Since this radius source is very far away, it must be extremely bright and have huge energy reserves. Most likely, other radio bursts also did not originate nearby, although there has been such a hypothesis. But we cannot completely exclude the assumption that orbits 12-1102 is a unique object, and other, fast radius luster have a completely different nature and belong to the non-repeating type. There are also quite exotic theories to explain the origin of fast radius bursts. For example, explosions of microscopic black holes or collisions of dark matter clots with black holes. A somewhat more prosaic explanation for the recurring PB 12-1102 bursts is that they come from the active galactic nucleus, but the same inclines to the fact that the radius close orbits 12-1102 and the almost constant source found nearby are associated with the remnants of a supernova, receiving energy from a young rapidly rotating neutron star. In principle, a host galaxy in the shape of 121102 is similar to those faint galaxies in which the brightest supernovae erupt. Scenario 4 is therefore tempting, though far from proven. The cry of a newborn black hole. In the 1970s, astronomers first recorded gamma-ray bursts. On average, they are randomly distributed in the sky and occur about once a day for a few seconds. These bursts release more energy than the Sun can produce in its 10 billion year lifetime. The shortest bursts usually last less than 1 second. They are currently thought to be caused by the merger of two neutron stars. Long bursts typically last from a few seconds to several minutes. Their origin is attributed to the explosion of stellar nuclei. When massive stars collapse, it's been observed that they coincide with very bright supernova explosions. One such gamma-ray burst, Jerry 080319b, could be seen in 2008. In the optical region with the naked eye, despite the fact that it occurred 7.5 billion light-years away from the Sun. The theoretical justification for long gamma-ray bursts is that along with the intense radiation during the flare and jets of matter descend and jets of matter at close to the speed of light. If the jets are oriented in such a way that they are aimed at Earth, they send directed radiation in our direction. Much of this radiation, because of the strong Pripyarovsky shift in the speed of jets near the speed of light, is recorded in the gamma range. What exactly happens at the center of the explosion is still unclear. Could it be that the collapse of the star results in the formation of a rapidly rotating neutron star with a powerful magnetic field? Such a star is called a magnet. It can strongly excite the surrounding matter, resulting in jets. Consider an alternative option: collapse of the star leads to the formation of a black hole. Then jets can be formed by the interaction of the black hole with matter falling into the black hole, as in a funnel. In either case, whether it is a neutron star or a black hole, the enormous energy for the motion of the central object is transferred to the jets. Which scenario is realized in the case of a gamma-ray burst can be understood by estimating the total energy released in the explosion. The energy of a rotating object depends on its mass, and we know the mass limit that a neutron star can reach before it becomes a black hole. And there is no mass limit for a black hole. So it can generate more energy than any neutron star. In 2010, Bradley and colleagues at Goddard Space Flight Center analyzed the four brightest gamma-ray bursts detected by the Fermi Gamma-Ray Space Telescope. The energy released in jets from the most powerful gamma-ray burst, Jerry 090926a, was as high as 1.4 per 10th degree joules. A neutron star can release no more than 3 per 10th degree, and only a small fraction of this energy will be released into jets. So the researchers are inclined to conclude that this burst, like the other three, was stimulated by black hole processes. At the same time, Stan from the University of California, Santa Cruz believes that this is true only for the most powerful gamma-ray burst, and weaker bursts can be explained by the activity of the magnet, since we see gamma-ray bursts from a very long distance. Scientists believe that their study can help in learning the history of the expansion of the universe from the earliest days, and through this, it may be possible to understand how dark energy behaves. But first we must figure out the mechanism of gamma-ray bursts to be able to calculate their true luminosity by analyzing fluctuations in their emission. If we are very unlucky and such a gamma-ray burst occurs in our own galaxy and is directed towards our planet, it could cause significant damage to the Earth. It is possible that gamma-ray bursts in our galaxy have caused mass extinctions of certain species of living organisms on the Earth historically. On the other hand, Thanks to them, genetic mutations could have occurred, as a result of which new diverse forms of life appeared. Cosmos upheavals. Virtually all the information we possess about the universe is obtained by us from analyzing electromagnetic radiation. While for several millennia the ancient astronomers who observed the sky had at their disposal only the visible range of wavelengths, in the last 100 years their capabilities have greatly expanded. Instruments have appeared that can detect radio waves, see infrared and ultraviolet radiation, and examine X-rays and gamma rays. The only exception was neutrinos. But as the reactor at the center of the Sun continues to work, the day will come when neutrinos will also be used to study the central regions of active galaxies. In 2015, scientists caught an entirely new type of signal. The experiment either detected gravitational waves, stretching and compressing spacetime from the collision of two black holes about 1,300,000,000 light-years away. In 2017, the Nobel Prize for this discovery was awarded to the three scientists who led the project: Rainer Weiss, Barry Barry, and Kip Thorne. The signal was picked up on September 14, 2015, by the two observatories of Nelepo in Ford, Washington, USA, and Livingston, Louisiana, USA. By the details of the waveform, it was possible to trace how two black holes with masses of 36 and 29 solar circled near each other, coming closer and closer until finally merged into a single black hole. The announcement of the discovery was a sensation among physicists and astronomers around the world. Gravitational waves would allow us to explore fundamental physical phenomena, study the strangest objects in the universe, and perhaps even peek into the earliest moments of its evolution. Then more findings followed. The lead collaboration caught gravitational waves from other pairs of colliding black holes. One of these phenomena was also observed at the Franco-Italian gravitational wave detector at the Argio near Pisa, Italy. The presence of this second detector allows astronomers to much more accurately determine the direction to the source, which in the future may help them to track hypothetical emissions coming from this point, the masses of black hole collisions, which were recorded in the second episode, were about 8 and 14 solar masses. It is in this range, according to the calculations of astrophysicists, should be the mass of objects arising from the collapse of stellar nuclei. But other events suggest that there is a population of black holes with masses between 25 and 30,500 solar masses. Before the experiment, either we knew nothing about this group of objects. Then, in August 2017, the ITER collaboration saw gravitational waves from a neutron-star merger for the first time. This event, which occurred 130 million light-years away, was also observed by other astronomers. About 70 telescopes and observatories around the planet and in space simultaneously turned to the same point in the constellation Hydra and found there a gamma-ray burst and afterglow in the visible range. This proved that neutron-star mergers can cause short-lived gamma-ray bursts. Astronomers witnessed the formation of heavy elements for the first time. The explosion produced enough gold to make a planet the size of Earth, as well as other heavy elements including uranium, plutonium, and lead. As more such signals are discovered, we will be in a position to refine our understanding of the evolution and structure of the universe. As a goal, observations of several black hole mergers may help us understand the nature of dark energy by the shape of the signal, the rise and fall of the frequency and power of gravitational waves. We can determine the size of the black holes and find out how intense the event was during its nucleation. Comparing the initial power of the event to the faint detector vibrations would either tell us how far away the event occurred, along with observations from standard telescopes. This could tell us about the expansion of space and the time it took for the gravitational waves to reach us. On that basis, we can estimate the extent to which dark energy is affecting space. Other types of detectors have joined the effort to find gravitational waves. The European Space Agency plans to develop a laser interferon, a metric antenna, and FOX, a huge space detector capable of picking up much longer wavelengths, including waves to be studied in the collision of two supermassive black holes. The technology for this detector has already been tested in the preparatory FOX space program under VIDA FOX Pathfinder. In the future, we can expect to see detectors operating at shorter wavelengths than either, which may allow us to pick up primary gravitational waves from a very young universe. These waves must have originated during inflation, the accelerated expansion in the first moments after the Big Bang. The results of these observations may even point us toward a theory of the great unification of the universe. Once upon a time, all fundamental interactions with nature itself were unified into a single entity. As the universe expanded and weighted, these fundamental interactions lost touch with each other due to events not yet understood. But the study of gravitational waves may shed light on these events. What's the most distant object we'll see in the universe? It seems surprising that the pages of scientific and popular science journals focus on a small galaxy rather than on intense gamma-ray bursts or superpowered quasars. Object N11 has a redshift of 11.09, and that's much higher than any other known object. If you want to know how many light-years it would be, it's a difficult question to answer. One indicator is the travel time of the light. The light from NZ11 traveled for 3,400 million years. But since that light left the source, the universe has been expanding, which has changed the overall picture dramatically. Among the various ways of measuring distance used by cosmology, the method of measuring intrinsic distance seems to be the most intuitively correct. The distance to the pz of the 11th dimension is thus 32 billion light-years. I would like to bring up the topic of solar eclipses and gravity. No matter how elegant a theory may be, it must be able to stand up to experimental scrutiny. So Einstein came up with a series of possible experiments. The first thing he looked at was the strange orbit of Mercury. When astronomers calculated the motion of this planet, they noticed something a little unusual. Instead of moving along a perfect ellipse, as Newton's equation predicted, it was shifting slightly, as if it were writing out peculiar petals to protect Newton's laws. The astronomers decided that there was a new planet inside Mercury's orbit, which they named Vulcan. They said that Vulcan's gravity was affecting Mercury, causing it to deviate from its expected path. As we saw earlier, this is the same strategy that allowed astronomers to discover Neptune. But there was no way to find any proof that a volcano existed. Einstein did some more calculations using his own theory of gravity, perihelion, and Mercury, and found that the planet's point of maximum approach to the Sun was a little different from what Newton had said. He was thrilled when the data matched his calculations. He figured that the shift in Mercury's orbit, which Newton and the theory of gravity couldn't explain, should be 42.9 arc-seconds per century. That was right on the money, matching the experimental results. Later on, he fondly reminisced about the experience, noting that he had been elated for a few days. My wildest dreams had come true. On top of that, Einstein figured out that according to his theory, the sun should deflect light. He figured out that the sun has enough gravity to affect the path of light from nearby stars. Einstein figured that since these stars could only be seen during a solar eclipse, he should send an expedition to observe the 1919 eclipse to test his theory. The astronomers were going to take 2 pictures of the night sky, one without the sun and one during the solar eclipse. The idea was to compare the 2 pictures and show that the position of the stars during the eclipse had been shifted due to gravity. The son Einstein was sure that the observations would back up his theory. When asked what he would think if the experiments didn't back up his theory, he said, "I'd think maybe God made a mistake." Einstein was confident that he was right because, as he wrote to colleagues, his theory was beautifully mathematical and symmetrical. Eventually, astronomer Arthur Eden ran this amazing experiment. His results matched Einstein's predictions pretty much exactly. Today, astronomers regularly use the curvature of light under the influence of gravity in their practical work. As it passes close to a distant galaxy, starlight from the curve is bent, as if in a lens. This phenomenon is called a gravitational lens or Einstein's lens. In 1921, Einstein was awarded the Nobel Prize. He quickly became one of the most famous people in the world, even more well-known than most movie stars and politicians. In 1933, he showed up at a movie premiere with Charlie Chaplin. Both celebrities were swarmed by autograph seekers, and Einstein asked Chaplin what all the fuss was about. Chaplin replied, "Nothing at all." He added, "I'm welcome because everyone understands me. You're celebrated because you're not easily understood." Naturally, the theory that put Newton on the physics map for the next 250 years was bound to get a lot of criticism. One of the people who were skeptical and spoke out against it was Charles Lane, who is a professor at Columbia University. After reading about the theory of relativity, he said, "I feel like I've wandered through Wonderland with Alice and had tea with a madman." Hatter. But Planck was always quick to give Stein a boost. He believed that new scientific ideas don't gain ground by winning over their opponents. Instead, they do so by outlasting them and being embraced by a new generation who've grown up with them. Over the decades, there have been repeated attacks on the theory of relativity, but each time it has been successfully tested. Einstein's theory of relativity changed everything. It transformed physics, revolutionized our ideas about the universe, its origin and evolution, and changed our way of life. One of the ways we can see Einstein's theory in action is in the global positioning feature in your cell phone. The etc. geolocation system has 31 satellites in Earth orbits. As it stands, your cell phone can receive signals from 3 of these satellites at any given moment. All 3 satellites are on different routes and at different angles to you. The phone's processor then looks at the data it's received from the 3 satellites and figures out your exact coordinates. GPS systems are so accurate that they have to take into account tiny corrections due to both special and general relativity theory in their calculations. Since the satellites are traveling at about 27,500 kilometers per hour, the clocks on the satellites run a little slower than on Earth because of the special theory of relativity, which says that time slows down at high speeds. This is shown in Einstein's thought experiment where he tried to outrun a beam of light. But since gravity is weaker the further out you go, time actually speeds up a little. The general theory of relativity, which says that gravity and space-time are connected, suggests that the weaker the gravitational pull, the faster time goes. This means that the special and general theories of relativity work in opposite ways. The special theory of relativity says that signals slow down, while general relativity says they speed up. Your cell phone accounts for both of these effects and tells you exactly where you are. If it weren't for the combined efforts of the special and general theories of relativity, you'd be in big trouble. Newton and Einstein couldn't be more different. Einstein has been hailed as the new Newton. As it turns out, Einstein and Newton were complete opposites. Newton was a bit of a loner and wasn't very social. He didn't have any close friends and struggled to hold a simple conversation. Physicist Jeremy Bernstein once said, "Everyone who had the chance to socialize with Einstein long enough came away from it with an overwhelming sense of the man's nobility." When you think of him, the word humanity comes to mind again and again as a symbol of the simplicity and attractiveness of his character. That said, there were a few things Newton and Einstein had in common. The first thing to note is their ability to concentrate and gather enormous amounts of energy in a single thought. Newton could get so absorbed in a task that he'd forget to eat or sleep. He could even stumble in the middle of a conversation and start writing on whatever came to hand. Sometimes he even jotted things down on a napkin or a wall. Einstein could focus on a project for years or even decades. While he was working on the general theory of relativity, he was close to a nervous breakdown. They also had another thing in common, which was their ability to visualize the problem and draw it out. Newton could have written the beginning using only algebraic symbols, but he chose to illustrate it with geometric diagrams instead. It's pretty straightforward to apply integral and differential calculus using abstract symbols. And replacing it with triangles and squares is something only a master can do. Einstein's theory also includes lots of diagrams with trains, peace flights, and clocks. Ultimately, Einstein came up with two significant theories. The first is the special theory of relativity, which describes the properties of light rays and space-time and introduces the concept of symmetry based on rotation in 4 dimensions. The second is the general theory of relativity, which shows how gravity affects space and time. But after these two huge achievements, Einstein was looking for a third, even bigger one. He was driven to create a theory that would unify all the interactions of the universe into a single equation. He wanted to use field theory to create an equation that combined Maxwell's theory of electricity and magnetism with his own theory of gravity. He spent decades trying to unify the two theories, but was unsuccessful. As it happens, it was Michael Faraday who first suggested combining gravity with electromagnetism. He used to come to London Bridge and throw magnets from it, hoping to find some way to measure how gravity affects them. But he didn't come up with anything. One of the reasons Einstein didn't succeed was that in 1920, there was a big gap in our knowledge of the world around us. It took a whole new theory of quantum for physicists to realize, finally, that at least one detail of nuclear interaction was missing from the equation. But Einstein, who helped develop quantum theory, ended up being its biggest critic. He was quick to criticize quantum theory. Since then, the theory has passed every possible test and has led to the creation of many amazing electrical devices that we now find in our homes and workplaces. However, as we'll see, Einstein's complex and nuanced philosophical objections to quantum theory still have a place in the ongoing discussion. It was a battle of the titans. On one side of the debate were Einstein and Schrödinger, who were instrumental in launching the quantum revolution. On the other side were Niels Bohr and Werner Heisenberg, who came up with the new quantum theory. The two sides finally met at the Sixth Congress in Brussels in 1930. It was there that the biggest debate of the era took place, with the giants of physics going head-to-head in a battle over the meaning of reality itself. Paul Owen Fest later wrote about it. I'll never forget how, right before my eyes, two opponents were leaving the university. Einstein was a great guy. He walked with a calm, ironic smile. Bohr was really upset and changed. Beside him in the hall, someone was muttering a single word to themselves, Einstein. Einstein. Pain. Einstein. Einstein went on the offensive, raising objections to quantum theory and trying to show how flawed it was. But Bohr was able to successfully counter Einstein's criticisms one by one. When Einstein brought up the idea that God doesn't play dice with the universe again, Bohr is said to have replied, "Stop telling God what to do." Princeton physicist John Wheeler said it was the most impressive debate he'd ever seen in the history of our intellectual development. In my 30 years in this business, I've never heard of a public argument between two greater men that lasted longer and dealt with a deeper issue with deeper implications for understanding this strange world of ours. Most historians agree that Bohr and quantum rebellion won that argument. But Einstein succeeded in showing everyone the flaws in the foundation of quantum mechanics. He demonstrated that this colossus is built on shaky philosophical ground. His criticisms are still relevant today. At the heart of it all is an intriguing idea from Schrödinger. He came up with a simple mental experiment, Schrödinger's cat, which really highlighted the essence of the problem. Imagine you put a cat in a sealed box and then put a piece of uranium in the same box. If an elementary particle flies out of the uranium, a Geiger counter will go off, which will then trigger a gun that will fire a bullet into the cat. So, is the cat alive or dead? Since the uranium atom is decaying in a way that's purely quantum, you'll need to describe the cat in terms of quantum mechanics. For Heisenberg, before you open the box, the cat exists as a combination of different quantum states, which means it can be described as a sum of two waves. One of these waves describes a dead cat, while the other describes a living cat. The cat isn't exactly alive or dead, but it's a combination of the two states. The only way to find out if the cat is dead or alive is to open the box and take a look. At that point, the wave function will collapse into a dead or alive cat. Simply put, observation, which requires consciousness, determines existence. Einstein thought this was all ridiculous and reminiscent of the philosophy of Bishop Berkeley, who asked the question, if a tree falls in a forest and there is no one around to hear it, does its fall produce a sound or a train? And they'd say no. But quantum theory went even further. It said that if there's a tree in a forest with no one around, that tree exists as a combination of different states, like a burned tree, a young sprout, a log, a leaf, or even plywood. It's only when you look at the tree that its wave function collapses into an ordinary tree. When Stone had guests over, he'd often ask if the moon existed just because a mouse was looking at it. But no matter how outlandish quantum theory seemed, no matter how much it contradicted common sense, it had one serious advantage: it was empirically correct. quantum theory has been tested and proven to be accurate to 11 decimal places, making it the most precise theory ever developed. Einstein was open to the idea that quantum theory had some truth to it. In 1929, he even put Schrödinger and Heisenberg in the running for the Nobel Prize in Physics. Even today, there's no consensus among physicists on the cat problem. The old Copenhagen interpretation of Niels Bohr, which says that a cat only appears because we observe it, is no longer popular. This is because we can now manipulate individual atoms and perform similar experiments using nanotechnology. The many worlds interpretation is more popular these days. It says that the universe is expanding in two, with the cat dead in one half and alive in the other. Quantum theory was a huge success, so physicists in 1930 decided to turn their attention to a different problem and go for a new prize. They set out to answer an age-old question: why does the sun shine? Since the beginning of time, many religions have placed the sun at the center of their mythology, deifying it. The sun was one of the most powerful gods in the sky. The Greeks believed that Helios, a shining deity, traversed the sky each day in a gleaming chariot, illuminating the world and bestowing life upon it. The Aztecs, Egyptians, and ancient Hindus all had their own versions of the sun god. But during the Renaissance, some scientists tried to examine the sun through the lens of physics. If our sun were made of wood or oil, all its fuel would have burned out a long time ago. If there were no air molecules in the vast expanse of open space, the sun's flame would have burned out a long time ago. So, the sun's endless energy remained a mystery. In 1835, scientists around the world were presented with a challenge. Auguste Comte, the French philosopher and founder of positivism, said that science is a powerful tool that reveals a lot about the universe, but there's one thing it can't explain. Even the smartest scientists will never be able to figure out what the planets and the sun are made of. It was a fair challenge because the foundation of science is based on facts that can be proven. All scientific discoveries must be reproducible and verifiable in a laboratory setting. But it was obviously impossible to bottle up solar material and bring it to Earth. So, this question would always remain unanswered. As it turns out, just a few years after Comte made his claim in positive philosophy, physicists were able to answer his challenge in a worthy manner. They found out that the sun is mostly made up of hydrogen. He made a small but important mistake in his reasoning. Absolutely. Science should always be testable. As we've already discussed, most scientific research is done indirectly. In the early 19th century, Joseph von der developed the most accurate spectrum to date. He used a time spectrum to show how light passes through a prism or other similar element, resulting in a solar eclipse and gravity on the screen. No matter how elegant a theory may be, it must be able to stand up to experimental scrutiny. So Einstein came up with a few possible experiments. The first thing he looked at was the strange orbit of Mercury. When astronomers calculated the motion of this planet, they discovered a slight anomaly. Instead of moving along a perfect ellipse as predicted by Newton's equation, it shifted slightly. This meant that Newton's laws needed to be updated. The astronomers decided that there was a new planet inside Mercury's orbit, which they named Vulcan. They said that Vulcan's gravity was affecting Mercury, causing it to deviate from its expected path. As we saw earlier, This was the strategy that let astronomers discover Neptune, but there was no way to find any proof that Vulcan existed. Einstein did his own calculations using his theory of gravity, perihelion, and Mercury to find the point of maximum approach of the planet to the Sun. He found a small deviation from Newton's laws. He was thrilled when the data matched his calculations. He figured that the mysterious shift in Mercury's orbit in Newton's gravity theory should be about 42.9 arcseconds per 100 years, which was right on the money compared to the experimental results. Later on, he fondly reminisced about the experience, noting that he had been elated for a few days. My wildest dreams had come true. On top of that, Einstein figured out that, according to his theory, the Sun must deflect light. He figured out that the Sun has enough gravity to affect the path of light from nearby stars, which only become visible during a solar eclipse. Einstein suggested sending an expedition to observe the 1919 eclipse to test his theory. The astronomers were going to take 2 pictures of the night sky, one without the Sun and one during a solar eclipse. The idea was to compare the 2 pictures and show that the position of the stars during the eclipse had been shifted due to gravity. The Sun Einstein was sure that the observations would prove his theory right. When asked what he would think if the experiments proved his theory wrong, he replied, "I'd think that maybe God made a mistake." Einstein was confident that he was right because, as he wrote to colleagues, his theory was beautifully mathematical and symmetrical. Eventually, astronomer Arthur Eden ran this amazing experiment. His results matched Einstein's predictions pretty much exactly. Today, astronomers regularly use the curvature of light under the influence of gravity in their practical work. As it passes close to a distant galaxy, starlight is bent by the curved space-time as if in a lens. This phenomenon is called gravitational lensing or lensing. Einstein. In 1921, Einstein was awarded the Nobel Prize. He quickly became one of the most famous people in the world, even more well-known than most movie stars and politicians. In 1933, he showed up at a movie premiere with Charlie Chaplin. Both celebrities were swarmed by autograph seekers, and Einstein asked Chaplin what all the fuss was about. Chaplin replied, "Nothing, absolutely nothing." He added, "I'm welcome because everyone understands me. You're celebrated because you're not easily understood." It's no surprise that a theory that challenged Newton's physics, which had been the accepted wisdom for 250 years, was met with fierce criticism. One of the people who were skeptical and spoke out against it was Charles Lane, who is a professor at Columbia University. For more information, please see the attached document. After reading about the theory of relativity, he said he felt like he'd wandered through Wonderland with Alice and had tea with a madman. But Planck was always there to give Einstein a boost. He wrote, "A new scientific truth doesn't gain the upper hand by convincing opponents of its correctness and making them see the light. It gains the upper hand by having those opponents die out over time and raising a new generation that's initially familiar with it." Over the decades, there have been lots of attacks on the theory of relativity, but each time it has been successfully tested. Einstein's theory of relativity changed everything. It transformed physics, revolutionized our ideas about the universe, its origin and evolution, and radically changed our way of life. One of the ways we can see Einstein's theory in action is in the global positioning feature in your cell phone. The Genius geolocation system includes 31 satellites in Earth orbits. As it stands, your cell phone can receive signals from 3 of these satellites at any given moment. All 3 satellites are on different trajectories and at different angles to you. The phone's processor then looks at the data it's received from the 3 satellites and uses the broadcast method to work out your exact coordinates. GPS systems are so accurate that they have to take into account tiny corrections due to both special and general relativity theory in their calculations. The satellites are traveling at around 20,500 kilometers per hour. The clocks on the satellites run a little slower than on Earth because of the special theory of relativity, which says that time slows down at high speeds. This is shown in Einstein's thought experiment where he tried to outrun a beam of light. But since gravity is weaker the further out you go, time actually speeds up a little. The general theory of relativity, which says that gravity and space-time are connected, suggests that the weaker the gravitational pull, the faster time goes. This means that the special and general theories of relativity work in opposite ways. The special theory of relativity says that signals slow down, while the general theory of relativity says that they speed up. Your cell phone accounts for both of these effects and tells you exactly where you are. If it weren't for the special and general theory of relativity, you'd be lost. Newton and Einstein are 2 very different thinkers. Einstein has been hailed as the new Newton. As it turns out, Einstein and Newton were complete opposites. Newton was a bit of a loner and wasn't very sociable. He didn't have any close friends and wasn't very good at having simple, everyday conversations. Physicist Jeremy Einstein once said, "Anyone who's had the chance to interact with him long enough has come away from it with an overwhelming sense of his nobility." When you think of him, the word humanity comes to mind again and again as a symbol of the simplicity and attractiveness of his character. That said, there were a few things Newton and Einstein had in common. The first thing to note is their ability to concentrate and gather a tremendous amount of energy in a single thought. Newton could get so absorbed in a task that he'd forget to eat or sleep. He could even stumble in the middle of a conversation and start writing on whatever came to hand. Sometimes he even jotted things down on a napkin or on the wall. Stein could also focus on a project for years or even decades. While he was working on the general theory of relativity, he was close to a nervous breakdown. They also had another thing in common, which was their ability to visualize the problem and draw it out. Newton could have written the beginning using only algebraic symbols, but he chose to fill his masterpiece with geometric ones instead. It's pretty straightforward to apply integral and differential calculus using abstract symbols, but replacing them with triangles and squares is something only a master can do. Einstein's theory also includes lots of images of trains, peaceful rivers, and clocks. Ultimately, Einstein came up with 2 significant theories. The first is the special theory of relativity, which describes the properties of light rays and space-time and introduces the concept of symmetry based on rotation in 4 dimensions. The second is the general theory of relativity, which shows how gravity affects space and time. But after these 2 huge achievements, Einstein was looking for a third, even bigger one. He was driven to create a theory that would unify all the interactions of the universe into a single equation. He wanted to use field theory to create an equation that combined Maxwell's theory of electricity and magnetism with his own theory of gravity. He spent several decades trying to unify the two theories, but didn't succeed. As it turns out, it was actually Michael Faraday who was the first to unite gravity with electricity and magnetism. He used to come to London Bridge and throw magnets from it, hoping to find some way to measure how gravity affects them. But he didn't find anything. One of the reasons Einstein didn't succeed was that in 11920 years, there was a huge gap in our understanding of the world around us. It took a whole new theory of quantum for physicists to finally realize that the puzzle was missing at least one piece of the nuclear interaction. But Einstein, who helped develop quantum theory, ended up being its biggest critic. He was quick to criticize quantum theory. Over the past 10 years, this theory has passed every test thrown at it and has brought us some pretty amazing electrical devices that we now find everywhere in our homes and workplaces. However, as we'll see, Einstein's complex and nuanced philosophical objections to quantum theory still have a place in the ongoing debate. It was a battle of the titans. On one side of the debate were Einstein and Schrödinger, who had both played a role in launching the quantum revolution. On the other side were Niels Bohr and Werner Heisenberg, who came up with the new quantum theory. The two sides finally met at the Sixth Kiev Congress in Brussels in 1930. It was there that the biggest debate of the era took place, with the giants of physics going head-to-head in a battle over the meaning of reality itself. Paul Reinfeldt later wrote about it, "I'll never forget how, right before my eyes, the two opponents left the university club. Einstein was a big presence and walked with a calm, ironic smile. Bohr was pretty upset, too. From the family next to him in the lobby, I heard Bohr muttering, 'Einstein, Einstein.' Einstein started challenging the foundations of quantum theory, highlighting what he saw as its flaws. But Bohr was able to hold his own against Einstein's criticisms, one by one. When Einstein brought up the idea that God doesn't play dice with the universe again, Bohr is said to have replied, 'Stop telling God what to do.' Princeton physicist John Wheeler said it was the most impressive debate he'd ever seen in the history of our intellectual community. In my 30 years in this business, I've never heard of a public argument between two greater men that lasted longer and dealt with a deeper issue with deeper implications for understanding this strange world of ours. Most historians agree that Bohr and the quantum rebels won the argument. But Einstein did succeed in showing everyone the flaws in the foundations of quantum mechanics. He demonstrated that this colossus is built on shaky philosophical ground. His criticisms are still relevant today. At the heart of it all is a fascinating concept, Schrödinger's cat. Schrödinger came up with a simple mental experiment that really illustrates the essence of the problem. Imagine you put a cat in a sealed box and then put a piece of uranium in it. When an elementary particle flies out of the uranium, a Geiger counter will go off, which will then trigger a gun that will fire a bullet into the cat. So, is the cat alive or dead? Since the uranium atom is decaying in a purely quantum way, you'll need to describe the cat in terms of quantum mechanics. Heisenberg believed that before you open the box, a move exists as a combination of different quantum states. In other words, it is the sum of two waves. One of these waves describes a dead cat and the other a living cat. The cat isn't technically alive or dead, but it's a combination of the two states. The only way to find out if the cat is dead or alive is to open the box and take a look. At that point, the wave function will collapse into a dead or alive cat. Simply put, observation, which requires consciousness, determines existence. Einstein thought this was all ridiculous and reminiscent of Bishop Berkeley's philosophy. Berkeley asked, if a tree falls in a forest and there's no one around to hear it, does it make a sound? Litzits. They'd say no. But quantum theory did even more damage. It said that if there's a tree in a forest with no one around, that tree exists as a combination of different states, like a burned tree, a young sprout, a log, a leaf, or even plywood. It's only when you look at the tree that its wave function collapses into an ordinary tree. Einstein used to ask his guests if the moon existed just because a mouse was looking at it. Well, no matter how outlandish quantum theory may seem, no matter how much it went against what we thought was true, the one thing it had going for it was that it was backed up by experiments. Quantum theory has been tested and proven to be 11 decimal places accurate, making it the most accurate theory ever. Einstein was open to the idea that quantum theory had some truth to it. He even put Schrödinger and Heisenberg in the running for the Nobel Prize in Physics in 1929. Even today, there's still no consensus among physicists on the cat problem. The old Copenhagen interpretation of Niels Bohr, which says that a cat only appears to be alive because we observe it, is no longer popular. This is because we can now manipulate individual atoms with nanotechnology, which allows us to perform similar experiments. The world interpretation, where the universe splits in two, with a cat dead in one half and alive in the other, is gaining popularity. Quantum theory was a huge success, and physicists were able to turn their attention to a different problem and aim for a new prize. They set out to answer an age-old question: why does the sun shine? Since time immemorial, many religions around the world have placed a deity, whether the sun, at the very center of their mythology. The sun was one of the most powerful gods in the sky. The Greeks believed that Helios, riding across the sky in his glittering chariot each day, illuminated our world and dear life. The Aztecs, Egyptians, and ancient Hindus all had their own versions of the sun god. But during the Renaissance, some scientists tried to examine the sun through the lens of physics. If our star were made of wood or oil, all its fuel would have burned out a long time ago. If there were no air in the vast expanse of open space, the sun's flame would have gone stale a long time ago. So, the sun's endless energy remained a mystery. In 1835, scientists around the world were faced with a challenge. Auguste Comte, the French philosopher and founder of positivism, said that science is a powerful tool that reveals a lot about the universe, but there's one thing it can't explain. Even the smartest scientists will never be able to figure out what the planets and the sun are made of. It was a fair challenge because the foundation of science is based on facts that can be proven. All scientific discoveries must be reproducible and verifiable in a laboratory setting. But it was obviously impossible to bottle up solar material and bring it to Earth. So, this question would always remain unanswered. As it turns out, just a few years after Kant made his claim in positive philosophy, physicists were able to answer his challenge in a worthy manner. They found out that the sun is mostly made up of hydrogen. He made a small but important mistake in his reasoning. Absolutely. Science should always be testable. As we've already discussed, most scientific research is done indirectly. In the early 19th century, Joseph von Braun developed the most accurate spectrum of his time. When light passes through a prism or other discrediting elements, it creates a rainbow on the screen. This shows how many rays with different wavelengths are in the light beam when it passes through the spectrum of sunlight on the background of the usual rainbow. The lines are narrow and dark. These lines form because electrons jump from one orbit to another, releasing or absorbing energy along the way. Each chemical element gives off its own characteristic lines, which are like chemical fingerprints. They allow the observer to determine what the substance under study is made of. Spectral lines have also helped solve many crimes. They can tell you where the criminal came from, what kind of boots he wore, what kind of dirt was on his boots, what kind of toxins were in the poison, what kind of microscopic fibers and hair were on the scene, and even what kind of chemical composition all the substances present had. It was the analysis of solar spectral lines that showed that the sun is mostly made up of hydrogen. On top of that, physicists found a new, unknown substance in the sun. They named it helium, which means solar. So, helium was first discovered in the sun, not on Earth. Not long after that, he and the astronomers made another significant discovery. By studying the light from stars, they found that these luminaries were also made of substances that are common on Earth. This was a huge discovery because it showed that the laws of physics were the same in our own solar system as they were in other places in the universe. This is true not just of the solar system, but of the universe as a whole. Once Einstein's theories were recognized, physicists like Arthur Ellington and Hans Peter put all the data together and figured out what fuels the sun's energy source. The sun's gravitational field is strong enough to compress hydrogen, which causes the protons to fuse with each other to form helium and then heavier elements. Helium is slightly lighter than the total weight of the hydrogen nuclei that fuse to create it. This means that the missing mass is converted into energy. Einstein's formula states that he is equal to ms squared. While physicists were debating the echelon flying paradox of their quantum theory, the storm clouds of war were gathering on the horizon. In 1933, Adolf Hitler came to power in Germany, and physicists were forced to flee the country in droves to avoid arrest or worse. One day, Schrödinger saw brown-shirted Nazis poisoning innocent Jews, ordinary passers-by, and shopkeepers on a street. He tried to intervene. They jumped on him and started beating him up. The beating stopped when one of the students recognized Schrödinger and told the others that he was a Nobel Prize winner in physics and had shocked them. He had left Austria soon after. The top scientists in Germany were leaving their country in droves, worried about the daily reports of repression. The always diplomatic Max Planck, who came up with quantum theory, asked Hitler directly to stop the mass exodus of German scientists, who were leaving the country because they didn't want to be part of the Nazi regime. But Hitler just yelled at him, blaming it on the Jews. Planck later said that it was impossible to have a conversation with such a man. Unfortunately, Planck's son was part of a group of conspirators who tried to assassinate Hitler. He was brutally tortured and then executed. For decades, Einstein was asked if his equation could help release the huge amounts of energy trapped inside the atom. Einstein always said no. The energy released by a single atom is too small to be useful. Hitler wanted to use Germany's scientific superiority to create powerful new weapons of terror. like the VE-1 and VE-2 rockets and atomic bombs. After all, if the sun is powered by nuclear energy, it stands to reason that the same energy source could be used to create superweapons. The breakthrough idea on how to use Einstein's equation in the real world came from physicist Leo Szilard. Even before him, German physicists had shown that the nucleus of Uranus can disintegrate into pieces when bombarded with neutrons, releasing additional neutrons and energy by splitting a single nucleus. SYL realized that the nuclear power of uranium could be amplified many times over in a chain reaction. When one uranium nucleus is split, two neutrons are released. The neutrons can then split two more uranium nuclei, which will release four neutrons. Then you get 8, 16, 32, 64, and so on. So, the number of uranium nuclei would grow exponentially, and so much energy would be released that you could level a major city. The discussions at the Kiev Congress, which had previously been abstract and theoretical, suddenly became a matter of life and death. The fate of the nation and, ultimately, the entire human civilization was at stake. Einstein was shocked when he heard that the Nazis were blocking access to uranium mines in Bohemia and classifying their work. Einstein was a pacifist, but he felt he had to write a letter to U.S. President Franklin Roosevelt, urging the U.S. to build an atomic bomb. After getting the letter, Roosevelt gave the green light to the Manhattan Project, the largest scientific project in history. In Germany, though, the Nazis put Werner Heisenberg, who was thought by many to be the best quantum physicist in the world, in charge of the atomic project. Some historians believe that Heisenberg was so close to the Allies in creating the atomic bomb that the Office of Strategic Services, the CIA's predecessor, developed a plan to assassinate him in 1940. Berg's MO, a former pro baseball player turned Brooklyn Dodgers team player, was given the job of killing Heisenberg if it looked like the German atomic bomb project was almost finished. Berg went to a lecture Heisenberg was giving in Zurich with orders to kill the physicist. You can read the full story in Nicholas Demidov's book. This evening was a bit of a spy mission. Luckily, the Nazi atomic project was a lot slower than the Allied project. It was underfunded and constantly behind schedule. On top of that, the base was being bombed by the Allies. And most importantly, Heisenberg hadn't yet solved the fundamental problem of creating the atomic bomb. He didn't know how much enriched uranium or plutonium was needed to start a chain reaction. What is critical mass? What they actually needed was about 10 kilograms of uranium-235. To put it another way, it was about the amount of uranium that could fit in a handful. After the war, it became clear that the equation from quantum theory was not just about atomic language, but could even affect the future of humanity. But people gradually started asking the same question they had before the war: how to create a complete quantum theory of matter, weak interactions, and ghost particles. Meanwhile, research on weak nuclear interactions, which are about 1,000,000 times weaker than the strong interaction, was also making great strides. The weak nuclear interaction isn't strong enough to keep the parts of many types of atomic nuclei stuck together. Instead, they break down into smaller pieces and elementary particles. As we've seen, radioactive decay is the reason why the Earth is so hot on the inside. The weak nuclear interaction is what gives rise to the energy behind eruptions, existing volcanoes, and earthquakes. To explain this interaction, a new particle has been introduced. For instance, a neutron is unstable and will eventually decay into a proton and an electron. This process is called beta decay. But to make calculations possible, physicists had to introduce a third term into the equation, a particle called a neutrino. The neutrino is sometimes called a ghost particle because it can paralyze entire planets and stars without any interaction or absorption. Right now, a stream of neutrinos from deep space is passing through your body, and some of it has already passed through our planet. On top of that, these particles could zip through a solid lead wall like it wasn't even there, creating a highway from Earth to the nearest star. Pauli, who predicted the existence of neutrinos in 1930, once said, "I have committed the unpardonable sin. I've introduced a particle that can't be observed." But as hard to find as this particle was, it was eventually seen in experiments. In 1956, when they were studying the strong radiation that came out of a nuclear reactor, physicists noticed that neutrinos don't interact with normal matter much. But they found a way to make up for this by using the fact that the reactor emits a lot of neutrinos. To understand the weak nuclear interaction, physicists introduced a new symmetry. The electron and neutrino are both weakly interacting particles. The idea was that they could be combined to create a new symmetry, which could then be combined with the old symmetry from Maxwell's theory. The resulting theory, called electroweak theory, combined electromagnetism and the weak nuclear interaction. The electroweak theory, developed by Steven Weinberg, Sheldon Shaw, and Abdul Salam, won them the Nobel Prize in 1979. So, light, instead of uniting with gravity like Einstein had hoped, actually chose to unite with the weak nuclear interaction. The strong nuclear interaction relies on the symmetry of Gell-Mann, which binds three quarks together to form protons and neutrons. The weak nuclear interaction, on the other hand, relies on a smaller scale symmetry, the permutation of the electron and neutrino, which unites with electromagnetism. But whatever the possibilities of the quark, the new electroweak theory describes the variety of elementary particles. There was still a big gap in the description. The question was, what was holding all these particles together? Maxwell's field had once so successfully predicted the properties we discovered in electromagnetism. Physicists started looking into a new version of Maxwell's equation. Jensen Young and Robert Mills came up with the idea. In 1950, instead of just one field that Maxwell proposed in 1861, this theory introduced a whole family of such fields. The same symmetry that Hermann used in his theory to rearrange quarks was used in this theory to replace Young and Mills fields with one another. The idea was straightforward. Since atoms are held in a bound state by an electric field described by Maxwell's equations, it stands to reason that quarks are probably held by what follows from a generalization of Maxwell's equations. That is, by Young-Mills fields. The same symmetry that describes quarks now applies to Young-Mills fields. For several decades, though, this simple idea was overlooked because when calculating the properties of Young-Mills particles, the result was again infinite, just like the kite. Unfortunately, none of the tricks that Feynman proposed at the time were enough to reshape Young-Mills theory. For many years, physicists tried really hard but couldn't find the ultimate theory of nuclear interaction. At last, one inventor, Dutch graduate student Herbert Hauw, had the courage and persistence to tackle the problem head-on and wade through the thicket of infinite terms to normalize the Young-Mills field. By then, computers were powerful enough to analyze these infinities. When his computer program produced a series of zeros representing quantum corrections, he was finally convinced he was right. Word of this breakthrough got the attention of physicists right away. Sheldon Shaw even said, "Either this guy is a complete idiot, or he is the greatest thing to happen to physics in recent years." His head-on solution to the problem earned both his supervisor, Martin Wildman, and him the Nobel Prize in 1999. This opened up a whole new field for linking known particles in nuclear interactions and explaining weak nuclear interactions in terms of quarks. The Young-Mill field was dubbed Glenn because it acted like glue. How do quarks bond with each other? Computer modeling shows that the Young-Mills field condenses into a similar pole substance, which then acts like glue, binding the quarks together. For this to happen, you needed quarks of 3 types or colors, which obey the 3 quark and gluon symmetries. This new theory of the strong nuclear interaction quickly gained widespread popularity. It was called the quantum limp dynamics of CAR-AD, and today it's the most famous way to describe the strong and nuclear interaction. The Higgs boson is what some people call the God particle. So, a new theory, called the Standard Model of Elementary Particles, gradually emerged out of the chaos. The confusion surrounding the zoo of elementary particles gradually gave way to a more orderly understanding. The Young-Mill field, called Leon, held quarks in neutrons and protons, and another Young-Mill field, called B. And particles showed how electrons and neutrinos interact. However, the Standard Model wasn't fully accepted until the Higgs boson, sometimes called the God particle, was discovered. Symmetry wasn't enough on its own. What was needed was a way to break that symmetry, because the universe we see around us is not perfectly symmetrical. If we look at the universe as it is now, it seems that all 4 fundamental interactions are independent of each other. At first glance, it seems that gravity, light, and nuclear interactions have nothing to do with each other. But if you go back in time, these interactions start to merge, if you can believe it, into one type of interaction at the time the universe was born. A new picture began to emerge in which elementary particle physics was used to explain the biggest mystery of cosmology: the Big Bang and the birth of the universe. It was a sudden leap from 2 very different fields of science. Quantum mechanics and the general theory of relativity started to look more and more like one and the same thing. In this new picture, at the moment of the Big Bang, all 4 interactions were merged into one super interaction that obeyed the main symmetry. This super interaction was capable of turning all the particles of the universe into each other. The super interaction followed the so-called God equation. Einstein and the other physicists are having trouble understanding it because of its symmetry. After the Big Bang, the universe continued to expand, and the super interaction and symmetry started to decay. This left behind the weak and strong nuclear interactions, which are more fragmented. In the Standard Model, this process is called symmetry breaking. So, we need a way to break the original symmetry exactly so that we can get the Standard Model. This is where the Higgs boson comes in. To get a sense of what this looks like, think of a dam. The water in a reservoir also has a kind of symmetry to it. If you bring all the water back in a circle, the total mass of water will essentially stay the same and look about the same as before. As we all know from experience, water always flows downwards. Newton said that water always tends to arrive at the lowest possible energy state. If the dam were to collapse, the water would rush downhill to occupy a lower energy state. So, the water behind the dam is in a higher energy state. Physicists call the state of the water behind the dam a false vacuum because it's unstable until the water arrives at a true vacuum, which is a state with minimal energy at the bottom of the valley. Once the dam breaks, the original symmetry disappears, but the water reaches its true resting state. You'll see the same effect if you look at boiling water just before it boils. The water is in a false vacuum state, meaning it's unstable but symmetrical. In other words, you can pull the entire mass of water and it will still look the same. But over time, tiny bubbles start to form. And each one is in a less energetic state than the surrounding water. The bubbles start to expand until they merge and the water starts to boil. This scenario suggests that the universe was originally in a perfectly symmetric state. All the elementary particles were part of this symmetry, and they all had zero mass. Since they had no mass, they could be rearranged at will without affecting the equation. But for some unknown reason, the universe was unstable and in a state of false vacuum. The Higgs field, like Faraday's electric field, which permeates all of space, is what's needed to transition to a true but collapsed vacuum. The Higgs field also filled all of space and time. But for some reason, the symmetry of the Higgs field started to break down. Small bubbles started forming inside the Higgs field. Outside these bubbles, everything stayed massless and symmetric. As the Big Bang evolved, some particles inside the bubble gained mass. The bubble grew quickly. The particles inside the bubble started to gain different masses, and the original symmetry was broken. It seemed that the entire universe existed in a new vacuum inside one giant bubble at last. By 11,970 years, the hard work of dozens of physicists was starting to pay off. After spending decades searching for answers, they finally saw the pieces of the puzzle coming together. They figured out that by combining three theories about the strong, weak, and electromagnetic interactions, they could create a system of equations that would really match what they were seeing in the lab. The trick was to create an ideal symmetry by combining three separate, smaller symmetries. The first of these symmetries described the strong nuclear interactions and allowed for the three quarks to be swapped around at will. The second symmetry described the weak nuclear interactions and allowed for the swapping of electrons and neutrinos. The third symmetry described the original Maxwell field. The resulting theory was a bit unwieldy, but it was hard to argue with its success. It's pretty amazing that the Standard Model could accurately predict the properties of matter in the past, up to a split second after the Big Bang. The Standard Model is a pretty unusual set of elementary particles that accurately describes our quantum universe. The Standard Model has 36 quarks and antiquarks, 12 weakly interacting particles and antiparticles called tones, and a whole bunch of young fields, Mills fields, and Higgs boson particles that come from exciting the Higgs field. At the same time, even though the Standard Model reflected our ideas about the atomic world the best, there were still a lot of gaps in it. First of all, it didn't mention gravity. This was a big problem because gravity is the force that determines how the universe behaves on a large scale. But whenever physicists tried to add gravity to the Standard Model, they couldn't get the equations to work. The quantum corrections, instead of being small, turned out to be infinite, just like in the case of quantum electrodynamics and the young Mills particles. So, the Standard Model can't help us understand some of the universe's secrets, like what happened before the Big Bang or what's inside a black hole. Second, the Standard Model is put together by combining different theories about how particles interact. So, the resulting theory is a bit of a patchwork quilt. One physicist made this comparison. It's like putting duct tape on a platypus, an ant, and a whale and saying that's nature's most elegant creation. In reality, such a creature would only be loved by its mother. Third, the Standard Model has a lot of unknowns, like the masses of quarks and the forces of interaction. On top of that, it has about 20 constants that had to be entered manually, without any understanding of where they come from or what they represent. Fourth, the Standard Model has 3 versions of quarks, electron ions, and neutrinos. In total, there are 36 quarks with 3 colors and 3 generations, along with their corresponding antiparticles and 20 free parameters. It was difficult for physicists to accept something so clumsy. It's the fundamental theory of the universe. Given the high stakes, many countries are willing to spend up to $1 billion to build the next generation of particle accelerators. The Large Hadron Collider, which is located near Geneva in Switzerland, is currently making headlines. It's the largest scientific device ever built, and it costs more than $12 billion. It's about 27 kilometers in circumference. The tank looks like a giant bagel that straddles the border between Switzerland and France. Inside the tube, the protons are accelerated until they reach extremely high energy. Next, they collide with another high-energy beam of protons traveling in the opposite direction. The collision releases 14 trillion electron volts of energy and creates a violent shower of elementary particles that scientists are trying to make sense of. Buck's job is to use the world's most powerful computer to recreate the conditions that existed right after the Big Bang. This will help produce these unstable particles. In 2012, the Higgs boson was finally discovered, which was the last piece of the puzzle for the Standard Model. It was a great day for high-energy physics, but scientists knew there was still a lot more to do. The Standard Model really does describe all particle interactions, from the depths of the proton to the farthest reaches of the visible universe. The issue is that it's quite complex. In the past, whenever physicists came up with new ways to describe the fundamental nature of matter, they also came up with new, elegant types of symmetry. It was hard to believe that, at the most fundamental level, nature could have favored such a sloppy theory. The Standard Model has had some great practical successes, but it was clear to everyone that it was only the start. This is just the start of a new, more definitive theory that we're still waiting to see emerge. Meanwhile, physicists, inspired by the amazing achievements of quantum theory in the study of elementary particles, started revisiting the general theory of relativity, which had been largely overlooked for several decades. Physicists were now aiming for the ambitious goal of combining the Standard Model with gravity. All that was needed was to come up with quanta and a theory of gravity. This would be a true theory of everything, where you could actually calculate all the quantum corrections for both the Standard Model and the general theory of relativity. Previously, the TRC theory was a clever way to account for all the quantum corrections to the Standard Model. The solution was to represent the electromagnetic and nuclear forces as particles called photons and Euclid particles. And then it was as if we were waving a magic wand to make all the convergences disappear, to compensate somewhere else. All the unpleasant infinities were conveniently ignored. Physicists followed the traditional approach and took Einstein's theory of gravity and introduced a new point particle of gravity, which they called gravity. So the smooth surface that Einstein was talking about, which was supposed to represent the fabric of space-time in his theory, turned out to be surrounded by a cloud of 1 trillion tiny gravitational particles. Unfortunately, the techniques physicists have developed over the past 70 years to get around tricky issues like this one didn't work in this case. The quantum corrections created by the tons were infinite and wouldn't go away. This is where physicists hit a wall. The good fortune had run its course. The physicists were frustrated, so they set their sights on a more modest goal. They couldn't create a complete quantum theory of gravity, so they tried to figure out what happens when you combine quantum and ordinary matter. They decided to leave gravity out of it for now. This meant calculating the quantum corrections due to stars and galaxies without affecting gravity, using quantum atoms on their own. The plan was to take it a step further and get a better handle on the bigger picture of formulating a quantum theory of gravity. This goal was more modest, but it led to the discovery of a whole new world of fascinating physical phenomena that challenged our understanding of the universe. Suddenly, quantum physicists were faced with some pretty unusual phenomena: black holes, ready-made norms of dark matter and dark energy, time travel, and even the birth of the universe itself. But the discovery of these strange cosmic phenomena also presented a challenge for the theory of everything. It had to explain not only the familiar elementary particles of the standard model, but also all the new strange phenomena that were pushing the boundaries of human imagination. So, at the turn of the 19th and 20th centuries, there were two major pillars of physics: Newton's law of universal gravitation and Maxwell's equation for light. Einstein saw that they were at odds with each other and that one would have to give way. Newton's decline in mechanics led to some major scientific revolutions over the next 100 years. It's possible that history is repeating itself today. Once again, there are two main areas of focus in physics. On the one hand, we have Einstein's theory of gravity on the largest scale, which gives us black holes, the Big Bang, and an expanding universe. On the other hand, we have quantum theory, which explains how elementary particles behave. The issue is that these theories are at odds with one another. They're based on different principles, use different math, and adhere to different philosophies. We are hoping that the next big breakthrough will bring these two pillars together. It all started in 1968 when two young physicists, Gabriel and Max Suzuki, were looking through some old math books when they came across a strange formula that the mathematician Leonard Euler had derived back in the 18th century. This strange formula seemed to describe how two elementary particles scattered. How could an abstract formula from the 18th century do that? Can you give me the results you got with the new gas pedals? Physics doesn't work that way. Later on, other physicists, including Jupiter, Holger Nielsen, and Leonardo Laskin, figured out that this formula showed how two strings interacted really quickly. They were able to create a whole bunch of equations that represented how multiple strings interact. The researchers were then able to introduce spinning particles into string theory. String theory became a bit of an oil well. All of a sudden, a whole new set of equations came into being. I wasn't happy with this because physics since Faraday's time had been represented by fields, which contained a lot of information in a small space. String theory, on the other hand, was a bunch of different equations that came together to create what we call string field theory. With our equations, we can reduce string theory to a single field theory equation that's no more than an inch long. As the stream of equations took shape, a new picture began to emerge. Why are there so many particles? As Pythagoras said more than 2,000 years ago, the theory is that every musical note and string vibration describes some particle. Electrons, quarks, and Young-Mills particles are basically just different notes on the same oscillating string. What's particularly interesting about this theory is that it includes gravity as a necessary element. It shows up in the theory without any extra assumptions, as one of the lower vibrations. String theory. What's more, even if Einstein hadn't come along, we could have discovered his theory of gravity simply by looking at the lowest vibration of the same string. As physicist Edward Witten once said, string theory is really appealing because it just makes gravity make sense. All the known, non-contradictory string theories include gravity. So, while gravity isn't possible in quantum field theory as we know it, it's a must in string theory. But as the theory started to develop, more and more incredible, completely unexpected features started to emerge. It was found that it could only exist in 10 dimensions, for example. This came as a shock to the physicists because it was completely unanticipated. Typically, a theory can be expressed in any dimension. We tend to rule out other possibilities because we're used to operating in a three-dimensional space. We can only move forward, backward, right, left, and up and down. If we add time, 4 dimensions are enough to locate any event in the universe. If we want to meet someone in Manhattan, we can just say, let's meet at the corner of 5th Avenue and 42nd Street on the 10th floor. At 12 o'clock. It's not possible for us to move in any other dimensions. No matter how hard we try, it's just not possible. On top of that, our brains just aren't wired to picture what it would be like to move in higher dimensions. That's why the study of multidimensional string theory is done using only mathematical methods. In string theory, though, the dimensionality of spacetime is fixed at 10 dimensions in other dimensions. The theory doesn't hold up mathematically. I remember when string theory suddenly suggested that we live in a 10-dimensional universe, and it was a pretty shocking idea for physicists. Most physicists saw this as proof that the theory was wrong. When John Schwartz, one of the top minds behind string theory, ran into Richard Feynman in the elevator at Skulltech, the latter often backed him up by asking, "John, how many dimensions are you in today?" Nevertheless, over time, physicists began to demonstrate that all competing theories had significant shortcomings. For instance, many of them could be dismissed because their quantum corrections turned out to be infinite or anomalous. That is, it's not consistent with the math. So over time, physicists started to accept the possibility that our universe might still be 10 peaceful. At last, in 1984, John Schwartz and Michael Green demonstrated that string theory is free from all the issues that doomed other contenders for the role of a unified field theory. If string theory is right, then the universe may have started out with 10 dimensions, but it became unstable and 6 of those dimensions somehow came back and became too small to be seen. This suggests that our universe might actually be 10-dimensional, but the atoms are too large to penetrate these tiny higher dimensions. Despite all the craziness of string theory, one thing keeps her relevant. It successfully brings together 2 major physical theories, general relativity and quantum theory, to create the ultimate theory of quantum gravity. This is what makes string theory such a hot topic. As I said earlier, If we add quantum corrections or the Higgs boson, we get a stream of convergence that we need to get rid of. But none of this gets us anywhere. If we try to combine the two main theories of nature, relativity and quantum theory, to apply the quantum principle of gravity, we break it down into energy packets or quanta, called gravitational quanta. Then we use gravity to calculate collisions with each other and with particles of matter like electrons. But when we do that, the whole set of tricks that we've come up with using the variable and the canvas don't work anymore. Quantum corrections caused by the mutual action of gravity with other concrete variables diverge and are completely unrecoverable by the methods found by previous generations of physicists. This is where we need to pull out all the stops. String theory is able to get rid of these problematic convergences that have been a headache for physicists for almost 100 years. And this is where the magic of symmetry comes in. Historically, a symmetric equation was seen as a good thing, but not something that was strictly necessary. In quantum theory, symmetry is the most important property of physics when calculating the collision of two capitons. The answer is infinite, which makes it meaningless. But when two strings collide, we get two parts, one from the boson and one from the fermi-ions. In string theory, these two sums cancel each other out, which helps us create a finite theory of quantum gravity. As we've seen, when we calculate quantum corrections for a given theory, they often turn out to be divergent, that is, infinite or anomalous, meaning they break the original symmetry of the theory. It's only been about 10 years since physicists realized that symmetry isn't just a nice-to-have feature of a theory, it's actually a central component. A symmetric theory can often get rid of the issues that come up in non-symmetric theories. Symmetry is the tool that physicists use to overcome the challenges posed by quantum corrections. As we've already seen, Dirac realized that his equation for the electron predicts that electrons have spin, which is a mathematical property of the equations. This resembles the usual spin we observe in everyday life. Later on, physicists discovered that all elementary particles have spin, but there are two types of spin. In some quantum units, spin can be either an integer, like 0, 1, or 2, or a half integer, like 1 or 2. 3 halves. Particles with an integer spin describe how the universe interacts. These include the photon and the Yang-Mills particle with spin 1, as well as the gravity particle with spin 2. They're called zones in honor of the Indian physicist Bose-Einstein, so we can say that natural interactions are carried by zones. Then there are the particles that make up the matter of the universe. They have an entire spin on the floor. These include particles such as electrons, neutrinos, and quarks with a spin of 1/2. These particles are called fermi-ions in honor of Enrico Fermi. We can also build other particles, like atoms, protons, and neutrons. So, the atoms in our body are made up of terms. There are two types of atomic particles, mixed matter and interaction zones. The variables include electrons, quarks, neutrinos, protons, and the basic photon. Young and Mills, in their book Concrete and Particles, Bondi, Sakai, and Jean Ruby then showed that string theory has a new type of symmetry called supersymmetry. Since then, the concept of supersymmetry has been expanded to become the most comprehensive symmetry ever discovered in physics. As we've already discussed, the beauty for the physicist is the symmetry that allows us to find the connection between different particles. Supersymmetry can bring all the particles in the universe together. As we've already discussed, symmetry allows us to swap parts of an object while keeping the original object unchanged. In this case, the particles swap places in the equations, with the boson moving in one direction and vice versa. The idea that particles in the universe can change places and turn into each other is a key concept in string theory. This means that every particle has a superpartner, which is either a particle or a superparticle. For instance, the superpartners of an electron are called leptons, while the superpartners of a quark are called quarks. An electron or neutrino is what we call a blind tone. But there's something pretty remarkable that happens in string theory. When we crunch the numbers for string theory, we get two main components. There are two types of quantum corrections, those coming from the Fermi ions and those coming from the boson. They're pretty amazing. They're equal in magnitude but opposite in sign. One of the terms can be positive, but at the same time, there's another term that's negative. When you add them together, they balance out and you're left with a final result. It's been about 100 years now since physicists have been trying to bring together relativity and quantum theory. But supersymmetry, the idea that enzymes and bosons are basically the same thing, lets a lot of infinities cancel each other out. It wasn't long before physicists found other ways to get rid of infinities, leaving a finite result. This is where the hype around string theory comes from. It has the potential to bring together gravity and quantum theory. No other theory can make that claim. This might get around Dirac's initial objection. He didn't like the renormalization theory because, even though it's had some great results, it suggested adding and subtracting quantities that are infinite dimensional. It seems that string theory is, as it stands, unreformable. This could even fit into the picture that Einstein himself proposed. He once likened his theory of gravity to a marble. It's just as smooth and polished as can be. Matter, on the other hand, is more like wood. A tree trunk falls in a chaotic coffin and has no proper geometric structure. His ultimate goal was to create a unified theory that would bridge the gap between marble and wood. In other words, he was aiming to create a theory that was entirely made up of marble. That was Einstein's ultimate goal. String theory can fill in the blanks in supersymmetry, turning marble into wood and vice versa. Marble and wood are two sides of the same coin. In this picture, marble is represented by lawns and trees by Fermi ions. We don't have any proof that supersymmetry exists in nature, but it's so elegant and beautiful that it's captured the imagination of the physics community. Steven Weinberg once said, "Although we can't see them, we can tell that symmetries are there in nature, influencing everything around us." They're a reflection of all the other ideas I've shared. The reality is that nature is actually much simpler than it appears. I'm more hopeful than ever that our generation has the potential to unlock the secrets of the universe. What else will we be able to tell in our lifetime? Why is everything we see in this vast universe of galaxies and particles so logical and inevitable? If we take everything we've discussed and summarize it, we can see that symmetry may be the key to unifying all the laws of the universe. Symmetry helps us make sense of the chaos of chemical elements and elementary particles. Mendeleev's periodic system and the Standard Model can create order by lining them up neatly and symmetrically. Symmetry helps us fill in the blanks. It helps us identify gaps in current theories, which in turn allows us to predict the existence of new types, elements, and elementary particles. Symmetry brings together things that you wouldn't normally expect to find together. It links together space, time, matter, energy, electricity, magnetism, change and symmetry, and shows us things we didn't expect. It's also predicted new phenomena like antimatter, spin, and quarks. Symmetry gets rid of unwanted consequences that could ruin a theory. Quantum corrections are often marked by catastrophic convergences and anomalies that can be fixed by symmetry. Symmetry tweaks the original classical theory. The quantum corrections to string theory are so strict that they actually change the original theory by fixing the dimensionality of space-time. It's thought that at the beginning of time, there was one single super interaction whose symmetry included all the particles of the universe. But the situation was unstable, and the symmetry started to break down. The first to separate was gravity, followed by the strong and weak nuclear interactions, leaving only the electromagnetic interaction. So today, the universe seems to be in pieces, and the interactions are very different from each other. The challenge for physicists is to put the pieces back together again to create a single interaction. Superstring theory has all the right ingredients. It has supersymmetry, boson symmetry, and variable supersymmetry. It's also the most comprehensive symmetry ever discovered in physics and can unify all the known particles in the universe. We still have to put the final pieces together to build string theory. We just need to identify its fundamental physical principles. The reality is that we still don't have a grasp on how to derive the entire theory from one single equation. In 1995, string theory underwent another big change, and the new theory was born. The issue with the original string theory was that there were 5 different versions of the quantum theory of gravity, each with its own specific definition. All 5 string theories looked pretty similar, except that the spins were organized a little differently. People started wondering why there were 5. After all, most physicists believe that the universe must be unique. Edward Witten, a physicist, discovered that there's actually a hidden 11-dimensional theory called the theory. It was based on membranes, like the surfaces of spheres and bagels, not just strings. He explained the existence of the 5 string theories by saying that it's possible to turn an 11-world membrane into a 10-world string in 5 different ways. Put another way, all 5 versions of string theory were different mathematical representations of the same underlying theory. So, in a way, string theory and theory are one and the same. The thing is, string theory is a way of reducing the 11-dimensional theory to 10 dimensions. But how can one 11-world theory give rise to 5 10-world theories? Just picture an inflatable beach ball. If you let the air out of it, the ball deflates and looks like a sausage. If you remove the remaining air, it turns into a string. So, the string is really just a membrane that's been deflated of its air. If you start with an 11-dimensional beach ball, you can show that there are 5 ways to deflate it, turning it into a 10-dimensional string. Or think back to the story of the blind men who first came across an elephant. One of them reached out and grabbed the animal's ear, saying that it was flat and 2-dimensional, like a fan. Another person felt the tail and thought the elephant was like a rope or a 1-dimensional string. A third person, who looked at the leg, decided that the elephant was actually a 3-dimensional drum or cylinder. But if you take a step back and look at it from a 3-dimensional perspective, you can see the elephant as a 3-dimensional animal. Similarly, the 5 different string theories are like an ear, a tail, and a leg. But we haven't yet had the chance to see the elephant and the theory in its entirety. As we've mentioned, new possibilities have emerged in string theory over time. Not long after the theory was first put forward in 1995, Cohen, a young Jenner, made another surprising discovery. He surprised the physics community by showing what was once thought impossible, that Young's-Mills supersymmetry theory, which describes the behavior of elementary particles in 4 dimensions, is actually mathematically equivalent to a certain string theory in 10 dimensions. This caused quite a stir in the physics community worldwide. By 2015, 10,000 papers had cited Young's work, making it the most influential in high-energy physics. There's a connection between symmetry and spirituality, but they're two different concepts. Symmetry happens when we rearrange the parts of one equation and the equation itself doesn't change completely. It comes about when we demonstrate that two completely different theories are actually mathematically equivalent. It's pretty remarkable that string theory has both of these highly non-trivial qualities. As we've seen, there's a tug-of-war between the electric and magnetic fields in Maxwell's equations. The equations themselves don't change. If you switch the two fields, turning the electric fields into magnetic fields and vice versa, you'll see that the equations remain unchanged. You can see this mathematically because electrons' magnetic equations often contain terms like E squared, plus squared, that don't change. When we rotate these two fields, turning them into each other, as in Pythagorean theorem. Similarly, there are 5 string theories in 10 dimensions that can be proven to be connected. In fact, they all represent a single 11-world theory. Farness demonstrates that the two theories actually represent 2 aspects of the same theory. Young showed that there's another reality between strings in 10 dimensions and Young-Mills theory in 4 dimensions. This was a complete surprise, but it had some pretty big implications. This meant there were some pretty surprising links between gravity and nuclear interactions, even though they were defined in very different dimensions. As a general rule, the ranges are found between strings of the same dimensionality, representing summands that describe those strings. For instance, we can often swap one string theory for another. This creates a whole web of loyalties between different strings and theories that are defined in the same dimensionality. But before there was a web of loyalty between two objects defined in different dimensions, it was a totally new phenomenon. This isn't just an academic question. It has major implications for how we think about nuclear interactions. As we saw earlier, the best way to describe nuclear interaction is with the gauges of binary theory in 4 dimensions, as presented by Paul Young-Mills. But nobody has ever been able to find a single exact solution for the Young-Mills field. But since Colibri's exact theory in 4 dimensions could be part of string theory in 10 dimensions, it means that the key to nuclear interaction could be the theory of quantum gravity. This was a game changer because it meant that the fundamental properties of the nuclear interaction, such as the mass of the proton, might be best described by string theory. This caused a bit of an identity crisis among physicists. Those who work exclusively in the field of nuclear interaction spend all their time studying 3-dimensional objects like protons and neutrons. They often dismiss physicists who engage in theoretical speculation in higher dimensions. But with the new range between gravitational theory and gauge theory, they are having to unlearn a lot of what they thought they knew. It seems that 10-dimensional string theory might be the key to understanding nuclear interactions in 4 dimensions. This unusual post led to another surprising discovery, called the graphical principle. A hologram is basically a two-dimensional sheet of plastic that contains a specially encrypted image of three-dimensional objects. If you point a laser beam at the flat screen, a three-dimensional image appears above it. In other words, all the information needed to create a three-dimensional image is encoded and applied to a flat two-dimensional screen. With the help of lasers, this is roughly how the 2x2 from Star Wars projects an image of Princess Leia. It's also how they create the haunted houses at Disneyland, where three-dimensional ghosts glide around you. This same principle applies to black holes, as we discussed earlier. If you throw an encyclopedia into a black hole, quantum mechanics says that the information in the book can't just disappear. So, where does it go? One theory suggests that the information is distributed across the surface of the black hole's event horizon. This means that the two-dimensional surface of the black hole contains complete information about all three-dimensional objects that have fallen inside. This has some pretty far-reaching implications for how we think about reality. We're pretty sure we're three-dimensional objects that can move in space and are described by three numbers: length, width, and height. But this might be an illusion. Maybe we all live in holograms. It's possible that the three-dimensional world we experience is just a shadow of the real world, which is actually made up of 10 or 11 worlds. Since we move in three spatial dimensions, it seems that our real selves move in 10 or 11 dimensions. As we walk down the street, our shadow follows us and moves like us, except that it exists in two dimensions. Similarly, we might think we see shadows moving in three dimensions, but in reality, our selves are moving in 10 or 11 dimensions. In short, string theory is revealing new and unexpected results as time goes on. This means that we still don't fully understand the fundamental principles behind it. It's even possible that we shouldn't be talking about strings at all. When you formulate the theory in 11 dimensions, strings can be described as membranes. This is why it's still too early to test string theory experimentally. Once we understand the fundamental principles, we can start to test it. Then we'll know for sure what string theory is all about. Is it a theory of everything, or just a theory? Not yet. Even though string theory has had some great theoretical successes, it still has its weaknesses. Given the ambitious claims made by string theory, it's no surprise that it's attracted a lot of criticism. I have to keep reminding myself of what Carl Sagan said: extraordinary claims require extraordinary evidence. I'm also reminded of Wolfgang Pauli, who had a knack for putting a person down while they were giving a presentation. He could easily say that what you said was so confusing that it was impossible to know whether it was nonsense or not. He also liked to say, "I don't mind you taking your time, but I'm not happy about you rushing things without thinking them through." If he was still around, he might well have had something to say about string theory too. There's such a heated debate going on that even the best minds in physics are split on this issue. It's been a while since science saw such a split. The last time was at the 6th Liverpool Congress in 1930, when Einstein and Bohr clashed over quantum theory. Nobel laureates have also had different views. Sheldon Shaw wrote, "Over the years of hard work by dozens of the best and brightest, not a single testable prediction has been obtained. It's not likely we'll see any progress on this front anytime soon." Herbert Holt went even further, saying that the interest surrounding string theory can be compared to that of an American TV series. That is to say, a great deal of advertising and hype with little substance. On the other hand, Some people think string theory is great. David Gross said that Einstein would have been happy with the goal, at least, if not the actual outcome. He would have been pleased to see that the foundation of this theory is a geometric principle that we don't fully understand yet. Stephen Weinberg likened the history of string theory to the search for the North Pole on old maps of the Earth. A huge, bottomless hole was shown where the North Pole should have been, but nobody ever actually saw it. It seems that everywhere on Earth, compasses pointed to this mythical place, but no one ever managed to find the notorious North Pole. At the core of their being, ancient sailors knew there had to be a North Pole, but no one could prove it. Some people even doubted that it existed. However, in 1909, after centuries of speculation and conjecture, Robert Peary finally reached the true North Pole. The critic of string theory and show knew he was in the minority in this controversy. He once said, "I'll find myself a dinosaur in a world of upstart mammals." There are a few big issues with string theory. Those who are critical of the theory argue that it is a solid, well-constructed theory, that beauty is not a reliable indicator of the truth of a theory, that it predicts too many universes, and most importantly, that it is unverifiable. The great astronomer Kepler was once influenced by the power of beauty. He was really drawn to the idea that the solar system was like a bunch of regular polyhedrons stacked on top of each other. 100 years ago, the Greeks identified 5 such polyhedrons, including the cube and the pyramid. Kepler noticed that by putting these polyhedra one after another, like a matryoshka doll, you could reproduce some of the details of the solar system. It was a great concept, but it didn't pan out. A few physicists recently criticized string theory, saying that beauty can be misleading and shouldn't be a criterion for physics. Just because string theory has some great mathematical properties doesn't mean it's actually true. They made a fair point that some beautiful theories don't lead anywhere. But poets often quote the poem Ode to a Greek Vase by John Keats in Beautiful Truth. In truth, beauty is the knowledge of earthly things, what it all means and what it's really about. Paul Dirac was definitely following this principle when he wrote The Scientist in his attempts to express the fundamental laws of nature. When it comes to math and form, the goal should be to create something that's aesthetically pleasing. He also discovered his famous theory of the electron not by digging into the data, but by playing with mathematical formulas. But just as beauty can be a powerful factor in physics, it can also lead us astray. As physicist Sabine Hodgson put it, filter. Hundreds of theories about unified interactions, new particles, additional symmetries, and other universes have disproven some of the most beautiful theories. All of these theories were wrong. In fact, they were all wrong in different ways. It's pretty clear that relying on beauty isn't the best strategy. Some say string theory is beautiful mathematically, but it might not reflect physical reality. There's some truth to that, but it's important to note that certain aspects of string theory, like supersymmetries, aren't completely useless for physics. Even though there's no evidence that supersymmetry exists, it still has value. It's been shown that a lot of the issues with quantum theory can be fixed by making some changes. The mutual compensating boson and enzyme supersymmetry lets us solve the long-standing elimination problem. The theory of quantum gravity has some flaws. Not every beautiful theory is useful in physics. But every existing fundamental physical theory has some built-in beauty or symmetry. Is there a way to test it? The main issue with string theory is that it's not testable. The energy associated with gravity is called dark energy, and it's 1 million times more powerful than the energy produced by the Large Hadron Collider. Just picture trying to build a tank that's 1 trillion times larger than the current one. If we want to test the theory directly, we'd probably need a particle accelerator that's a galaxy in size. What's more, each solution to string theory is like an entire universe. And there seem to be an infinite number of solutions. To test our theory directly, we'd have to create new universes in a laboratory setting. Put another way, only God can test this theory directly, since it's based on universes, not just atoms or molecules. So, at first glance, string theory doesn't seem to have the quality of a testable network that's essential for any theory. But that hasn't stopped its supporters. As we've seen, science usually relies on indirect methods. It's similar to how we study echoes from the sun, the Big Bang, and so on. We're looking for signs of the 10th and 11th dimensions, for instance. There might be clues to string theory all around us, but we should focus on the evidence rather than trying to observe it directly. One possible sign from hyperspace is the existence of dark matter. Up until recently, it was thought that our universe was mostly made up of atoms. Astronomers were pretty blown away when they found out that atoms like hydrogen and helium make up just 4.9% of the mass of the universe. As it turns out, the vast majority of the universe is hidden from us and exists in the form of dark matter and dark energy. Just to recap, dark matter and dark energy are not the same thing. In the universe, 26.8% of the mass is dark matter. This is invisible matter that surrounds galaxies and prevents them from flying apart. And 68.3% of the universe is made up of dark energy, which is even more mysterious. It's the energy of empty space that keeps galaxies apart and makes them scatter. Maybe the proof of the theory of everything is hidden in this invisible universe. Dark matter is a strange and invisible phenomenon. But it's what keeps the Milky Way galaxy together and prevents its stars from flying apart. Dark matter has mass but no charge. If you tried to take it in your hand, it would go right through your fingers as if they didn't exist, fall straight down through the floor, through the ground, and out the other side, where gravity would gradually force it to change direction and come back up to where you are. This is how it would fly from you to the other side of the Earth and back, without you noticing the Earth itself. As strange as dark matter is, there's no doubt it must exist. If we look at how the Milky Way galaxy rotates and apply Newton's laws, we find that it doesn't have enough mass to resist the centrifugal force at the speeds we observe. Given what we know about the universe, it seems reasonable to conclude that the galaxies should be unstable and falling apart. But they haven't fallen apart for 1 billion years. So, we have two options: either Newton's equations are wrong when it comes to galaxies, or there's some kind of unseen object that allows galaxies to remain intact. It's worth noting that Neptune was discovered in a similar way. The discovery of a new planet was crucial in explaining why Uranus' orbit differed from what the theory predicted. Right now, one of the top contenders for dark matter is what are called weakly interacting massive particles. One likely example of such a particle is the Fatima supersymmetric partner of photon. It's almost unstable, has mass, is invisible, and has no charge, which exactly matches the characteristics of dark matter. It's thought that the Earth is moving through an invisible stream of dark matter, which is likely to be present in your body at this very moment. When platinum hits a proton, it can cause the proton to decay into a shower of elementary particles that can be recorded today. There's a huge detector, about the size of a swimming pool, filled with fluids containing xenon and argon. It might one day catch the flash generated by a collision involving Fatima. Right now, about 20 groups are actively searching for dark matter, often deep underground in mines, away from cosmic rays. It's even possible that collisions involving dark matter could be registered by our instruments. Once this happens, physicists will start studying the properties of dark matter particles and then comparing them to the properties mentioned. Let's call her Fatima. If it turns out that string theory is right and the experimental results on dark matter match the predictions, it will be proof that physicists are on the right track. Another option is to develop the next generation of particle accelerators, which is something that's already being discussed. Once we've got the tank sorted, we can move on to the next step. The Japanese are looking into funding the International Linear Collider, which would involve shooting a beam of electrons along a straight tube and having them collide with a counterbeam of anti-electrons. If everything goes well, the facility should be up and running in about 12 years. The benefit of this collider is that it uses electrons instead of protons. Protons are made up of 3 quarks held together by members, so proton collisions always get pretty messy and produce a veritable shower of extra particles. The electron is a truly elementary particle, so its anti-electron collision is much cleaner and requires much less energy. The result is that at an energy of only 250 billion electron volts, these collisions should produce the Higgs boson. China has shown interest in building a circular electron-positron collider. We should start building it in 2022 and be done by 2030. The cost of building a collider like this is estimated at $5 million. This 100-kilometer ring will reach an energy of 240 billion electron volts. Physicists at CERN are planning a successor to BUT called the Circular Collider of the Future to keep up with their colleagues. It's expected to reach an energy of 100 trillion electron volts at some point. It'll have a circumference of about 100 kilometers, too. It's not yet clear if these gas pedals will ever be built, but it does mean there's a chance of detecting dark matter in the next generation of gas pedals. Once the Large Hadron Collider is up and running, if dark matter particles are detected, we could compare their characteristics to the predictions of string theory. Another thing these gas pedals could help us test is whether there really are miniature black holes. That's because string theory is a theory of everything. It covers gravity as well as elementary particles. So, physicists are expecting to find tiny black holes in the gas pedal. These tiny black holes are different from stellar black holes. They're harmless and have the energy of tiny elementary particles. They're what we call dying stars. As it turns out, the Earth is constantly bombarded by cosmic rays that are far more powerful than anything these gas pedals can produce, and there's no ill effect. There's still hope that we'll be able to use the greatest gas pedal of all time, the Big Bang itself. The radiation from the Big Bang might help us understand dark matter and dark energy better. It could even help us detect the echo or residual glow of the Big Bang. It's pretty easy to detect. Our satellites can detect this radiation with great accuracy. As you can see in the photos, the background microwave radiation is pretty smooth, with only a few small ripples here and there. These ripples reflect the tiny quantum fluctuations that existed at the time of the Big Bang and were then amplified by it. The question is whether there are irregularities or spots in this relic radiation that we can't explain. Some people think these are traces of collisions with other universes. In particular, there's a cold spot with some unusually cold markings on the otherwise uniform background radiation. Some physicists think this might be a remnant of some kind of connection or collision between our universe and some other parallel universe that occurred at the beginning of time. If it turns out that these strange marks are indeed evidence of our universe interacting with parallel universes, it might make the multiverse theory seem more plausible to those who are skeptical. There are already plans to place gravitational wave detectors in space, which would help us make more accurate calculations as far back as 1916. Einstein showed that gravity behaves like waves, spreading out from a stone thrown into a pond in concentric circles. The gravitational entities should spread through space at the speed of light, but they're so weak that Einstein thought it was unlikely they'd be detected in the near future. Einstein was right, but only in 2016. 100 years after he made the prediction, scientists were able to register gravitational waves for the first time. The detectors picked up signals from two black holes that collided in space about 1 billion years ago. Each of these detectors, which were built in Louisiana and Washington, covers an area of several square kilometers. They're shaped like the letter "S", with laser beams along each shoulder. The two beams meet at the base of the letter and form an interference pattern that's so sensitive to vibration that it can pick up traces of black hole collisions. The 2017 Nobel Prize in Physics was awarded to Rainer Weiss, Kit Thorne, and Barry Barish for their pioneering work. To achieve even greater sensitivity, there are plans to send gravitational wave detectors into outer space. The new system, which is called the Space Antenna for Laser Interferometer Three-Faces Blazer, Interferometer, Honey, and Space Antenna, might even be able to pick up vibrations from the Big Bang itself. One version of the design is a network of 3 satellites in space, linked together by a network of laser beams. The triangle would be about 2.5 million kilometers on each side. When the Big Bang's gravitational waves hit the detector, it'll cause tiny fluctuations in the laser beams that we can measure with sensitive instruments. The plan is to record the Big Bang shockwaves and then play them back in reverse to get the best possible view of the radiation. Before the Big Bang, we'd then need to compare the waves that existed before the Big Bang to what different versions of string theory predict. This could potentially provide some numerical data on the multiverse before the Big Bang. It might even be possible to get baby pictures of our universe with devices that are more advanced than faces. We could even find evidence of the umbilical cord that connected our newborn universe to the mother universe. Another common argument against string theory is that it suggests we actually live in 10 or 11 dimensions. However, there's no experimental proof of this. But this aspect can likely be verified with the tools we already have. If our universe is 3-dimensional, then the gravitational force between objects decreases in direct proportion to the square of the distance between them. This famous Newton's law helps our space probes navigate through space at 1 quadrillion kilometers with incredible precision. So, if we wanted to, we could easily guide our spacecraft through Saturn's rings. But Newton's famous law of inverse squares has only been tested at astronomical distances, not in the laboratory. It's possible that the gravitational force at short distances doesn't follow this inverse law, which could suggest the existence of higher dimensions. For instance, if the universe had 4 spatial dimensions, gravity would decrease in proportion to the cube of the distance. If the universe had n spatial dimensions, gravity would decrease in proportion to the first power of the distance between objects. However, it's pretty uncommon to measure the gravitational force between two objects in a lab. It's tricky to do these experiments because the gravitational forces in a lab are really small. The first measurements have already been taken in Colorado, and the results were negative. So, Newton's inverse square relationship still holds true. That just means there aren't any additional measurements. For theorists in Colorado, all these criticisms are a bit of a challenge, but not a deal breaker. What's tricky for theorists is predicting the existence of a multiverse of parallel universes, many of which are far more out there than anything you'd see in a Hollywood movie. String theory allows for an infinite number of solutions. Each one describes a different theory of gravity that's quite different from what we have in our universe. In many of these parallel universes, the proton is unstable. This means that all matter decays into a vast cloud of electrons and neutrinos. In these universes, the complex matter we know as atoms and molecules simply don't exist. They're made up of only a gas of elementary particles. Some might say that these alternate universes are just a mathematical possibility and not real. The issue is that our theory doesn't allow us to make predictions because we don't know which of these alternate universes are real. This is not just a problem with string theory, though. For instance, how many solutions are there to Newton's or Maxwell's equations? It depends on what you're looking at. If you start with light bulbs or lasers and solve Maxwell's equation, you'll find a single solution for each of these devices. But in general, Maxwell's and Newton's theories also have an infinite number of solutions depending on the initial conditions. So, we're back to square one. It's likely that this is a common issue with any theory of everything. Any theory of everything will have an infinite number of solutions, depending on the initial conditions. But how do we define the initial conditions of the entire universe? This means we have to introduce the Big Bang condition from the outside, manually. Some physicists think this is a bit of a cheat. It would be great if the theory could tell us what happened before the Big Bang, including the temperature, density, and composition at the beginning. The theory of everything should include its own initial conditions. In other words, we want to be able to make unambiguous and accurate predictions about the beginning of the universe. And string theory gives us a lot of options to choose from. Can it predict the universe we live in? Yes, it can. That's a bold claim, and it's been a goal of physicists for nearly 100 years. But can it predict just one universe? It's unlikely that it will. This is what's known as the landscape problem. There are a few different ways to approach this problem, but none of them have really caught on yet. The first is the test principle, which says that our universe is special because it contained us, beings who possess consciousness and can discuss the matter. Put another way, there could be any number of universes, but our universe is the one where the right conditions allow for intelligent life. The initial conditions of the Big Bang were set at the beginning of time in a way that allows intelligent life to exist today. It's possible that other universes may not have life. I distinctly recall my first introduction to this concept in second grade at school. Our teacher told us that God loved the earth so much that he placed it at just the right distance from the sun. If it were any closer, the oceans would have boiled, and if it were any further away, they would have frozen. Even then, as a kid, I was blown away by this logic that defined the nature of the universe. But today, we've got satellites that have discovered 4,000 planets orbiting other stars. Unfortunately, most of them are either too close or too far from their star to support life. So, you could see my teacher's reasoning in two different ways. Maybe there really is a loving God, or maybe there are 1,000 dead planets that are too close or too far away. And you and I live on one that's just right for sustaining intelligent life. Who's to say whose representatives can argue about such matters? Similarly, we can assume that we exist in an ocean of dead universes, and our universe is special only because we are in it and can discuss this issue. The anthropic principle also helps us understand another curious phenomenon. The fact that our universe exists at all is proof that the fundamental physical constants are just right for creating the conditions for life.